discrimination of these two states D1 and D2, then this distinguishability is given by the square root of 1 minus mod of inner product of D1 and D2 square. With this, you can show that there's a duality relation which is followed, and this duality relation has become sort of a standard for double slit experiment. This is more like Bohr's original idea that if you want to find out which slit the particle had passed through, in the previous approach, you are not actually finding out experimentally which slit the particle is going through. So this is also a quantitative statement of Bohr's complementarity principle. So these two different approaches have been there for a long time, since the very beginning, and people have been using them in disjoint ways. And many people have actually been confusing these two P and D very often, although these two pertain to very different kinds of experiment also. So the thing is that how are there is there a connection between these two duality relations? Then is there a connection between P and D? So this question has been there, but people have not been able to resolve it for a long time. Then specifically, if we go beyond two slits, then what happens in multi-slit scenario? Is the same similar kind of relations can be done, and the same kind of questions can be answered for multi-slit scenario or not. So now let us look at this n-path interference. So first, without any path detector. So without any path detector, as similar for this two-slit experiment, here you have n slits, and the state will be given as a superposition of psi1, psi2, psi3 till psi n. And if it is equally likely to go through all slits, this will be 1 upon square root n. All these constants C1, C2, C3 will be 1 upon root n. So path predictability then can be defined as like so. This is some work which we had done. So path predictability can be defined as this, where you can see it depends only on the diagonal elements of the density matrix of the quanton. For n equal to 2, this reduces to the same relation which I showed you earlier. This, this one, Greenberg-Yassens relation. So for n equal to 2, it reduces to the Greenberg-Yassen relation. One can have an alternate definition for this path predictability in this form, where it looks expression wise a bit simpler than this, and these two are related like this. P square is PQ into 2 minus PQ. So for n greater than 2, fringe visibility is not a good measure of wave nature. This is something which people had not realized, but I think in 2001 some experiments were done where they actually showed that fringe visibility is not a good measure of wave nature for interference experiments where n is larger than 2. In such a situation, one can show that normalized coherence can be a good measure of wave nature. So normalized coherence has been recently introduced, 2015 I think, by this Plenius group, and this has become a very hot area. So it is simply this sum of the mod of all off-diagonal elements of the density matrix. So obviously it is the basis dependent quantity, and if you put this, then this quantity becomes normalized. Now the question is that if you want to treat it as a good measure of wave nature, can coherence be measured in interference experiments? So first, let me show you why when why this visibility cannot be considered a good measure. This experiment was done in 2001, and where what they did was they did a four-pass interference experiment, and they flipped the phase of one of the paths by change the phase by pi, or rather flipping the phase, and they applied decoherence only on one path. Then they showed that even if they are applying decoherence on one path, it leads to an increase in fringe visibility. So this obviously flies in the face of complementarity, that this decoherence has the same effect as getting path information. If you get path information even in any small amount, it should always lead to a decrease in interference visibility. But here it leads to an increase in fringe visibility. So this led to a lot of debate, and people that time concluded that interference cannot be considered a good measure of wave nature for uh, multi-slit experiments. So coherence, interestingly, does not suffer from this issue. But the thing is that can coherence be measured experimentally? So then we had proposed this method of measuring coherence in multi-slit experiment. So first, let me show you how this is conventional visibility is defined. Conventional visibility is defined in this way, as I explained earlier. So in this experiment, you can see that this is Imax and this is Imin. So standard visibility is Imax minus Imin divided by Imax plus Imin. So what our proposal is that you take Imax, but you don't take Imin, you take uh, the intensity where if this uh, incoming wave is made incoherent, then interference would be gone and you would see this kind of thing. So then at this location, what will be the intensity? That is what we call I incoherent. So if you take I max minus I incoherent divided by incoherence, you can show that it just turns out to be equal to the coherence. So that is something which is very interesting. But for two slits, these two give identical answers. So this idea was, our proposal was also experimentally demonstrated recently in 2021 in this Nature paper. And I think Tanumai, who is part of this meeting, he is one of the authors of this. This is a Chinese group. So this has been experimentally demonstrated that coherence can be measured experimentally. Okay, so now let us consider an slit experiment in the presence of a path detector. In the presence of a path detector, of course, this psi1, psi2, psi3, they are all correlated with the states of the path detector, D1, D2, D3, and so on. So path distinguishability in this situation can be defined using what is called unambiguous quantum state discrimination. So as I told you earlier that the Englert considered minimum error path minimum error state discrimination. If you use minimum error state discrimination, it turns out that you cannot get a nice duality relation. It doesn't work. So this turns out to be very good. So the expression for this is the following. A very simple expression. So physically what it is the maximum probability with which one can unambiguously distinguish between n paths. Or rather, if you are given these n states d1, d2, d3 till dn, and they are not necessarily orthogonal to each other, then if you want to discriminate between them, what is the maximum probability with you can unambiguously distinguish without any error? So that is given by this. So another form of distinguishability we can define based on this only. So d square, and which is dq into 1 minus dq. You will understand the purpose of defining it this way also later. Okay, then you can show that wave particle duality relation can be formulated for n path interference in this way. So dq plus c less than or equal to 1, or if you are looking for a quadratic form of this relation, then it will be just d square plus c square less than equal to 1. So you can see d here is this. Without path detector, you can have these similar relations with predictability and path predictability. So now again, we are asking the question, how is dq physically related to pq, and how is d related to p? So predictability, predictability and distinguishability. So this dq which I had introduced, here I have written it in a slightly different form. I have actually added and subtracted this term, as you can see. And then I can write it as in terms of PQ plus this quantity which I call EQ. So EQ is given by this. And you can compare this with I concurrence. So you see I concurrence is of this form and our EQ is of this form. So you can see it is quite similar to I concurrence. Whenever there is a difference between these two, there will be difference. If difference between these two increases, difference between these two will also increase, and so on. So it is expected to behave in a similar way as I concurrence. So it has many properties of this an entangled measure. You can show that if the state is disentangled, then this will be 0. If it is maximally entangled, then this will be equal to 1. But of course, this is not a strict entanglement measure. One has to show that yet. So it has not been shown whether it is a strict entanglement measure. But the interesting thing that turns out is that with this, you can actually write the duality relation as a triality relation. PQ plus EQ plus C is less than or equal to 1. You can do a similar thing for D also, not DQ, the different form of distinguishability. Here also you can show that this is equal to E square, and E square is given by this. And again, E has many properties of an entangled measure, and for n equal to 2, this is actually exactly equal to concurrence. And again, the duality relation becomes a triality relation. So you can see that now here, these two kinds of relation involving predictability and distinguishability are actually merged into one conference. So this tells you how these two are connected, and also this tells you how predictability and distinguishability are connected. Predictability and distinguishability are actually connected through entanglement. Yeah, so this is a duality relation for n-path interference in the presence of a path detector. Then you talk of distinguishability, either this kind or this kind. If all path detector states are the same, then obviously the path detector is not entangled to the quantum anymore. In that situation, this itself reduces to PQ plus C. It reduces to this predictability relation. So here you can see that these two duality relations are actually connected through entanglement. You can actually measure, so this relation can be used to measure entanglement. Suppose you have a ancillary interference in the presence of some ancilla system. So there is a quantum going through multi-slit, and there is some ancilla here. So this quantum gets entangled with different paths of the quantum, but you have no handle on this ancilla. You can't probe this ancilla. But suppose you want to know how much it is entangled, how much is the quantum entangled with the ancilla. So now you can see this triality relation will hold in that situation also. So you can see that PQ can be measured experimentally. This is basically related to the intensities at different slits. Coherence, I showed you, can be measured experimentally. So now from the,
Hello,
uh, hello,
hello, hello.
yeah, Prabha, I can hear you.
Prabha has joined. So Prabha,
So
right?
I think
Yeah, you continue.
I'll continue. So so you can see that since there is an equality relation, if you can experimentally measure PQ and C, you can actually experimentally know what is the entanglement, degree of entanglement of this ancilla with the quantum. So I think this is something very useful. So this can be evaluated from the triality relation. So this all looks very nice. And so, but what is lacking? What is lacking, as you can see, is that EQ is somewhat like an entanglement measure, but it is not a strict entanglement measure. So can one do better than that? So then we came to know that Prasanta with his students, they were dealing with a similar problem. They had introduced a different form of predictability, and for visibility, they were using this Hilbert-Schmidt coherence. And my student Neha was in the meantime studying the same kind of Hilbert-Schmidt coherence to see whether it is a good measure for multi-slit interference or not, whether it suffers from the same problem as I had showed you in this 2001 experiment. So then we decided to work together, and then it turned out that we got some very nice and interesting results. So let me just show you those results in brief. So now visibility is now defined simply as this. So this, you know, is Hilbert-Schmidt coherence. Mod of this, mod of the off-diagonal elements of the density matrix. And this term normalizes this. Predictability is defined as this. So this predictability is of a somewhat different form than we had defined earlier. But for n equal to 2, it again reduces to the predictability of Greenberger and Yasin. And normalize I concurrence, as you all know, I concurrence is this with a 2 here. I think if you introduce this term, this becomes normalized. So this is I concurrence, and this term normalizes it. Then we can show that these three quantities, they satisfy a tight triality relation. P square plus E square plus V square equal to 1. You can also write this as, you can also from this say that distinguishability is P square plus E square. So now you know that since E is a strict entanglement measure, so this distinguishability and predictability are actually connected, quantitatively connected through entanglement. And these two kinds of duality relations are also connected through entanglement. So now you might say that you define this visibility in this kind of a way, expression wise it looks very nice and it is related to Hilbert-Schmidt coherence, but how do we experimentally measure it? So it turned out that the very interesting way in which it can be measured. So for a two-path experiment, as I showed you earlier, the visibility is just given by I max minus I min divided by I max plus I min. So now if you do this n-path interference experiment in a slightly different way, that you block all slits except the ith and jth slit, then for that interference, from IS and JS slate. If you measure the visibility, that you will define as this simply. So our end pass visibility turns out to be related to that. So what you do is you open only IS and JS slits and measure this Vij. Then you close these two slits and open another pair. So you repeat this same process for every pair. Then for all visibility for all the pairs, you square them, add them, and you multiply with this. This is basically what you are dividing it by the number of pairs. So this is actually, you can see, this is the root mean square of the visibility from pair of paths. So you can see this is equal to the visibility which we had defined. So very interestingly, this V is root mean square of the visibility from pairs of paths. Similarly, for distinguishability, you can show that if you open only two slits and measure distinguishability, so our n path distinguishability is just root mean square of the distinguishability of pairs of paths. So this was so beautiful and everything fits so nicely. So we were really happy about it, because you see that n path interference experiment and two path experiment are different. So you can't simply, by having, say if you have three slit experiment, you can't get the same interference by different two slit experiments. Is Urvachi's work on three slit experiment, which she has been doing, you can see from that three paths interference is not the same as sum of two path interference. But as far as this distinguishability and visibility is concerned, you simply can get n path interference from n path visibility and distinguishability from two paths visibility and distinguishability. Okay, so let me conclude. So the two kinds of wave particle duality relations involving predictability and distinguishability, they are related to each other via entanglement. Distinguishability is quantitatively connected to predictability via entanglement. The triality relation combines both kind of duality relations. So you can use this, if you use this triality relation, you don't need to use two different kinds of duality relations. And most importantly, triality relation may be used to experimentally measure experiment. So I hope experiment of that kind may be done in some near future. People are, there are some, I know some people who are actually doing this kind of experiments. Okay, that's all I have to say. Thank you very much.
Thank you, Kavich, for your beautiful talk. And now it's open for question and comment. Yeah, any question?
Good morning, Kavi sir.
Good morning.
Sir, is this result holds only for the pure states?
Yeah, we have shown it for pure states, but it should hold for mixed states also. But the thing is that then it will no longer be an equality. It will be an inequality.
Okay.
Yeah, so this relation will be an inequality for mixed states.
Okay.
What do you mean by normalization? What is normalization?
Yeah, normalization just means that its maximum value will be 1. Minimum is 0.
Yeah, Kavich, I have a question to ask because I have not followed the lecture fully. But when you are speaking about entanglement between what degrees of freedom here?
So entanglement is between the quantum, the particle which is passing through the multislit, and the path detector.
Yeah. So which property of the particle is entangled with this path?
The which no, and the paths of the particle, they are, so these are the special degrees of freedom of the particle. They are entangled with some degree of freedom of the path detector. So path detector, since I have not specified, it could be anything.
So maybe it is not the entanglement in the usual sense that which you can use for in quantum information processing, not in that sense.
No, it can be used in that sense also. It depends on the kind of experiment you are doing. Because in quantum information also people try to use spatial photonic spatial qubits and qubits also, as far as what I have heard. So since I have not defined what kind of path detector you are using, it could be anything. For example, it could be the spin of the particle.
Yeah.
So each path is correlated to one spin state of the particle, or it could be state of some other system. Not, it may not be the property of the particle itself.
But spin and polarization I understand, but when you are taking so many degrees, so many dimensions, I mean n number of slits, so I was wondering which property you are actually entangled with.
So then you can't, so it's difficult for that to use the property of the particle. Then you have to use an external system. You can have an external system with n degrees of freedom, and that gets entangled with the path of the particle.
Okay, thanks.
So people have actually done
Sir, one more question.
Yeah.
Actually, when you were talking about spin and path degrees of freedom, so we can talk it in single particle system also. Because in a single particle we have spin of that particle, spin degrees of freedom, and also it has some path degrees of freedom also. So in that sense we cannot talk about this entanglement, that is concurrence. So then how your result will take different form?
No, in single particle also you can, if your spatial degrees of freedom can get entangled with the spin degrees of freedom, then of course you can easily talk of concurrence. You just need two different degrees of freedom. They may be of the same particle, they may not be of the same particle.
Means you are talking about the entanglement between different degrees of freedom.
Right. So, for example, in Stern-Gillick experiment, what happens? Because of the magnetic field, particle has a amplitude to go in the upward direction or downward direction. And for the upward direction, the spin is up. For the downward direction, the spin is down. So here again, the spatial degree of freedom of the particle is correlated with the spin degree of the freedom of the same particle. So that entanglement is there.
Okay.
Okay, I'm not taking any more question because we're running a little bit late. Okay, thank you, Tabish, for your very good talk. Okay. So we are passing to our contributor.
Hello.
Yes.
Yes, sir. Yes, sir. I have one question.
Just quickly tell your question.
Okay, sir. Sir, this is Abdul from CSINTL. Thank you for nice talk, sir. I have one question regarding your. You have mentioned that the path detectors you are using D1 and D2, so they are normalized but not orthogonal. So for independent measurement, can it be done to be orthogonal or not? Is it possible to make the two path detectors orthogonal to each other, D1 and D2?
No, D1 and D2 are not detectors. They are different states of the same
detector. Yeah, different states. So can we make these two states orthogonal as well?
Yeah,
that is my question.
Of course, in reality, you want to make them orthogonal because you want to be sure, but it is always not possible. So I took the general situation.
Okay, thanks.
Okay, we are coming to our next talk. Next talk is by Natasha Avasthi. She is from DIT University, Dehradun, and she will be talking on universal quantum uncertainty relation between non-ergodicity and loss of information. So, Natasha.
Yeah.
Yes,
am I audible?
Yeah. You are audible.
Slides visible?
Slide visible.
Okay. Just a minute. Okay. Good morning, everyone. First of all, I would like to thank you and the organizing committee for accepting my talk to present my work here. So this is the topic basically, universal quantum uncertainty relation between non-ergodicity and loss of information. Okay. So these are the collaborators whom I work with them. Okay, so basically, before going to the main topic, let me introduce first with the dynamics of quantum system. Suppose we have a system so that we can control, and we have the rest part of the system called an environment is. So our main task is to define how does the small part of the whole quantum system behaves as the time passes. Here the system could be anything. It could be like a single atom. It could be like planet Earth or the black hole. But what else the system is the whole environment. So we know that according to quantum mechanics postulate, a closed quantum system undergoes unitary evolution, followed by, according to Schrodinger equation, we know that systems are not closed. Normally systems are, we cannot control the system. There is always some unavoidable, interaction with the environment. That could be electromagnetic radiations or some kind of vibrations in the room. So here the picture will tell you that this is the system and this is the environment. And here the line itself depicts that, that the system plus environment is a closed system. So, okay, I'm giving you a physical sense that give you how the system embedded in a composite system. Suppose you have a cup of water or a tea, which is not closed, that may, so that may interact with the environment, so that some particle may come into the cup of water or may go out of the water. So when we think of this cup of the water as independent quantum system, we have to go out of this Schrodinger equation. So a question can be asked that what is the most general evolution of a quantum system is, and that give rise to the dynamics of a open quantum system. Okay, so before going to the concept of noise in quantum mechanics, let me introduce with the concept of noise in classical mechanics. Suppose you have a hard disk drive which consists of bits, and after a long time the bit in the hard disk may flip with the probability p, and with the probability 1 minus p the bit remain unchanged. And for the single stage process, the output probability related to the input probability through this equation. So if we summarize this key feature, there is a linear relationship between input and output probability. There is something called a positivity requirement and completeness condition. So each of these key features has an important analogs in the theory of quantum noise. Okay, so this is the goal of quantum computation. Basically, suppose we want to create a well-defined state from this bunch of qubit. So we prepare all them in the zero state and add them all, and we want to act on the qubits with some unitary matrix. So we will have some arbitrary unitary matrix to perform arbitrary evolution. Basically, in physical sense, we do not handle such unitary matrix. So what we used to do in order to generate unitary, we have to generate this Hamiltonian. So here the Hamiltonian act on the system, but in reality, our system Hamiltonian not act on the system, but it act on some part of the environment, and that will create an additional value also. And this additional Hamiltonian will generate an entanglement between the system and environment. So this is basically the picture, that this is the Hamiltonian of the system that interact with the environment. So our Hamiltonian will act an entanglement between the system and environment. So the state cannot be defined as a pure state, but it can be defined in terms of something called a density matrix. So we know that we are familiar with this somehow operator sum representation in open quantum system. Suppose the state, the initial state, which is assumed to be the direct product state of both system and environment, which undergoes the unitary evolution. So in order to get the reduced density matrix, we will take the trace part of the environment, and with the assumption that the density matrix of the environment can be represented in terms of this, in terms of this basis. So if we evaluate the trace, here I divided this, this lambda into two parts so that it looks symmetric, and this density matrix after evaluating the trace is represented in the form of this operators, and these are basically known as the cross operator. So cross operator basically define the evolution of the open quantum system provided by the uncorrelated initial condition. So these are some of the properties of the OSR, operator sum representations, and these are the three common channels. One must be familiar with this. Okay, so let me come to the main topic first. So this is the work, basically the universal quantum uncertainty relation between non-ergodicity and loss of information. We know that in practical situation, it is impossible to completely isolate a quantum system from its surrounding and subjected to information loss due to dissipation and decoherence. So in modeling an open quantum system, the simpler approach is to consider the environment to be memoryless, that is Markovian. So the system environment relation is, however, more often that not non-Markovian, and there are possibility of information backflow into the system, which is considered as a resource in a quantum information theoretic task. So in Markovian evolution, this information flow is one way, and that quickly leads to an unwanted total loss of coherence and the other quantum characteristics. So basically what we have done, we quantify the loss of information in quantum system due to environment interaction in terms of some distinguishability measure for quantum state. So the loss of information denoted by this I delta t at any instant of time, and that can be quantified by the difference between the distinguishability between the pair of state, this rho 10 and rho 20, and that of instantaneous pair of state rho 1t, and this is rho 2t. Followed by this condition that the valid distance measure must satisfy the following condition. So a class of distance measures satisfying these conditions may include the trace distance, Hilbert-Schmidt distance, and Lewis distance. Here in this work, we consider trace distance as one of the distance measure. Then to draw the connection with non-ergodicity, we define here the density matrix in terms of this long time average state, and the information loss for the long time average state can be represented by this equation, which is lower and upper bounded by 0 and 1 respectively. Okay, so here we introduce the term of non-ergodicity. I mean, ergodicity basically plays a important role in quantum statistical mechanics to describe the realization of reversible relaxation of the system to the thermal equilibrium. So ergodic hypothesis states that if a system evolves over a long period of time, so the long time average state of the system is equal to the thermal state, which correspond to the temperature of the environment. So using the symmetric property and the triangular inequality, we arrive at the uncertainty relation between non-ergodicity and average loss of information. So the above inequality, okay, this is another result. The above inequality help us to overcome the drawbacks of the relative entropy, which was now satisfying the last two property. And in our work, we are able to overcome the drawbacks here. Then again, we have generalized up to now we have considered an arbitrary density matrix of arbitrary dimension, and we now restrict ourselves to the case of a two-level system as an example to further understand the connection between non-ergodicity and information loss. For a two-level system, the pair of state that is maximize the trace distance is located on the opposite side over the block sphere that are pure and mutually orthogonal. Therefore, in the case of trace distance, the uncertainty relation is represented by this equation. And then we consider our system to a spin bar. I mean, non-ergodicity and information backflow in a central spin model. So in this work, in this section, we consider another non-Markovian model, and we study the status of the uncertainty relation The system here consists of a single qubit that is interacting centrally with n non-interacting spin. So the total Hamiltonian of the system is given by the Hamiltonian of the system plus Hamiltonian of the bath and the Hamiltonian of the environment, where the sigma k, or we can say sigma z, are the Pauli spin matrices, and alpha is the coupling strength. So we just derive the exact reduced dynamics of the central spin after performing the Schrodinger evolution for the total system and the bath by tracing out the bath degree of freedom. And the reduced dynamics of the system can be calculated by this expression. And this is basically the results. Here in this plot, we plot this information loss with the time, keeping n as a parameter, spin as a parameter. We see from this plot that with the increasing number of the bath spin, the loss of information also increases. So the instantaneous loss of information shows oscillatory behavior, whose damping, oscillation usually decreases with time, and it is independent of the system parameters. And with the increase of the number of spin in the bath, temperature as well as the increasing strength can be seen as the increase of influence of bath on the system. So in case the loss of information increases with the respective increase. In the second picture, in the second figure, here the plot of I, this delta t with time, keeping alpha as a parameter, and we can see from the plot that with the increasing interaction strength, the loss of information also increases. Similarly, here we can see from this plot that with the increase in the bath temperature, the loss of information increases. So this is basically the histograms of I delta t and the non-ergodicity with the increase of the spin bath interaction strength with the number of spin baths, say n equals to, here we consider in our work n equals to 1000, and the temperature is a parameter, and we can see from the plot that with increasing interaction strength, the sum of the information loss and non-ergodicity decreases and finally saturates. So we can also see that with the increasing temperature, some decrease and come closest to 1, which is the lower limit. And this is again all the quantities except this t. We fix here t to some values, and for a reasonably low temperature in the bath, we observe that the sum of loss of information and the measure of non-ergodicity coverage to a relatively high value than saturated value of unity. So this is the plot, the uncertainty relation, where whenever the information loss increases, non-ergodicity decreases. So these are the concluding remarks. We establish an uncertainty relation between information loss and measure of non-ergodicity. The relation holds for arbitrary quantum system that is interacting with arbitrary environment, and the elements of uncertainty relation are quantified by some distance measure, and here we consider trace distance in our work. This relation shows that for non-ergodicity, the lower bound of information loss decreases, which believes that non-ergodicity plays an important role to preserve the information of quantum state under the lossy evolution. Interestingly, we have found the uncertainty relation saturates. So that's all. Thank you.
Thank Natasha for your nice talk.
Yeah, thank you, sir.
And you have finished in time. So now it's open for question. Any question? If there is any question, you can speak. No question. So if there is no question, let us thank the speaker once again, and we move to our next speaker, Devashi Shah from SN Bose National Center of Basic Science. And Devashi actually is very well known in the community, though he's very young. He had done some works even when he was a student at either Kolkata. Now it's turn of Devashish. Okay, Devashish, you take over.
Yeah. Yeah.
Devashi,
Can you?
share your
Yeah.
screen and start your talk.
Okay. Yeah. So is it visible now?
Yeah, it is visible.
Okay.
Yeah, it's full screen.
Okay. Yeah. So thank you for this nice introduction. So firstly, I thank the organizer for organizing such a splendid conference. Let me also add that I know many Indians who are working on quantum information and foundation in India and also in abroad had gained their initial interest on this topic from ISI Kolkata SN Bose Center, and I'm one of those people. So I thank Guru Prasad sir, Archon sir, Manik da, and also the other organizers for introducing this topic to many young students in India. Well, so today I will talk about one of our recent work on unbounded advantage in communication complexity and quantum key distribution based on contextuality proofs, which is done in collaboration with Shashank Gupta, who has submitted his thesis from SN Bose Center, Jen Peng, who is a postdoc in Germany, Professor Adan Cabello, whom we all know, and Professor Achon Mojumdar from SN Bose Center. Yeah, so let me first define what is communication complexity task and what do I mean by contextuality proofs. So here we have a sender, Alice, and a receiver. So in each run of this task, Alice receives some classical input variable x that may take some values from 1 to n and encode this input in some physical system and send that physical system to Bob, and Bob receives some input y also from a set of classical natural numbers and output some variable z, and Bob wants to get some function of their input x and y, and we take here the functions to be binary for simplicity. Okay, and the figure of merit of this task is given by this expression. So the probability of z should be equals to the function of xy given the input xy, and we have some weights for different inputs that we denote by txy. And here the restriction is that the dimension of the communicator system by Alice is upper bounded by some value, let's say d. Okay, so and these two devices may share arbitrary classical randomness. So if it's a classical communication, so depending on the input x and the random variable lambda, Alice would send some message m, and after that Bob receives that message and the input, and depending on the lambda, Bob outputs the variable z, and the lambda could be arbitrarily large, but the message should take one of like the different possible values. So this is how we obtain the probabilities in classical communications, and for quantum communications, Alice would send some quantum state that should act on d-dimensional Hilbert space, and the measurement on Bob's side should be represented by some positive operators, and then we get the probability according to the bond rule. And we can also ask that what is the minimum dimension of the physical system that is required to communicate to achieve to accomplish this task perfectly, so like such that the value of s is 1, and this is normally referred to the complexity of this task. So qf is basically the dimension of the quantum system that is required, and cf is the dimension of the classical system that is required to guess this function f of xy. And quantum advantage would mean that classical complexity is higher than the quantum complexity. Right. Now the witness, any witness of Cochin-Specker contextuality can be described by three things. One is a graph with some weights and the quantum states and the set of projectors. So we consider the simplest graph, and a graph basically consists of a set of vertices and a set of edges. So every vertex basically represents a projector, and if two vertices are connected by some edge, that means those two respective projectors must satisfy the orthogonality conditions. So this basically specify the scenario. And these weights, so these are basically positive numbers that are associated with each vertices. So let's say there are n vertices of this graph, and these are like the positive numbers, and this basically defines the weakness of the contextuality. So here we basically consider the probability of getting outcome corresponding to projector pi I for the state rho, and then we take the sum over all possible probabilities with the weights omega I, and if this quantity is greater than the independence number of this weighted graph, then we have a weakness of contextuality. So you may think that this independence number is the non-contextual or the classical value of this expression. So for example, we can consider this graph with 5 vertices and 5 edges, and let us consider all the weights to be 1 for 5 vertices, and the independence number of this graph is 2, and the fact that there exists like 5 projectors such that they actually satisfy the orthogonality conditions according to the 5 edges, and also there exists a state in dimension 3 such that this quantity is greater than the independence number. So I need 2 more definitions. One is the minimal weakness of contextuality. So suppose we have a weakness of contextuality and where the state and the projectors acts on, let's say, d-dimensional Hilbert space, and it is a minimal weakness if there doesn't exist any weakness in lower dimension. So basically a weakness is minimal if it is realized in the minimum dimensional Hilbert space that is possible. Okay. And also we know the notion of state independent weakness of contextuality, where we don't have the state. It is defined by the graph and the set of projectors, such that for all state we have the contextuality weakness. So for example, here this is a graph of 13 vertices that like follows these certain edges that have certain edges, and if we consider like the weights of those vertices to be in certain numbers, then there exists like 13 projectors such that for all state we have a weakness of contextuality. So before moving to some details, let me just present you the sketch of the results. So we basically showed that for any minimal weakness of contextuality, there exists a communication complexity task such that the quantum strategy, which is solely based on the proofs of the contextuality, provides advantage over any classical communication. And among those tasks, if the weakness is state independent, then we can have unbounded advantage. I will like go into the details. What do I mean by unbounded advantage? And also based on those communication tasks, we can have a key distribution protocol that is semi-device independent, and we can also derive some security against eavesdropping using some monogamy relation of the non-contextuality weakness. Okay, so now let me go into some details. So suppose we have a minimal proof of contextuality, and here we take the projectors to be the rank 1 for simplicity, and this acts on dimension D. So first we have to consider an extended graph where each vertex belongs to D-clique. D-clique means a set of vertices that are like a set of D vertices that where each pair of the vertices are connected by edge. Okay, So here, so for example, in this 5 cycle, so we have the minimal dimension where we can have contextuality witness is 3 dimension. So, and then we have to add some extra vertices like 6, 7, and 8, such that each vertices belongs to a triangle. Okay, so yeah, so basically we extend the set of projectors in such a way that each vector belongs to a basis. And then the task is as follows. So the x basically takes the values from the set of vertices. So x basically takes one of the vertices, b one of the vertices, and the additional input 0, and y is also be one of the vertices of this graph. And the function that Bob wants to guess is basically as follows. So if x and y are same, then the function is 0. And if y belongs to the neighbor of x, that means like y is the vertex that is connected with x by some edges, then the function is y. And if x is 0, the additional input, then the function should be 0 for y 1 to n. And if y is not equals to x and y doesn't belongs to the neighborhood of x, then we basically those runs doesn't count in the figure of merit. Okay, so for example, in this graph, if x is equals to 1, we are also only consider y to be 1, 2, 5, and 6. Well, so this is the figure of merit. If x is equal to y, we want the output to be 0. If y belongs to the neighborhood of x, we want the output 1. And if x is equal to 0, irrespective of y, we want the output to be 0 with the weights, that is omega y. And this basically comes from the weights of the vertices from the contextuality proof. And so let me give a quantum strategy where for input x, Alice basically sends the rank 1 projector that corresponds to that vertices to Bob. And Bob basically measures 2 outcome measurement, and the measurement effect corresponds to the 0 outcome. For input y is basically the same projector, and for x is equal to 0, Alice basically sends the state rho. And if you calculate, then you will see that the first 2 terms will be perfectly accomplished. So this should be the maximum value in this strategy, and this quantity is basically the left hand side of the contextuality witness. And you can show that in any classical communication, the value of this figure of merit is bounded by this value, where delta is some non-negative numbers. And since this is greater than the independence number, by the definition of the contextuality witness, we have advantage for any contextuality witness. So there are some graphs which there are some graphs for which the chromatic number is greater than d. And what is chromatic number is basically if I want to color all the vertices of a graph such that no 2 vertices that are connected by edge are assigned the same color, then the minimum number of color that we require to color that graph is known as the chromatic number. And there are graphs where the chromatic number is greater than the dimension d. Okay, so this is the minimum dimension where we basically can realize the graph by assigning projectors, right? So delta here is basically the number of vertices that cannot be colored when d colors are used to color the graph. So d is basically positive when we have such condition, otherwise d is basically 0. So now we only consider those graphs where the chromatic number is greater than d, and we know that for any state independent contextuality witness, this property should satisfy, like this property, like the graph should have this property. Well, and now we consider a simpler communication task where x basically could be one of the vertices and y also could be one of the vertices, and we want to guess whether x is equals to y or not. So if x is equals to y, the function is 0, and if y belongs to the neighborhood of x, the function is 1. So this is basically distinguishing problem. So this is also known as the equality problem in the language of communication complexity and has many applications. Yeah. So, and if we consider this figure of merit, like guessing this particular function, then we can show that the quantum communication complexity is basically D for this task, and the classical communication complexity is the chromatic number. And by definition, the chromatic number is greater than D, so we have some advantage according, like in terms of the communication complexity. Now, to show that the advantage is unbounded, we have to consider a particular product of graph, that is inclusive graph products. And so it is like this. So if G has n number of vertices, then G times G has n square number of vertices, and we can like represent those vertices by this tuple, where I and J basically are vertices from first G and second G, and they are connected by edge if one of these two are connected by edge in the original graph. Now we can also define the same communication complexity task, this equality problem, on this product of two graphs. And similarly, we can multiply many graphs and consider the equality problems. And we have shown that the ratio of this communication complexity for classical and quantum communication is lower bounded by some constant into the ratio of the chromatic number and the dimension to the power m. So if m increases, as n increases, this value could be arbitrarily large. So that's why we have an unbounded advantage. So to showcase, so here basically we have considered like some contextuality proof, and we have calculated the ratio of the complexities such that we need like 200 qubits to solve this equality problem. So where the quantum communication complexity is basically around 200 qubits, and you can see this value is quite large, the ratio of these two complexity. Well, so yeah, so let me also talk a few things about the QKD protocol. So we can also use this communication task that I told you in the beginning to use to generate quantum key, and in a semi-device independent scenario, where basically we don't assume anything about the measurement device, anything about the internal working of the measurement device. We only assume that the preparation device prepares a d-dimensional quantum system, like d-dimensional system, and also these inputs are uncorrelated with the like the classical randomness that these two devices may share. Okay. And so the protocol is as follows. So Alice and Bob basically randomly choose this variables x and y and perform this experiment many times. And after that, Alice randomly chooses some runs and announces her input x, so that Bob can verify the figure of merit is greater than the classical value. That's why he knows that it must be a quantum system under this assumption. And then Bob announces his input y for the remaining runs. And so Alice now knows x and y. So he basically notes down the function f x y as the shared key. Right? And if x, like this input y is not in the context, then as Alice basically announced that run of transmission is unsuccessful. Now, to prove the security is difficult for arbitrary eavesdropping, but we have shown that if the contextuality witness satisfies monogamy relation, then it is secure against individual eavesdropping with some restrictions. So yeah, and so thing is that if you want to know the details of this work, you have to wait, because we haven't put it in the archive yet. So yeah, so that's all I wanted to say.
Thank you, Devashi, for your nice talk and also maintaining the time. So now it's open for question.
Yeah, Devashi, can I ask a question?
Yes, yes, sure.
Yeah, let's say I see in this way. So by 1 qubit, if let's say Alice Bob share arbitrary amount of entanglement. Now by 1 qubit, I can say sending 1 qubit, I can send 2 qubit communication.
Yes.
This is the dense coding.
Mhm.
If I send 2 qubit, then I can actually send 4 qubit.
Yes.
If I send 3 qubit, then 8.
Yeah.
So will you call this advantage also unbounded?
No. So here, basically we are considering that they do, like Alice and Bob, they do not share any quantum entanglement.
No, that I understand. That is the scenario.
Yeah.
But because what I am trying to say, this unboundedness is. But what I am trying to say, this in dense coding, I am taking different basic tasks, tensoring those tasks. Here you take this basic graph and then tensoring. That's what I am trying to say.
So here actually, no, so I wouldn't say that is unbounded. I mean, that is, so I wouldn't say that is even a proper advantage, even in dense coding, because a priori we need to share 1 bit of entanglement. Okay. And
No. Devashi, what my point is, this dense coding scenario is completely different. I am just trying to understand unboundedness, because generally unbounded, like if we look into Hardy's protocol, there he trying to show that by a qubit you can perform a task that requires infinite qubit actually. That is means that is very powerful. Of course, the task is not that much practically applicable task. Here from where you are getting that, I understand, because you identify the basic graph. Now you tensoring these things, so that this ratio now it goes with m with the power of m. This is happening, no? Here.
Yeah. Yes.
Okay.
So,
okay. We can further continue discussion later. Let's say. Yeah.
So yeah, so the thing is, if you in a operational, if you are considering operational task, whether where there are classical inputs and outputs,
sure.
Then a d-dimensional quantum system, like
Yes.
there are some bounds that any statistics of a d-dimensional quantum system that can be reproduced by like this amount of like this dimension of classical system. So, so if you are,
so then you saying that there may not be any such means unbounded advantage is possible.
yes.
To get the unbounded advantage, you require this tensoring of this basic task. Okay. Yeah. Thank you, Devashi.
Any more questions?
So can I just a small comment? Yeah, this is Shrikant here. Just wanted to. Yeah, so thank you very much, Debashish, and also it was very interesting to hear Manik's, insightful comment. So just continuing Manik's question, I wanted to ask you, I guess in dense coding, what happens is, as Manik was saying, so you have a kind of an advantage that comes in. So if Alice and Bob are sharing a D into D entanglement, right? So I can send basically D square, bits with a D-dimensional system, right? So 2 log D bits of classical information can be transmitted, but I suppose in your case you have the m sitting on the exponent, right? So I guess probably is that part of your motivation for saying that it's unbounded? I mean, that sort of a terminology has come in because your m is, it's not like m square or something, but instead it's this whatever chromatic index divided by d power m. So I was just thinking that probably this is a point you might be of some interest.
Yes. So as we take more number of products, then the ratio can be arbitrarily
grows exponentially in the number of copies that you're tensoring producting, right?
So it also says that, like, it also suggests that there exists some communication complexity task that can only be achieved in quantum communication.
Correct. Yeah.
So at some point, this would be like, this would blow up and it should not be possible even like in classical communication to achieve that task.
Okay, Devashish, your discussion can be continued in some other way, but we have to move. We have to move to our next speaker, Mir Alimuddin from Aizar Trivandrum. He is going to speak on local quantum measurement demands, type-sensitive information principle for global correlation. Okay, Mir Alimuddin, you share your screen and start.
Yes, sir. So is it visible?
Yeah, it is. Yeah, so move.
So am I audible?
Yeah, you
but
are.
My screen is moving.
Yeah.
Okay. Thank you, sir, for introducing me, and thank you all the organizers for organizing such a wonderful event, and allow me to discuss my work, our work actually. So I did my PhD from ISI Kolkata, and last year I have submitted my thesis, and currently I have joined at Isaac TBM as a research associate with Dr. Manik Boni. So today I will discuss our recent work, and these 4 people are the collaborator of this work, and they are first year PhD student under Dr. Manik Boni. So since actually I will talk about the quantum correlations, I need to, so actually this is my, okay, it is not completely visible. So this is my plan of talk. Firstly, I will talk about the quantum correlation. So I need to define the scenario first. So actually, I will show that I will discuss some previous result of local quantum and no signaling implications with quantum correlations, and that results was discussed in the standard Bell scenario, that popular standard Bell scenario. And actually, this implication is not. I will discuss this implication is not quite true in little different scenario, because in the most general scenario. So we'll discuss the semi-quantum scenario. In that scenario, we'll show that this implication is not quite true. And the major role, the non-orthogonal inputs will play the major role of this case. And then I will say what can be the I'll say what can we include as a principle to imply this two relation. And then I will conclude our work with some remarks and some open problems. So firstly, I will introduce the standard Bell scenario. In the standard Bell scenario, actually Alice and Bob. In the standard Bell scenario, actually Alice and Bob, they are actually sitting in the spatially separated lab and sharing with maybe some classical, maybe some quantum, or maybe some beyond quantum states. There is some collaborative referee who is giving some classical input. This is very important. The referee in the standard Bell scenario, the referee sending some classical inputs to Alice and Bob both, and according to that classical inputs, Alice and Bob perform some local measurements and giving some classical outcome A and B, and that yields a correlation matrix. So using that so we can always generate some function using those correlations matrix. That functions may help us to distinguish between classical theory, quantum theory, and some beyond quantum theory. Actually, Bell have started that things. Actually, he have shown that if the physical theory has a local and realistic description, then this value for the separable type of states or for classical states, or the theory has a local and deterministic realistic description, cannot go 0.75. But actually, our quantum states show quantum states violate this bound and show the non-locality. But this bound is also limited. It is 0.85. Seidelsons have shown that for arbitrary bipartite systems, arbitrary dimensional quantum systems, it can't go beyond 0.85. But if you take a correlation which is follow the no signaling constraint, we can reach actually the optimal value at 1. So the question is why quantum is not more non-local, or rather we can say that what extra principles do we need to bound this value? I mean, or what extra principles do we need to exclude those points to exclude those unphysical correlations. Here, unphysical means the correlations which cannot be produced by quantum. So we want our task, if we rely on quantum mechanics, then our task is to exclude the unphysical correlations or the correlations which cannot be produced by quantum mechanics. So in this case, several research have already done and some principles approach has given. And another way, in another extreme, some mathematical postulates. Our quantum mechanics is that kind of things where we have taken few mathematical postulates and derived our quantum mechanics, which is very much compatible with no signaling principles. But we can go in the middle also. I mean, suppose we will not take that many mathematical postulates. We'll reduce our mathematical postulates. I mean, we'll exclude some of the mathematical postulates from quantum mechanics, and we may include some principles to derive to single out those unphysical correlations. So to discuss that things, firstly I have to introduce Gleason's and Boo's contributions. This Gleason's and Boo's contribution is for the locally quantum systems. So what they have taken, they have considered the systems, they have considered the observables or the measurements are the nothing but the positive operator acting on the finite dimensional Hilbert space HA, and their generic measurements are the elements of the positive operator which is satisfying these conditions. So what they have done, so they define a probability measure on those positive operator, and that probability measure, if that probability measure satisfies these following three conditions, 1, 2, and 3, these are the nothing but the Gleason's conditions. They have shown that it is actually uniquely defined with the trace rule or the bonds rule. So that means if you consider your measurement as a positive operator, local, obviously I'm talking about the locally quantum system. So here is no comment about composite systems right now. So if your local systems is defined by your local observables are nothing but the positive operator, then your systems are nothing but the density operator. So this is the one postulate we'll take, and another principle we'll take. I'm coming to that point, but okay, now move to the composite system. So you see, we'll take the locally quantum. So local observables are okay with us. Now, we will not consider any global positive operator, I mean, just like the entangled positive operator, because those are, so we'll only consider the separable kind of positive operator. In this theory, we'll consider only the separable positive operator, no entangled positive operator. And if we define some measure on those separable positive operator, just same and put the condition or put the Gleason's conditions on the all local systems. And with along, if we include the no signaling principles, then we'll come up to the solution like W. As you see that actually our observable space has been squeezed to the separable. We are excluding those entangled observables. So it actually giving the state space little larger. And so this is the state space of this new theory, local quantum theory, and this is the state space of quantum. So some states are added. These are the this will call the beyond quantum states or POPT. Why it is POPT? Because it will give you positive over the all separable type of things. And you see for every so here is the very good implication that if you take this state, this W, which is the beyond quantum, then there always exists some entangled states which can give you the negative value. So that's why for that entangled state, this is acting as a witness operator. So what is the conclusion here? If you consider the local quantum measurements and no signaling, so this is the mathematical postulates and this is the principle, our state space is nothing but the POPT, which is the larger than quantum. Okay. Now come to the now come to the correlation scenario, whether this POPT can give you some beyond quantum correlations. Okay, so I'm coming to that point. Okay, so if you consider this POPT and do some local measurements, whatever the correlations we'll get, we'll call it Gleason's correlations. Obviously, this set inclusion relations would follow because the state space of POPT or witness, the state space of POPT is larger. So the Gleason's correlations have, I mean, this state has that much potential. This state may have potential to give you some beyond quantum correlations. But actually Barnum have shown that, Barnum and their collaborators have shown that whatever the correlations you get from a POPT states or from a witness, the same correlations always can be achievable by some quantum states and some other choice of local measurements. So from there, Barnum has concluded that, okay, local quantum plus no signaling implies quantum correlations for bipartite systems. But we'll show that these conclusions is very much restrictive. I mean, they have not considered the general scenario. I am coming to that point. I will take, in our work, we'll take local quantum and no signaling, and still we can give some correlations for each and every POPT. We can give some correlations which is beyond quantum. So that I'll show that how Barnum have taken these things as a very limited scenario. Actually, in the Barnum made this conclusion also. I mean, made this comment that our results shows that if any experiments would give non-local correlations beyond quantum mechanics, quantum theory would be invalidate even locally. So this conclusion is not quite true. I'll show that things. Okay, in the line of Barnum's work, if we consider a one parameter class of beyond quantum states, actually this state would be beyond quantum. Okay, what is this? This is the partial transpose of 5 plus for a particular choice of basis. So this would be a POPT. This would be a witness. So if you take these combinations with this witness and identify 4. It would be a beyond quantum states, or it would be a witness for the range of 1/3 to 1. You can it will act as a witness operator for psi minus for this range. Actually, we have shown that, okay, Barnum have shown that, okay, this POPT would give you some non-local correlations, but actually we are showing that these POPTs, this kind of POPTs for the range of this value 1/3 to half, if the range of P range 1/3 to half, actually we are providing a LHV model under projective measurements. So that means, and LHV model for P less than 5/12, LHV model under POV measurements. So that means actually for this range, these states in the standard Bell scenario don't have the non-locality power. Okay, but still I will show that this state this state have that potential to create some beyond quantum correlations. I will come into that point. Just let me give some time. So okay, so after this Barnum work, actually the Assins and their collaborators have tried to see the status of Barnum's theorem in the multipartite scenario, and then there they have established that if the witness is in this form, where these lambdas are the positive operator and over the quantum states, then the status is same. They will not produce any beyond quantum correlations. But then immediately they have shown that if the state is in this form, or actually they have constructed an explicit example where they took a witness operator in this form, which is producing a beyond quantum correlations. They have shown this case for the tripartite scenario. Because in the bipartite scenario, this is always the valid. I mean, quantum correlations is equivalent with the Gleason's correlations. So then they ask a question, why the Barnum theorem does not hold in the multipartite scenario? And then they made these conclusions. They made these conclusions because they tried to figure out what are the extra conditions is necessary, extra principle is necessary to single out this type of Gleason's correlations. Okay, that was the open problem, and we have answered that questions also. So now I'm coming to our scenario. Our scenario, actually this is the most general scenario and introduced by the Bush semi-quantum scenario, where in the again, if the Alice and share some states, some preparation, and referee is, instead of some classical input, referee is sending them some quantum input. Generally this quantum input can be non-orthogonal. And then Alice and Bob, locally, they are performing some measurement on the joint system, what they are received and what they are shared in the joint system, and producing some classical output and yields these correlations. And again, one can define another functions like this linear function and try to distinguish between classical theory, quantum theory, beyond quantum theory based on some value. We have done these things actually. We have shown that every beyond quantum, if Alice and Bob share some beyond quantum states, whatever the states, that state may be in the standard Bell scenario, that state may have LHB model, cannot produce any non-local correlations, but that states also can give you some correlations which is beyond quantum. So okay, so what we have done, so actually for every beyond quantum state, we so the existence of a game which is giving you negative value, whereas if they shared some entangled states, whatever the entangled state may be, so this game obviously we have, again, for this game we have to choose some local measurements. That local measurement is very important. I'll come to that point also. So, but whatever the state they shared between, I mean, whatever the state they shared, and whatever the measurement, whatever the quantum state they shared, and whatever the measurement they choose locally, they can't get any negative value. So since I'm talking about the whatever the measurement, so this is a device independent scenario. So actually the power comes because of the Hahn-Banach separation theorem, because each and every beyond quantum state can be distinguished with some hyperplane separation theorem. And actually that is, you can see it is in this way. Suppose this is a quantum state, and for this state, this is the witness. So this would give you negative. In the other way around, I can use this chi-AB is the witness for this POPT state, or for this POPT states. So what we have done, for a particular choice of measurement, when they will share some WAB, for a particular choice of measurement, will show that actually this value of this game becomes proportional to this quantity, and that gives you the power of this semi-quantum game. And actually, since this is a quantum states and this is a quantum state, it would always give you greater than 0, mean positive value. So it would remain positive whatever the measurement you choose. So so for this WAB, for any beyond quantum state WAB, we'll choose this kind of measurements. So they will perform a joint measurement on the received and the shared systems, and this is the 5+ measurement. And they would take the click of the 5+ measurements only in the both side, and returning that correlation to the referee, and they will calculate this function, and that functions would be equal with this quantity. So what is the conclusions? I mean, what is the things Barnum have taken these conclusions for the standard Bell scenario? So he have not taken the most general scenario. So he has taken local quantum plus no signaling is equal, it implies quantum mechanics, quantum correlations and relations correlation. So that is not true. Rather, in the just like the states, the difference between just like the state space difference, here also in the correlation space also POPT has a rich correlations. I mean, it would produce some beyond quantum correlations. But the most important point, the non-orthogonal inputs are very much necessary in our scenario, because you see, if referee send them some orthogonal input, Alice and Bob can perform some measurements and distinguish what they say, what referee tried to say. So this would immediately collapse to the standard Bell scenario, like classical input scenario. So the non-orthogonal input is very much necessary. And another thing is that the local quantum is still valid, because in this scenario, Alice is performing some local measurements on their respective system. They are not performing any global type of measurements. So we need to consider the quantum input and then try to perform the measurements. That would be the most general scenario. We need to actually investigate this correlation. We need to investigate the power of this POPT. Actually, whenever you are taking classical input, the power of these beyond quantum states is not coming into your correlations. It is coming only at the point when the inputs are non-orthogonal. Okay. So we have actually shown that things. And continuing that things, we have shown very general results. Mean for any arbitrary dimension and any multipartite systems, for any beyond quantum states, there exists this kind of game which can give you some non-quantum, some unphysical correlations or beyond quantum correlations. Even the state is in this form that Gleasons have shown, that Assins have shown that this type of states has an equivalent status in the correlation space, but this states also would give some beyond quantum correlations. So this is the conclusions of my talk, that every beyond quantum POPT states yield some unphysical correlations, and we have answered the open problem raised by the Assin, how it was that. So what we have shown that local quantum and no signaling is not sufficient to single out quantum correlations. So we need some more principles. What would be the principles? What would be the status of those principles? Obviously, the new principle must be quantum sensitive. Otherwise, if it is a classical input, then we'll come to the we can't distinguish the POPT states from the quantum states in the view of correlations or in the view of space-like correlations. So, but yeah, so that's the point. You see, the semi-quantum game. So now the ingredients, what ingredients we can take? It should be quantum sensitive, and the semi-quantum game, those are the potential candidate to make this sufficiency. Okay. So we have answered this Assin's Assin's point or Assin's open questions. And another important thing is that you see that for POPT and quantum, the structure, let's try to see the structure. In the quantum, the state space and the measurement space are self-dual. So in this measurement space, there not only exists some observable which is separable, there exists some entangled observable also. But in the POPT, there exists only separable kind of observables. So you see, in between this quantum and POPT, that means, okay, in the POPT theory, if you, so in the POPT theory, there is only the separable type of observable. If we include one entangled observable in that and construct a new theory, in that new theory, some witness would be discarded, but there might exist, we can construct in that, or we can construct infinitely many theory in between quantum and POPT. But all those theory cannot be excluded. Cannot be yes, sir. Cannot be excluded by the Barnum scenario. But here, using our scenario, we can exclude that things, and we can. The one open problem is that Torre et al. Have shown that when the local systems are identical qubits, then any theory admitting at least one continuous reversible interactions must be identical to quantum theory. These conclusions or these implications also made in the standard Bell scenario, like classical input and classical output scenario. Again, we need to investigate these implications in the semi-quantum scenario, because that is the most general scenario, and we need to try to investigate what extra principle is necessary to make these implications. So thank you all. Yeah.
Thank you, Mir. We can take at most one question if there is any question.
Hi, can I ask some question?
Yeah.
Yeah. So Mir, thank you for your presentation. But one question comes to my mind, that for your settings, that referee has to send the separable quantum states to Alice and Bob, right? The
yes.
psi S A0, psi phi T Bob B0, right?
Yes.
But is your device actually acts if referee sends entangled state?
No, it would not act, because it would not act because what will, so suppose there is extra entangled state is lie there, then what they can do, so you see here we can do
means I'm asking okay.
So you are saying whether this would be valid things if they shared some entangled states, or referee sending them some entangled state.
Yeah, referee
I'm
sending
trying
them
to
some
say you some things. So suppose this referee sending some entangled state. Using that entangled state, they can teleport this WAV to here at Bob's lab or Alice's lab. Okay, and
yeah, but that needs communication.
Yeah, that's true. That needs communications. Yes.
Yeah, but the question is.
Thomas, you can continue the discussion later, but at least I can tell for this picture that he wanted to discard some POPT states which could not be discarded by earlier work. So by this they could do this. So it works. So using entangled state by the referee, what will happen, that can be checked, but that is not very interesting because what was the purpose that has been solved? No. So okay, you can discuss this thing later, but I have to start the next talk by Tathagata Gupta. He is a research scholar at ISI. He will be talking on genuine activation of a strong quantum non-locality. Yeah, Tathagata.
Unmute your mic, Tathagata.
Oh, sorry. Hello, am I audible now? Yeah, you are audible. Okay. I thank the
You are audible, yeah. You share your screen.
Yeah. I thank the organizers for giving me the opportunity to present my work. My screen is visible.
You slightly increase your volume.
Hello?
Yeah, you continue.
Yeah, thank you. Okay, I thank the organizers for giving me this opportunity to speak in this wonderful platform. So I will talk about genuine activation of strong quantum non-locality. So this is a work that I did with many people, and Shubhendu, Anando, Shudhavadi, Rameshda from ISI, Adra, who is a student at ISI Thiruvananthapuram, Kamalda, who is a postdoc at University of Hong Kong, and Amida, who is at SN Bose National Center for Basic Sciences. And this talk is based on these two papers, which are on Icqif, and they are yet to be communicated. Okay, so let me start by the familiar notion of Bell non-locality. We all know that Bell non-locality captures the non-locality manifested in correlations between separated events, specialized separated events. And this was in 1964. And in 1999, Bennett and others introduced a new kind of non-locality, which where the scenario they dealt with was some locally preparable states, but which cannot be distinguished locally. You need to come, all need to come together in a lab to distinguish them, which is extremely non-classical feature. So now the question that we want to ask here is that, can this non-locality be activated? That means that we start with some distinguishable states, locally distinguishable states, and we perform some local operations and maybe possibly some classical communication. We will qualify this term LOCC later. But this is the most general scenario, most general local operations and classical communication. Can we, through these operations, convert the locally distinguishable states to locally indistinguishable states? So this was in
fact. Voice is not clear.
Hello?
Your voice is not clear.
Is it clear now?
Now you're okay. Okay.
Hello?
Continue.
So is my voice clear now?
Okay, you continue.
Okay. So so we asked here the question that can this locality or non-locality be activated? That is, starting from some locally distinguishable states, and by LOCC can we convert those states to some locally indistinguishable states? So this was in fact answered yes, first addressed in this paper, Genuine Activation of Non-Locality, by Shomshuto Bandyopadhyay and Sharanath Haldar, which came out last year. So after them, we took inspiration from that paper and we presented a broad class, broad examples of such non-locality activation, and that those classes and examples I am going to present here. Okay, so first we need to qualify the term LOCC here. Any LOCC, we will not consider any arbitrary LOCC, because that won't be very interesting. I can, of course, the local agents can always measure in some arbitrary manner and make the states non-orthogonal. Starting from an orthogonal state, they can perform some arbitrary local measurements and convert them to non-orthogonal states, and thus making them indistinguishable. But that won't be very interesting. So what we want here, we want only those measurements which local measurements which preserve the orthogonality of the states. Number one. Number two, we need to worry about local redundancy. We do not want such trivial scenario where only discarding one subsystem from one of the agents, possibly one or more of the agents, can make the set of states indistinguishable. For example, take this state. So with I've taken here 4 Bell states, and with each Bell state I have so consider a state, say set of states where the each Bell state is tagged by 00011011, the computational locally discriminable computational basis of 2 qubits. So if I tag the Bell states with these basis states, it is always distinguishable, because I will only just perform, the local agents will only perform on the prime system and will conclude about the AB system, which Bell state they are given. If they discard their classical tag, the AB system becomes indistinguishable. This is not an interesting case. We do not want such trivial activation of non-locality. We want the agents to really perform some local measurements and then activate the non-locality. All right. So how can we activate, suppose in Bell states, how can we activate such a non-locality? We start from these states. Here the states are they are distributed between 2 parties, Alice and Bob as usual. But one party's system is a qubit, another party's system is a composition of 2 qubits. So the second party's qubit, the second party system is actually 0, 1. The basis states are 0, 1, 2, and 3, since these states in the Hilbert space C4. So starting from these states, and these are okay. So what we need to check? We need to check that they are locally distinguishable, because we want to activate non-locality. So they are locally distinguishable, and second, they are free from local redundancy. These are quite straightforward tasks that one can perform. I'm not going into that, because that is a very tedious task and will take a lot of time to explain actually. So they are free from local redundancy and they are locally distinguishable. So how can we activate non-locality from this state? Let Bob make the positive measurement in this basis, and from one can show that if P1 or P2 clicks, the states they end up with are these. Now these states are maximally entangled Bell states in C2 tensor C2. They are obviously locally indistinguishable. Also, they are not locally markable. Local markability was discussed by Dr. Somshankar Bhattacharya on Saturday, and this is a reference that one can see about local markability. Also, instead of these 4 states, one can take 3 of them, any 3 of them, and one can perform the same measurements to get another set that will consist of 3 Bell states now, and which is also locally indistinguishable and unmarkable under one-way LOCC. All right. So apart from Bell states, what can we do? In this reference, the authors gave a local quantum state marking. The authors gave an example of a set of states which are locally indistinguishable but locally markable. We can have such states where the activation of non-locality leads to those states which are locally indistinguishable yet locally markable. So starting from so these psi1, psi2, psi3, psi4 are these these psi1, psi2, psi3, psi4, and each is tagged with some base state, phi plus here, and for all the rest of the cases, phi minus. So if a Bob again performs the same measurement, then they will end up with the 4 base states tagged by these phi plus, phi minus, phi minus, phi minus. Now these states, they are locally indistinguishable, but yet they are locally markable. All right. So what about multipartite scenarios? What about scenarios? The simplest scenario that we can think of is going to 3 parties. We can think of the GZ state, the GZ basis actually. So that is also possible. So we start from this set of states. Alice's system is a C4 system, resides in the Hilbert space C4, and Bob and Charlie's each of Bob and Charlie hold 1 qubit. So now let Alice perform the projective measurement, this one, and after applying an appropriate unitary, they can convert these set of states. So there are 8 states, each with a plus minus sign. So these 8 states to this set will be converted to the standard GXZ basis with appropriate. Also, see all these states. Whenever we present an example, we have to make sure that all are locally distinguishable and free from local redundancy. That has been checked. I mean, I'm not repeating that for sake of brevity, but these are all locally distinguishable and free from local redundancy. So with appropriate operations, local operations, they can convert this to the GXZ basis, which are locally reducible and indistinguishable. But we all know the GXZ basis, if 2 parties come together, then they remain, although they remain locally indistinguishable, but nevertheless they become locally reducible. Okay, so what about product states? Can we do something about the product states? Yes, we can. So take this bipartite product states, where Alice is holding a Q treat and Bob is holding 2 Q treats, say, and they can also activate non-locality from these states by performing these measurements, and they will end up with the UPB in C3 tensor C3 with the unstable product basis in C3 tensor C3, and we all know that this is locally indistinguishable. This can apart from the bipartite UPB, we also know there is a tripartite UPB, the shifts UPB, that can also be activated. Suppose Alice, Bob, and Charlie, say Charlie holds a C4 system, and this can easily be converted to the shifts UPB of C2 tensor C2 if Charlie performs this projective measurement. Now, this is very interesting, actually more interesting than the entangles case, this product case, because they are getting the same power with product states actually. But in this shift CUPB case, Charlie alone can activate the non-locality. See here, that Charlie's system is C4, so only he needs to make the main measurement to activate the non-locality. But the other 2 parties can still come together and identify the state. So the next interesting question that can be asked, that can we have a scenario where the activation power is still concentrated to 1 party, but the other parties cannot identify the states by themselves? That is, it is indistinguishable in every bipartition, yes. So actually we can have such a situation, and actually more than that, we can have a set of state which is not only indistinguishable but also locally irreducible in every bipartition. For that, we need to consider, but see, any product states in 2 cross n system is is distinguishable in bipartition. So we cannot have that situation in for that situation to occur, we need to go to three C3 scenarios. So here we have taken 3 parties, and 2 of them share Q-trig, and 1 of them has a system which resides in the C6 silver space. And these are a set of 27 orthogonal product states, except for state number 5, 10, and 15. All have a partner, so it's 12 into 2, 24 plus these 327 product states. So also they are free from local redundancy, they are locally distinguishable, and we can activate a very interesting kind of non-locality from them if we let Charlie perform this projective channel. What kind of non-locality can we activate? Depending on Charlie's outcome, the states will be converted to this set, which is not only locally indistinguishable, but they are also locally irreducible, which means that even if, so say Charlie is having authority that Bob and Alice should not be able to identify the state when they come together. Not only that, Alice and Bob, if they come together after Charlie has activated this non-locality, Bob and Alice will not be able to exclude even one state from this set of states, even if they come together, let alone distinction. So these are the examples we came up with and the scenarios we came up with. Also, there remain some questions, and I want to end my talk with mentioning those questions. So here 3 notions of non-classicality are at play: indistinguishability, unmarkability, and irreducibility. So can we give a comparative? Can we give a more concrete study about the interplay and the interdependencies of these 3 notions of non-classicality? For example, distinguishability. If we can distinguish a set of states, then we can always mark and always reduce them, right? So unmarkability and irreducibility will imply indistinguishability. But what about the relationship between markability and irreducibility? And also, what about their activation? Which one is more strong activation? These are the questions one can think about. Also, one can think about the activation of non-maximally entangled states, which in turn will lead us to indistinguishability with 2 copies. I mean, in the Bennett's paper in 1999, they conjectured that any set of orthogonal states can be distinguished given 2 copies. But in this reference, the authors found a set of states, non-maximally entangled states, which require at least 3 copies to distinguish. So can we have a situation where the non-locality activation leads us to that set of states which require at least 3 copies and not 2 copies? They are indistinguishable with 2 copies. That is also one possible question. And another possibility is the obvious extension of the non-locality activation. We have here considered non-locality activation under LOCC or under OPLMs, orthogonality preserving local measurements. So what about non-locality activation under more general SAFE or positivity under partial transpose, all those operations that preserve positivity under partial transpose, those kind of operations. So these are the questions one can think about, and here I would like to end my talk. So thank you. Any questions?
Thank you, Tathagato. We can take one short question, I think, if there is any question. Is there any question or comment? So maybe Tathagato's voice was not that clear. So maybe there is no question. Okay, if there is no question, let us thank the speakers and thanks all the speakers in this session. And so we conclude this session, and now it is lunch break, and we'll start again at 2 p.m. I mean, 14:00. Okay, thanks to all participants.
Is always a real symmetric matrix, but RLD Fisher information matrix sometimes has a complex component. This one has Elmincher matrix. Using that complex part, sometimes we obtain better bound by using the RLD Fisher information matrix. So in this sense, this one is somehow more useful. But in this talk, mainly we focus on the one parameter situation. So in this sense, maybe people consider that it is enough to discuss SLD. However, in the later part, RLD takes a very important role. So in this sense, RLD Fisher information is also very important. And also sometimes we consider, this is a mistake, not a Heisenberg scaling. This is a conventional scaling. So in the case of state estimation, we often consider limiting distribution. This is not Heisenberg scaling. This is conventional scaling. This is conventional. So please replace Heisenberg by conventional one. So in the conventional scaling, we consider 1 over square root n or scaling. So in this way, we consider limiting distribution because the error behave as this order, 1 over root n order. So then this kind of distribution converts to the one fixed distribution. In the classical case, usually this distribution converts to the Gaussian distribution. We focus on this one. And if this distribution does not depend on C, In this case, we say that estimates are satisfy asymptotic covariance. So this is asymptotic covariance. So that kind of a limiting distribution does not depend on C. So then we have asymptotic covariance, and under this condition, we have this Craméral inequality for the limiting distribution version. This is another version of limiting distribution, another version of Craméral inequality. So this is the second part. Now we move to the Craméral bound for the channel estimation. So in the channel estimation, we need to choose input state. So we can choose a good input state. Then we have an output state. So that output state reflects the information about the channel parameter. So then estimating this state, you can estimate through parameter theta to characterize the channel. So this is our setting. So in this situation, our estimator has two components. One is an input state. This is one choice. And another choice is choosing the measurement, P of M. So then our estimator can be written as a pair of input state and P of M. But sometimes we can consider much more efficient method. For example, we can consider this extension. Using this extension, as you know, we can make a choice representation. So this is a choice matrix of the channel if we prepare a maximum entangled state. But if max input is not different from the maximum entangled state, so then output is not necessarily a choice representation. However, this kind of output state sometimes much better information than choice matrix. So in this sense, we need to optimize input state on the this composite system. So we have two choice input state on the composite system and output measurement on the composite system. So then also we have an NIID extension in this way. Similarly, we can define unbiased condition and locally unbiased condition. But in this case, we have a freedom of choice of input state. So in this sense, we define it's kind of feature information. First one is SLD, but in the case of SLD, we need to choose input state. So for example, this is a state family. If we fix one input state, then we have a state family. Using this state family, we can define SLD and RLD feature information. These feature information described by this one and this one, JS lambda rho and JR lambda rho in this way. And we can optimize feature information by choosing the good input state. So then we have two kind of optimum value, SLD, optimum SLD and optimum SLD. Trivially, this maximum RLD is larger than maximum SLD. So in this sense, people consider that it is enough to consider this quantity. However, the story is not so simple. In the case of channel estimation, sometimes this one use a very important role to discuss the channel estimation. So this is a locally unbiased condition. As you know, locally unbiased condition, we have this inequality. So in this sense, this one gives a bound for the estimation, mean square error. This one gives a lower bound of the mean square error. However, we need to consider n-copy situation. In the n-copy situation, sometimes there is a possibility to get a Heisenberg scaling. So in the case of Heisenberg scaling, this one behaves 1 over square n. But in the usual case, this one behaves 1 over n. To cover all situations, we put the scaling order parameter alpha. So depending on alpha, we consider this inequality. So we focus on this limitation. This limitation characterizes the performance, asymptotic performance. and we need to carefully choose alpha depending on the situation. Now okay. Now we consider this quantity. So this one is optimum SLD quantity. So we consider optimum SLD Fisher information, and we take this quantity over alpha, because alpha sometimes 1 and sometimes 2. So this is order parameter. So then we define that coefficient. But here we want to put tilde because later I will explain that that quantity does not clarify express the true bound. This is only the theoretical or mathematical meaning. So I will explain why we have a tilde for this definition. I will explain this reason later. So we also consider RLD Fisher information. Sometimes we can define RLD Fisher information in that previous way, but that maximum of RLD can be calculated by using in this way. So firstly, we define rho lambda by using this way. This is maximum entangled state. So you don't need to optimize that state. And also, we take its derivative in this way. And you take this quantity, and you take partial trace only on system K. K is, I cannot remember K, sorry. K is the, maybe, output system. Sorry, K is output system. So then this final state is K tensor R. R is a reference system. So in this sense, R is the same dimension as input system. So we have this density matrix on the composite system between K and R. So we have a two system. However, to consider this quantity, we only take partial trace on the system K. So then this quantity is a matrix on the R reference system. The dimension is the same as input system. So then we take operator norm on the matrix on the R reference system. So then we have some real number. This number is equal to the maximum RLD Fisher information. This is my order result. So in this way, we can calculate this quantity. But to obtain this inequality, we need to do this condition. If this condition does not hold, the maximum RLD becomes infinity. So this condition is very important. If the square of that derivative, the range of square of derivative is included in the range of this density matrix, so in that case, this quantity can be calculated. This is a very important condition. Anyway, you can calculate the maximum Fisher information of RLD. So in this way, so then we have another result. Under the same condition, we have this additivity condition, additivity relation. This means that this RLD increase only linear way. And also, I already mentioned that this RLD is upper bounded by SLD. So in this sense, this is a mistake. This tensor N. So maximum Fisher information tensor N increase only with linear order. So in this way, it is quite difficult to calculate the maximum SLD. This is almost impossible. However, you can calculate maximum RLD by using the N times one copy situation. So in this sense, if this condition hold, you can trivially find that this one increase only linear order. So in this sense, we can easily find that this model is has only this order. This means that this model does not have Heisenberg scaling. So this one has only user scaling. Of course, if this condition does not hold, there is a possibility that this one increases the more larger scaling, Heisenberg scaling. For example, this channel is given as in this way, in this unitary model. In that case, maximum Fisher information can be returned in this way. So in that case, alpha should be chosen to 2, and this quantity equal to 1 over difference of eigenvalues, square of eigenvalue. So we have this result for this case. And also recently, there is a very nice significant contribution by Mark Wilde and Kataria. Mark Wilde is maybe later speaker of today's session. So they extend my old result to the adaptive situation. My problem setting, we have a parallel application. So we have a parallel application, but they consider slightly different setting. They allow this kind of adaptive situation. Even in this adaptive situation, we have a same upper bound. In this sense, RL efficient information very useful. Once we have a finite value of RL efficient information, we found that there is no possibility to the Heisenberg scaling. However, in that situation, RL efficient information is become the infinity. So in that case, we cannot have the same discussion. Then there is a possibility for the Heisenberg scaling. So in this sense, it is very important to check the behavior of maximum RLD. Once we can find a finite maximum RLD, we guarantee that there is no possibility of Heisenberg scaling. Now we consider two kind of asymmetric bound. So there is a state estimate, a channel estimation. There is some problem. Usually, it is we need to consider low minimax condition. So usually, in order to estimate some parameter, that estimator should be robust. Robust means that that performance or error is not so bad, even if the true parameter changes slightly. So in this sense, we need to consider minimax criteria. Minimax criteria means that we need to consider worst error in the given area, in the given choice, given range. So, but it is quite difficult to make a global minimax. So in this talk, we consider local minimax. Local minimax is the following. So we have this neighborhood. I'm going. Do you use the Douglas fluctuation? I cannot understand this question. Do you use Douglas fluctuation of range of content in the range of operator? Sorry, I cannot. I don't know the definition of Douglas factorization. So then I cannot answer this question. Sorry. Anyway, so we consider this range, and we consider worst case and range. But in this situation, epsilon is arbitrarily small, but it should be fixed number. Does not depend on n. So in that case, firstly we take limitation n go to infinity. Later you take epsilon go to 0. So this kind of order of limitation is very, very important. If you take epsilon go to 0 first, in that case, the problem setting is very trivial. So you need to keep this order. So then we define local minimax quantity. So we consider this minimum area under this condition. So then we obtain this inequality. So always this minimax error is greater than that's the previous one. So this is the minimum under the SLD, inverse of SLD. So we have this inequality.
Yeah, Professor Hayashi, there is There is a small question.
Yes.
Yeah.
I will check this one, but Douglas factorization, I cannot understand the definition of Douglas factorization. So I cannot answer. Could you explain the definition of Douglas factorization?
Yeah, please go on.
Otherwise, I cannot answer. What is the definition of Douglas?
Yeah, that's fine. Please go on. Maybe we can discuss later.
Okay. So then we have this inequality. And surprisingly, if alpha equal 1, both quantity must be same. These are mainly shown by using the two-step estimator. In the two-step estimator, in the first stage, you use the square root n sample to estimate the first stage. So then later we can choose the locally optimum estimator. However, if the order is not equal to 1, equal to 2, so in that case, that kind of two-step method does not work. This is very serious problem. Due to that reason, we don't have these two quantities different. So in the case of this phase estimation, this is very famous one. So and H is Hamiltonian is this one. In that case, that's inverse of Fisher information is equal to 1. However, global optimization is pi square, local minimax square. In the case, this is pi square. This is much greater than 1. So in this sense, local optimization, so this kind of optimization, Fisher information does not give the true bound. So in this sense, this works only for the order estimation. So this so now we show that the meaning of two coefficients. In the first coefficient, there exists a sequence of estimators that asymptotically attain the bound. This is this non-zero bound for at all points. This is a very normal setting. However, for C tilde, there is another meaning. There exists a sequence of estimators that asymptotically attain the bound C tilde and satisfy the locally unbiased condition only at point C theta 0. So in this sense, only one point, at the only one point, that point can be attained. So in this sense, this bound can be attained for all points, and this point can be attained only at specific points. That kind of strange behavior is often called super efficiency. This is a very famous concept in the classical statistics. For example, 1986, many years ago, Lucam, this is maybe a French guy, he found that in the estimation of probability distribution, there exists a sequence of estimator such that mean square error go to 0 at a specific point, and mean square error behave as only 1 over n Fisher information at a point. This estimator does not satisfy locally unbiased condition in that optimal point. This possibilical example tells us the importance of suitable condition for the estimator. If we don't consider the good condition or good criteria, so sometimes we have that kind of pathological example, pathological case. So in this sense, this one is only the bound achieved by pathological estimator. So we need to avoid that pathological situation. In order to avoid that pathological situation, I propose to use a local minimax criteria in this way. This point works well. This bound works well. So then it is very important to calculate this quantity. But it is quite difficult to calculate this quantity in general situation. That kind of C tilde is much easier to be calculated. So in the case of state estimation, there is no super efficient estimator under the locally unbiased condition. Of course, if we avoid this condition, then sometimes we have some very bad pathological situation. However, in the case of channel estimation, super efficient estimator exists even under the locally unbiased condition. This one gives a bound for the regular estimator, and this one gives a bound for the super efficient estimator. So usually in the classical case, there is no bound for the super efficient estimator. However, in this situation, there exists another bound for the super efficient estimator. So in this sense, the story is slightly different from original classical case or state estimation case. And also now we need to explain the limiting distribution in the case of Heisenberg scaling. In the Heisenberg scaling, we can define limiting distribution in this way. Of course, sometimes this one depends on C, but if the estimator satisfies some good covariance, this limiting distribution does not depend on the parameter T. In that case, we call that estimator is asymptotic covariant. So, but sometimes this one depends on the parameter theta. So we take the average. We have this distribution, and we take average with respect to parameter theta. Then we take limit. So this one means is the average limiting distribution. Average limiting distribution. Sometimes we focus on this quantity. Now we consider a phase estimation problem. This is a much more realistic situation, and in the following part, I will explain the much more practical estimator. Now we consider that situation. This is phase estimate, phase parameter, phase unitary, and but unfortunately there is some noise, small noise p. So with small I forget p here. So with small probability p, we have a dephasing noise in this way. We need p here. Sorry, we need p here. So then we can calculate RLA Fisher information in this way. So then, in order to achieve Heisenberg limitation, this quantity behave m square, because in order to get the Heisenberg scaling, Fisher information increase n square order. So in order to realize this situation, already Fisher information also increase in this order, but in that one is essentially impossible. However, if noise parameter depends on parameter number of n, in that case, this quantity can be increased with this order. So this quantity can be calculated this, and in order to behave this quantity with this ordering, so we this assumption, this noise parameter is smaller than 1 over n. Of course, this condition is somehow pathological, but to achieve the Heisenberg limitation, the noise must be very, very small in this order. This is a requirement to achieve the Heisenberg scaling in the phase estimation. So we can, and also we can achieve Heisenberg scaling in a practical way, because sometimes our estimator is somehow more complicated, and it is not so easy to implement this one. Now we consider following method. We employ adaptive method only with 1 qubit memory. So please back to the previous situation. So we consider that situation. Of course, in the generic situation, this kind of adaptive scheme is very difficult. Almost not so practical. So this is quite difficult to implement a general situation. However, in my talk, I want to propose or suggest to use very restrictive adaptive method. This one has only 1 qubit memory. If the 1 qubit memory and you adaptively apply this unknown unitary, in that case, that scheme can be easily implemented. So 1 qubit memory is more practical than parallel method. If you have a parallel method, usually you need to make correct measurement. However, if you have only one qubit memory, in that case, the measurement should be done only on the 1 qubit system. 1 qubit measurement is very easy, not so difficult. So in this sense, that kind of situation is much easier than parallel method. So now we explain that practical method with 1 qubit memory. Surprisingly, that kind of method has been already proposed in the 1998 in the 20th century. So last century. So this is very easy, and this is somehow related to Shah's factorization. So in the initial step, you should prepare your state in this way. This is very easy. And you apply this unknown unitary to n times, so many times. And finally, you make measurement, plus measurement and minus. Minus means that the superposition with minus coefficient. So then you can make phase measurement. And you obtain outcome 0 or 1. So this one should be A1. And we repeat 1 k equal to n plus 1 times. So in the k step, you make this one, and the difference is only this number. In the initial case, 2n, but in the case step, 2n minus k plus 1, this way. And later you apply this one. This one depends on our previous outcome. Previous outcome A1, A2, k minus 1 pi. So you apply this unitary, and finally you made the same measurement, and you set the outcome in this way. So then finally we get this estimate. So this is very simple. They choose this method. Of course, their assumption is slightly different from ours because in their setting there is no noise, and theta should be restricted to some discrete value. So this method works with discrete assumption. Theta belongs to the discrete assumption. In that case, the outcome should be always equal to the unknown parameter, exactly same as that's true parameter. If theta is discrete value in this way, and p equal to 0. But even if p is not 0 and theta is continuous value, this method works well. This is one of our results. Firstly, I will explain the p equals 0 case. P equals 0 case, we have this error. So surprisingly, we have this error, behavior in this one. So this order is the same as the number of input copies. So in this sense, we have this one. This is not Heisenberg scaling. Somehow slightly strange. And SY2 pi is somehow very somehow special function. So this coefficient equal to 1.41815 this way. And we can calculate the limiting distribution, but limiting distribution surprisingly Heisenberg scaling. This is quite a strange situation. If we evaluate this error in the mean value, mean square error is in this way, in the sine square, in that case, there is no Heisenberg scaling. However, if you focus on the limiting distribution, average limiting distribution, then we have this Heisenberg scaling. Because the variance of this distribution is infinity. Due to that reason, we cannot have the Heisenberg scaling in the mean square error. And also, we can extend our result when P behave this small behave in this way. So in that case, this average error become this one. However, limiting distribution behave this one. N equal to 1 over this quantity. Sorry, small n is 1 over 2n. I forget this one. Small n equal to this one, this quantity. This is the number of application. So then we have this quantity. This is somehow complicated because theta is a very complicated random variable, and there is a infinite sequence of random variable A and X. The distribution A is somehow truly this is IID and uniform binary variable, and X is somehow biased binary random variable. This X and positive X equal 0 is somehow this one, and X equal 0 is another variable. So this is another independent variable. So by using this quantity, you can calculate this quantity. But this distribution can be calculated because I could make a calculation approximately by using mathematical in this way. So green one is a noisy case. Noisy case is the peak is very small, so not so concentrated. Then this is the limiting distribution. But the noiseless case, we have a very sharp peak in this way. So, but still we have a same scaling. So in this sense, we still have the high dynamic scaling under this condition. So that's all. So now we have some conclusion. So we have a very nice sufficient condition to achieve the high dynamic scaling in the sense of SLD. And also we introduced two kinds of acyclic bound in the channel estimation. And this one gives sometimes good estimator. So, and also we propose using the Fourier transform. So essentially, sorry, I forget this one, but essentially my method based on the Fourier transform. So using the Fourier transform, we can consider phase estimation. And also we have addressed high dynamic scaling. So thank you very much. So this is a reference of my talk.
Thank you very much, Professor Hayashi. The floor is open for questions. Professor Singh, do you want to clarify your question?
I cannot hear. What is the problem?
Yeah, I'm not very sure. I don't know myself. So.
So in this sense, so in the last day, some speaker use the maximum of SLD, Fisher information. However, once we calculate the RLD Fisher information, we can easily check that maximum RLD, maximum SLD behave this way or not. So in this sense, it is very important to check that this condition. Once this condition holds, the maximum RLD can be calculated. This is my method. And this method still extend to this adaptive method. This is not my result. This is the result by Kataria and Wild. He was a PhD student, or maybe he already get a PhD under the supervised by Mark Wild. Maybe he's an Indian guy. I never met him.
I don't.
Indian guy?
I'm not sure actually.
Oh.
There is a further question about other entanglement or PPT breaking properties related.
Their entanglement, PPT breaking, PTP breaking plate. Entanglement, PPT breaking, PPT partial transpose.
Positive partial transpose.
Yes, I know. So, of course, no, channel, yes, if channel is separable or PPT, the problem somehow easier, but I think in that situation, maybe maximum RLA is exist. Maximum RLA should be exist. So in this case, we don't have high dynamic scaling. We don't have high dynamic scaling.
Thank you. Thank you.
Thank you. Are there any other questions or comments?
And also, another important comment is this one. So we need to consider local minimax to realistic bound. Many people only consider inverse of Fisher information. So in this sense, their bound is only this one, so locally optimal. But that local neighborhood shrink very quickly. So in this sense, that kind of method does not work with this limiting order.
Okay, thank you very much, Professor Hayashi, for a very interesting talk. So I would like you to thank you on behalf of the organizers and move on to the next speaker of the afternoon.
Yes.
Naqib, are you around?
Yes, I am around. Can you hear me? Am I audible?
Naqib, can you please share your screen?
So am I audible?
Yes, you're audible. So our next speaker is Naqib Ahmad Warsi. Naqib received his PhD degree from the Tata Institute of Fundamental Research, Mumbai. Prior to his PhD, he was working as a scientist of the Indian Space Research Organization till 2009. And he joined the ISI Kolkata now as an assistant professor. His research interests include non-asymptotic information theory, especially in the designing of information theoretic protocols. Naqib will be talking about quantum OR bounds with application to communication or entanglement assisted compound quantum channel.
So can you give me just 1 minute because there is some issue with my laptop.
Yeah, please take your time. So Naqib, are you there in ISI right now?
Arul, did you ask something?
No, I was asking Naqib whether he was in ISI right now.
Yeah, Naqib is in ISI.
Okay.
Whether he is trying to communicate from ISI or his house, I don't know.
That's what I was asking. Whether right now he is in ISI.
Yeah, but he's not in our department. He's in computer science department.
Okay, okay. That explains the communication.
Hello, Naqib. Hello.
Naqib, if you, sometimes it helps to log out and log in again. That's our issue. Yeah, okay.
Arul, can you see the possibility of that we can start with Shoikat Ghosh?
Saikat is here. Saikat, are you ready with your talk? Of course.
Hello.
Oh no, Saikat is already sharing his screen. Okay.
Hello.
Yeah, Saikat.
Yeah, can you hear me?
Yes.
Yeah, we can hear you.
Yeah, so should I go ahead or?
Yeah, you can.
Yeah, Naqib will have your talk after Saikat. So our next speaker is Professor Saikat Ghosh. Saikat received his PhD from Cornell University in 2006. He's working as associate professor in the Department of Physics, IIT Kanpur. He works on quantum optics, atomic physics, graphene microscopy, and so on. His talk today is quantum coherence, synchronization, and metrology. Saikat, look forward to your talk.
Yeah, can you hear me and see my slides?
Perfectly.
Hello?
Perfectly.
Okay, yeah. So, yeah, many thanks, Arul, for the introduction and to the organizers for giving this opportunity to talk. So I'll actually be talking about quantum coherence, how we like the main theme is quantum coherence, how we actually generate and characterize, along with two applications which are basically synchronization and quantum enhanced metrology, particularly with spin-1 atoms. So so with that, I understand that this is a very highly theoretical audience. Most people are in theory, so I'll basically try to give a flavor of the experiments that we do in the lab and how it effectively looks like. So so when I'm talking of quantum coherence, I'll particularly be basically for us experimentalists, like coherence and superposed states in a wave function picture are identical. So if I start with a very basic experiment of sending a resonant light, just 1 second, can you see my cursor?
Yes, yes.
Yeah, so if I if we just think of an experiment where we are actually sending in a resonant light through a collection of two-level atoms, and we can actually write down an effective Hamiltonian where effectively the light is interacting with the atoms through a transition of this form, which is basically making the atoms go to the excited state and back. And we can solve this, like this is just undergraduate physics, and we already see that there are Rabi oscillations in the system. And when I'm talking of coherence or superposed states, basically, as we all know, that actually like in these Rabi oscillations at any point except the top and the bottom parts for the populations, actually the system is in a superposed states. And that is what we are after, and that becomes a major resource for us experimentalists. But the issue is that like life is not that simple, because this these atoms are actually coupled to many systems, even like all those vacuum modes. And as a result, one of these excited states of this very typical experiment is actually highly decaying. So actually, if as an experimentalist, if I put numbers, this excited state lifetimes are like 30 nanoseconds or 50 nanoseconds for a typical atom of rubidium. And as a result, there is actually not the Hamiltonian is not the whole story, but there's a whole like environment that comes in the evolution. And when actually this experiment is done, we actually see kind of this not really oscillations, but in spectrum, we actually see this kind of Lorentzian line width, which is a signature of the fact that the dominant physics is that of the decay of the excited states. So then the question becomes actually how one can create superposed states of atoms in the lab, which are long-lived, which actually we can actually play and manipulate with. So that's what was kind of a major breakthrough, like almost 3 decades back, where people realized that instead of just a single atomic field, like single 2-level atom, if one actually just extends it a little bit with like 2 ground states, and this can be ground states some Zeeman splitting and so on, so some hyperfine manifold. And if one uses a second laser beam, so again the dipole Hamiltonian looks like that, but there's a beautiful symmetry that comes out, because it turns out now that that bad decaying excited state, which is coupled to these vacuum modes, actually couples to the ground states in a specific way, and that's what actually is making the transition, which immediately implies that there is a state which is orthogonal to this so-called the bright state, this particular composition. And eventually the system will actually go into this kind of a superposition. And here 1 and 2 are both like long-lived ground states. And as a result, like, if you can drive the system as a superposition of 2 ground states, then you can actually observe the physics and see this. And this is what is traditionally called a dark state, or the physics of EIT, or electromagnetically induced transparency. And the key thing to realize is that in this kind of a superposition, there is no spontaneously scattered photons. So basically, actually this if one can actually do this, one can actually take this to the level of like even a single photon, because there is no spontaneously scattered noise and so on. So this is how a typical experiment would look like, that when one is actually sending in this 2-level atom, just this typical thing I was showing, one sees a Lorentzian line width, but when one sends in the second beam, actually what happens is that because this dark state, these atoms are getting pumped in the dark state, so actually suddenly the 2-level physics changes a lot, and you really do not see any absorption, because the atoms are getting trapped in this dark state, which is not coupled to the excited state. And as a result, if you do spectroscopy, you actually will see that in this middle of this Lorentzian line width, there's a transparency window that has opened up, basically, and this was observed like some 3 decades back, and this created this frequency spectrum, actually created a lot of excitement. And this is really like this kind of transparency because of this dark state is because of the reason it's called actually electromagnetically induced transparency, which actually leads to this very long-lived coherences. And this is what I'll primarily be focusing on. So when I'm talking of atomic coherence, which I'll do a lot in this thing, I am basically like, for the theorists, like, even for a single atom picture, like for this kind of a 3-level system, I'll actually be talking about this kind of like off diagonal terms of the density matrix, the diagonal terms being population. So one of the things we studied is actually we started asking the question that this is the spectroscopic signature, but most of the modern day quantum technology experiments are actually done in in real time with pulses. So can we actually characterize the same coherence in time domain, in presence of various decoherence channels and so on? And so this is kind of a real picture of the experiment. What you see here with these coils and so on, inside there's a cell. The coils are for magnetic field, and this is actually a very hot room temperature atoms moving at 350 meters per second. So highly decoherent system, and the question is like whether you can create the superpositions very quickly and actually like have them long lived. So we kind of, so this is a typical experimental trace, the green one, where what you're looking at is the x-axis is actually the peak of a pulse that is sent in exactly in this kind of a scenario, and this is the level structure where actually like there are these two ground states 1 and 2 which I talked about. Hello.
So I could go on.
Yeah, Arul, I'll sometimes ask because we are having some problems with our connection. So I just want to, sometimes I'll ask whether I'm there still. Yeah, so basically, but actually in reality, when we are working with atoms, there are many ground states. So it's an open quantum system. And what I'm talking of is actually sending in a pulse of light and looking at the peak transmission. And when we started doing the experiment, so this is what we see. Actually, the transmitted light is getting absorbed, like, like you see only 40% transmission. But when you turn on this second beam, you suddenly see this transparency, which is what the spectroscopic signature I was showing. And then there's this very interesting like decay, like it actually shoots up a lot and then comes down. And then at a point around 10 microsecond, this x-axis is time scale. When we shut it off, we see actually there's a sharp decay and there's a slow rise actually. And this is a long story, but what we realized is that this time scale, this very sharp time scales, whether it's a rise or fall, are actually a direct measure of the quantum coherence, and comparatively slower decays are actually the classical channels already. And for example, experimentally, we can simulate a system which is otherwise spectroscopically very similar signatures of a transparency window, but without any quantum coherence, and there we do not see any sharp time scales. And actually, this works out very well. So what we realized as experimentalists is that actually this sharp fall actually becomes a very good measure of the amount of coherence. By coherence, again, I mean that a superposition of 1 and 2, like the ground state long-lived coherence that is generated in the system. And basically, so we basically can generate develop a quantifier, which is actually like in an experiment, it's just looking at the oscilloscope and looking at the sharp fall. And it turns out that it actually works out extremely well for closed quantum systems. So we can actually simulate experimentally a closed quantum system. By the way, the green points are experiments, and the dotted lines are actually a full Maxwell block simulation. And we see that for a closed system, for an open quantum system where the generated coherence is much smaller, and for a completely incoherent system, you really do not see a fall. So this is one of the things we studied. It turns out that actually like there's some like very interesting spectroscopic signatures which can fool you from this ground state superposition, which is Otler-Tau splitting. And there too, we actually see that, like if you actually measure this coherence, this fall, there is a very stark difference in the time domain, which actually otherwise it's very hard to discern in the spectroscopic domain, basically. So and finally, in this kind of a very highly decohering hot atom system, what we found is that there is a way through projective measurements you can actually freeze the coherence from decay, and basically you see this beautiful phase coherence actually. So this is just a very quick introduction to what I'm talking of when I mean by quantum coherence. But actually, the really interesting behaviors of this coherence starts happening when we take these atoms, cool them down to very low temperatures, such that even the Doppler, the atoms are not moving so fast, and as a result, you can study these things and manipulate them for a longer time. And that's the next half, which is basically the same physics of this very simple physics, which one can just understand from the Hamiltonian, this dark and bright state and long-lived coherence can actually lead to a quantum memory, where actually one can adiabatically transform optical pulse into an atomic coherence, and then basically retrieve it back. So basically one can make a quantum memory. So how the experiment looks like, this is the setup we have in the lab. This is all home built, and in here you see that these are all different optics, but in between you see this there's a glass cell where the action happens, and we do laser cooling and trapping with radiation pressure. And when everything is right, all the frequencies and so on, you see this kind of this cigar-shaped cloud of atoms. So the coolest thing you can see, because these are 100 microkelvin, much lower than dilution fridge or helium temperatures, and these are about 1 million atoms, highly dilute in this configuration. So we start with this, and how again a typical experiment looks like, just to give you a flavor. So for example, just to start with, if you send in a pulse of light, and just for technical reasons, I'm calling that pulse of light or the electric field as omega p, by the Rabi frequency. So if you send it in a detector, you will see this pulse. But when you actually trap these atoms on its path, you basically see this red one, which is actually all the atoms are getting trapped. It's just a simple two-level physics. But then if you actually turn on, this is what exactly I was talking about. If you turn on a second beam, you actually see that there's a transparency. So basically the pulse again kind of comes out, and you see this kind of large peak that's coming out. And that's here, it's a little complex. There are issues of phase matching, but we send it for some technical reasons in a perpendicular direction. And you can actually play more games. You can actually turn off this control field in somewhere in the middle. So this is where the pulse was coming out because of this generation of the ground state coherence. But now you can turn it off. So you see that actually it gets immediately absorbed. The probe gets immediately absorbed. But later time, when you actually turn it back on, by it I mean the control field, you see that there's a little peak that comes out. And this physics, if one tries to understand, this is again 2 decades back, people understood it very well. Actually, it turns out that if you think of the photons and or the optical field and the atoms together, then you can kind of see that the total state of the system has a part which is purely photonic and a part which is purely atomic, and the atomic part is actually the ground state coherence. And this mixing terms are actually, this omega c is the field because of this kind of perpendicular field which you're turning on and playing this game. So you can actually suddenly it becomes a classical knob to control this quantum state. So by making cosine theta 1, you can make it all photonic, and by making sine theta 1, you can make all atomic. And this is kind of the whole point of the memory. And you can immediately see that actually in this region, and this is data from our lab, you can actually see that in this region we are actually storing an optical pulse coherently in an atom for a finite amount of time, about a microsecond, and then you basically kind of retrieve it back, So this is the point of quantum memory, which is again a 2 decades old physics, but we actually kind of extend this to a little further. We actually extend this to a ground state manifold, which is not just limited to 2 fields, but 3, not 2 states, but 3 states. And right away, one can see that, I was talking all this time, this is the ground state. So there's a spin 1 atom. Now I'm first time coming to the spin 1 atom. And you can see that here, actually, I have talked about a generation of coherence through an excited state of only this one. But the moment you extend it to another level, and if you do similar kind of things, you will have a coherence here. here and a coherence there. So just to mention, this kind of a state, which is partially photonic, partially atomic, and you can control the parts, are what are technically called these dark state polaritons. They are very similar to this condensed matter polariton physics, atom and light states. So basically, you can actually create two such dark state polaritons, and then there is a possibility of them interfering. And that's exactly what we do. That's the new part. So basically, a typical experiment is like this, where there is a probe field, there are two control fields, now, which are actually creating this coherence. And the same thing, you can actually write down now this kind of two polaritons, or we call it spin waves, for if you think of them as collective atoms, So there are two such polaritons. And actually, when you try to retrieve it back, ideally, if everything is coherent, you have done the experiment properly, then these two polaritons should interfere and you should see the relative phase. For example, if you put a magnetic field, this state will go up, this state will go down. So there will be a relative phase between the polaritons. And you should actually see, when you retrieve that little pulse, you should actually see these two coherences interfering. So in some ways, or in a very direct manner, you can think of this as an SU11 interferometer, where actually these probe fields come in, but create these two coherences with a relative phase, and and this is where it's stored inside the atoms. So the light is stored inside the atoms, and in a later time, you can actually retrieve them back into a photonic field. And you can actually exactly think of this as an interferometer with a relative phase. So this is is this true in the experiment? So this is a typical experimental plot. What you're looking at is the x-axis is time, the y-axis is basically the intensity that's measured of the probe field, and you see that this is basically a probe field intensity that goes into the system, and at some point we stop the light and then later retrieve it back. And this series of months are actually, we are doing it later and later, So basically, you see that this, as we retrieve the stored excitation later and later, you see that this intensity is going down, and this is because of some decoherence in the system, So actually, you see that in this region, the system is stored in atoms, and this is purely atomic state, and when we retrieve back, it is photonic. But now we are extending it into a spin-1 ground state manifold. So is this true that actually two coherences are interfering? Can we actually see that interference? And that's, to do that experiment, we actually apply a magnetic field, and what we see is this, that actually the retrieval. So as we wait longer, and so this is for a constant magnetic field, and if you see that the phase accumulated is like b times tau, the storage time. So as we wait longer and longer, you see this beautiful kind of oscillation that's happening because of the magnetic field. And if at any point, if we wait, and so these are experimental plots, and if at any point, hello?
Yes, I can.
Yeah, okay.
I think about
so at any point, when we actually, so this is basically retrieval at a particular point, and when we basically just sit there but change the magnetic field. So here the x-axis is the magnetic field, and the y-axis is basically the relative phase between these optical fields. You see this beautiful interference pattern, exactly like an optical interference. But this interference is purely because of the fact that the atoms, while storing the light, the states are basically picking up a relative phase, So with that, this immediately gives us a tool for looking at something very interesting, which is this quantum synchronization, which was predicted for a long time, and people have played with this, and where actually there was some theorem, there was some no-go theorem. People showed that in a two-level atomic system, you cannot really have synchronization. So So basically, one needs a 3-level system, and the synchronization happens because of this interference of coherence. So since the time is very short, I'm giving you a very quick introduction to synchronization. This is just classical synchronization, which starts with a limit cycle oscillator, which is otherwise, if you look in the phase space, looks very similar to a simple harmonic oscillator, except that there are nonlinear decay and gain, which kind of sets the oscillator to a fixed amplitude, but the phase is completely undetermined because it's kind of driven by the reservoir. But the interesting thing about this limit cycle oscillators is that if you put a very small phase perturbation, I'll come back to this over and over again. If you put a tiny little phase perturbation, then it turns out that actually the system locks to that. So in reality, if you look at a simple harmonic oscillator, it exactly looks like a limit cycle oscillator, which is this bottom thing. If you put a phase perturbation to a driven simple harmonic oscillator, it forgets after a while the phase perturbation, and goes back to its driving one. But for a limit cycle oscillator, if you put a phase perturbation, it kind of locks to that, and from there on it follows that. And the question was whether you can realize this in quantum systems. There was a very interesting proposal in 2018 where actually people kind of like Roulet and Bruder kind of proposed that firstly you can actually visualize this a quantum system, a very low dimensional quantum system in phase space through a Husimi-Q function, and there you can actually see something like a limit cycle. If you actually prepare, for example, if you take a spin 1 atom and prepare all the atoms in this middle state, then you can see something very similar to a limit cycle. And there, if you actually can manufacture this this incoherent decays, then actually the system, like in presence of this like anisotropic decoherence, the system actually just localizes basically. Please ask questions if you have, like, since I cannot go too much into details, but basically, and it turns out that this localization of this this system in the space actually happens because purely of interference of quantum coherence in a spin 1 system, which is lacking in a spin half, where the phase is an overall phase. So this is the experiment we set out to do. If you see actually what I talked about, this coupling control and the probe are effectively coupling between the spin 1 system. So this was the ground state manifold. In fact, this is how the theorist would view. This is how this ground state manifold we experimentalists view. So here, besides this storage and retrieval that I talked about, phase sensitive, you also need to act. Hello.
So I could go on, I think.
Yeah, so basically you need to also manufacture this this decoherence, and that we do. I would avoid this, this is just technical, very experimental, how we manufacture this decoherence. This doesn't actually exist. And this is how the experiments look like, so we actually, from the experiment, we do a state tomography. So we reconstruct the states through actually a perfect matching of simulations. And if you see, this is the experiment. These are how the simulations look like. This is in presence of magnetic field. This is in absence of magnetic field. And when we reconstruct the state, this is what we find, that, like we start with a limit cycle state. So we actually create the atoms all in the middle state. But then we have this, we actually basically turn on this storage. And when we reconstruct the state while it's stored in the atoms, so we are only looking at the atoms, we have eliminated the optical fields, we actually see that right at the point when we generate these couplings through this control and probe fields, the system gets localized. In fact, that localized one, as I was saying, that if you put a small little phase perturbation, it follows the phase. And that's exactly what we find, that when we put a little magnetic field, this is how the system is evolving. This is from data that actually this localized state from the limit cycle actually starts precessing around the equator because of this dynamic phase that we are putting in. The system is actually a little bit more complex than that, and I would avoid that unless there are questions. It turns out this is not the whole story. There's a very important part that these decay channels play. In fact, if you look at the whole phase space, not everywhere you can actually get synchronization unless you put this decay. So you know the same interference with the decays to be identical, and there you see that there are regions but there is no synchronization. So these plots are actually a measure of synchronization. But when you make the decay anisotropic, actually you find that the system actually starts getting synchronized in every region. Actually, so these are actually all experiments and experimentally constructed synchronization measure. And synchronization measures are just basically that limit cycle I was talking about, just integrated over phase space to see and kind of calibrated in a way so that for a limit cycle it will exactly be zero. Arula, am I running out of time?
Yes.
So basic, huh?
Yeah, I think you have 5 minutes in all, including questions, Saika.
Okay, so there are some questions about there were always people worried about whether there's something different about quantum synchronization versus classical synchronization. There's a prediction of destructive interference and synchronization blockade, which we observed actually. I'll skip all this. There is a telltale sign of this Arnold's tongue where actually there are some collective effects. I'll skip all that. I'll just end with the last part, which is actually the fact that immediately, from the system, you can see that the system is extremely sensitive to magnetic fields. In fact, this is magnetic field, and you can see that this retrieved polariton actually has an oscillation in time, which is basically from the fringes, you can right away use to measure the magnetic field. What we see very interestingly is that as you change this the number of atoms, actually the scaling of the retrieval is non-linear. It's not linear with the number of atoms. So basically, so there's an enhancement, quantum enhancement. And if you look at the sensitivity of the magnetic field, firstly, these are AC magnetic field measurements, and in the lab we measure magnetic fields down to picotesla or less. And you see that as you scale the number of atoms, usually for non-interacting systems, you would have expected a linear scaling. Here, there's a non-linear scaling with the number of atoms and magnetic field. And you can, as a result, compare it with a linear gain that you would have expected normally. And you see that there's a metrological gain of almost 6.57, 6.5 dB of metrological gain, purely because of the fact that you are not looking at one atom, but a collection of atoms. So to summarize, I have talked about very quickly, I apologize to the audience, but it was a short time, 3 things. One is in a highly decoherent system where atoms are moving very fast, how you can very quickly in time domain characterize quantum coherence, and then how you can use it to see interesting new physics, which is basically quantum synchronization. Ours was the first observation ever of quantum synchronization in any kind of system. And finally, how we can use it for good use of quantum technologies, which is basically metrology with many atoms and measuring very small magnetic fields with quantum, enhancement with the number of atoms. So with that, the work, all the work are done by the students. So the primary thing I talked about is with Pratik, and a large part is Arif, who is now a postdoc in Germany, and also Arnab, Shubham, Gautam are directly working on the systems, but we also have a parallel system working on graphene, where we actually are now observing very interesting time crystalline phases, and those experiments are actually being headed by also Arnav, but Javed, Jyoti, Atish. So with that, it will be great to actually take some questions.
Thank you, Saikat, for summarizing 3 lovely works at least. Thank you very much. So questions.
I apologize. I think I went too fast. So
No, it was actually.
I think it didn't make any sense, probably. So people are overwhelmed. Anyways, it was a very theorist group, and I think anyways experiments are harder. Yeah, but it's fine, absolutely. Yeah. But thank you for the opportunity.
Let me start with people who take time. So, Saikat, you were showing how information moved from photonic to atomic back to photonic thing in your memory experiment, right?
Yeah.
So is that something which you can repeat again? I mean, is it possible for you to go back into
yeah, in fact, it's very interesting that you are asking this, because we have been like, we are actually gearing up, like starting to do this kind of experiments where actually kind of this like doing it over and over again, kind of towards a time crystalline phase again, and seeing, like, after n repetitions, when we recover, whether we see a phase like I showed oscillations as a function of magnetic field, but it's very interesting to ask whether one can actually see an oscillation which breaks the time reversal symmetry. So yes, that's something we are very, very keen on. So basically periodically driving the system. I guess that's what you're asking, right?
Yeah.
So that would be the next, another set of experiments, which we are actually presently setting up and doing in fact. Yeah.
And the synchronization is very interesting. I have only basic understanding of classical synchronization, where you have some driven system which is synchronizing with something else, driving or something. Is that the kind of thing which is being done here?
Here it is exactly like that, except that
actually,
so
even in the classic synchronization of those pendulums and so on, you have some couple of driven systems which are synchronizing. Rather than a single oscillator, I mean, what is it synchronized with, right?
Yeah, so basically that's the thing that like in the simplest possible case, it's a limit cycle oscillator, which is actually synchronizing with an external driving force, right? Which is so weak that it's actually not changing the amplitude, but it's just doing a phase perturbation. That's the point I was saying, that in fact the classical synchronization itself can be thought of purely for a single oscillator in terms of phase perturbation, that the only difference between a driven, like if I think of a single oscillator synchronization, the only difference between a driven classical simple harmonic oscillator and a limit cycle oscillator is that the limit cycle oscillator remembers the phase perturbation. So if you do a phase perturbation, the system actually, because like the limit cycle oscillator is basically like it has this it has some nonlinear damping and so on. So the phase is not determined, so that's what the limit cycle is. It might have arbitrary shape, but basically the phase is not set. And if there is a forcing, which might actually happen because of an external weak perturbation, or which might happen because of its neighbor, actually providing it, that it remembers in some ways. This is also a classical memory, right? Because it immediately picks up that phase and picks up the phase oscillation. So this is the simplest classical synchronization with a single oscillator, and that's kind of what we realize, except that we are still very intrigued and trying to explore, thinking whether there are collective effects already there, but already everything I talked about in the quantum synchronization is effectively a single particle system.
Thanks. Lovely experiment. Are there other questions? I don't want to fault Saikas here. Okay. Doesn't seem to be anymore, and I think we'll continue Saikat later. Thanks again for a lovely.
Thank you. Thanks a lot. Thank you for seeing all of you. Yeah, it's very nice.
Yeah, thanks a lot. So our last speaker for this session is Icqif Warsi from ISI Kolkata. Yes. You can see a whole lot of. You can see your desktop. Yeah. Icqif, can you talk?
Yeah, hi. So can you?
Yeah.
I thought like, am I audible?
Yes, yes. You're
Okay. So, I mean, I'm very sorry for all these technical issues.
It's okay. Yeah, please.
Yeah. So, okay. So, many thanks to the organizers for inviting me for this talk, and I would also actually like to congratulate the speaker, the organizers, for organizing such a nice conference. So, as the title of my talk says,
Sorry, Nakib, just to interrupt, may I request all participants to kindly mute themselves? I think there's some disturbance. Yes, please, Nakib.
Yeah, so as the title of my talk says, that I will talk about a quantum or bound. So this is a joint work with Rahul Jain and Anurag Anshu. So what I mean by quantum or bound is that I will try to prove a quantum version of the classical result, which is about the fact that the probability of the union of two events is lower bounded by the probability of the individual events. So what I mean by all this is the following. So what I mean by all this is that, given two sets which are a subset of a bigger set, let's say here in this case is the calligraphic X. So what we want here is that, like given these two sets E1 and E2, we want to find a set E star such that the probability of the set E star is at least bigger than both of these individual sets. And the answer we know is quite obvious. In the classical case, we'll just take the union of these two sets. But now I want to ask the same question in the quantum case. That is, given a quantum state, rho, which is a positive operator with trace 1, and given two projectors, the question is, using these projectors, can we construct a pi star such that the trace of pi star rho is at least bigger than the max of trace of pi 1 rho and trace of pi 2 rho. So you see that this question has a similar flavor to the previous thing about the probability of the union of two events. So one trivial case can be that, like we can take this pi star as the whole of the Hilbert space. So I can take this pi star as the identity, and then of course this trace of rho would be greater than the trace of both of these guys. But that would be quite trivial. So we want something very, so we don't want such a trivial thing in terms of pi star. So the question again is that, does such a pi star exist? And the good news is that it does exist. And a version of this quantum or bound was proved by Aronson individually, and then by Harrow, Lin, and Montanaro. So in particular, Harrow, Lin, and Montanaro proved that given two projectors pi 1 and pi 2, we can come up with a pi star using these two projectors such that we can get this lower bound, but with a scaling of 1 over 7. But this is not very interesting for our purpose. So I will tell you what my purpose was to find this pi star. So we try to find some other lower bound, and we actually show that given two projectors pi 1 and pi 2 and a state rho, we can construct a pi star such that for every delta in 0 and 1, we can construct a pi star such that the trace of pi star rho would be at least that the trace of pi star rho would be bigger than both the trace of pi 1 rho and pi 2 rho, but we get a hit of delta. And the second property which we show that this pi star satisfies this ordering condition. So the second condition might look not so interesting, but for our purpose, it has a lot of value. And when we discuss the application of this pi star, we will see that like why this second condition is also important. So to convince you why this lower bound in the first case here should exist, like why such a pi star should exist, I will try to give you a very brief proof of why this bound is true, and actually our result is actually a very not so, right, it's actually a very straightforward application of a very nice result by Jordan, and which is called as the Jordan's lemma. It says that if we are given two projectors, pi1 and pi2, then actually what we can do is that there exists a basis such that both pi1 and pi2 can be simultaneously diagonalized. So you see, like, because of this nice basis which actually exists, we can sort of make this pi1 and pi2 commute. So I mean, I'm using this roughly here. I mean, of course they will not commute, but what I'm trying to say is that this pi1 and pi2 suddenly start behaving very nicely relative to each other in this nice basis which Jordan proved in his paper. But also further, the good property is that each of these elements on the diagonal will be either be a 1 cross 1 matrix. So if it is a 1 cross 1 matrix, then the entry would be either a 0 or a 1. Or if these entries are a 2 cross 2 matrix here, then they would be a rank 1 projector. So all in all, each of these entries in the blocks are actually a rank 1 projector. So the way we construct our pi star is as follows. So what we do is that we go inside each of the blocks. Okay, so let's say we go inside the alpha block and try to see whether the overlap between each of these rank 1 projectors is very high. So if it is high, we choose any one of them in that block. So for example, in the alpha block, if this overlap is very big, so we choose one of the guys. So in our case, I have just chosen pi1 alpha. But if the overlap is not so big, then what we do is that we take the identity over that block. So for us, this pi alpha is an identity over the alpha block. So actually our pi star, which has some nice properties, would be constructed like this. So what we'll do is that we will sum up all these projectors by the conditions above, like we will choose the projector depending upon their overlap is high, that is their inner product is high or not. So and then what we do is that over all the blocks we will sum up all these projectors. So if we construct this pi star in this way, it is not very difficult to show that that the answer to this question whether we have this kind of pi star is true, and we can actually show that that this lower bound and the upper bound, like these two conditions holds for this pi star. And actually not only about like here we have only talked about the case when we have two projectors, pi1 and pi2, but actually using this construction about two projectors, we can actually show the following: that suppose we are given a collection of quantum states, and suppose we are given a collection of projector operators, then actually what we can show is that for every delta in 0, 1, we can show that there exists a projector pi star such that the trace of pi star rho I. So basically, the trace of pi star rho I means that if we use pi star as the measurement, then this measurement will succeed on rho I with very large probability. But the bad news is that if you see that we have an extra log 2s terms here, and this is coming up because we are applying our Jordan's lemma over pairs. So and we are applying this Jordan lemma again and again until we are exhausted with all these pairing of pi1, pi2, and so on and so forth. So in fact, if S is some even number, then we'll get a hit of log S. But if S is not an even number, then at most we will get a hit of log 2S. And similarly, we will have this other condition. So now I will tell you the application of a quantum or bound, just to tell you why we came up with such a bound, such a quantum or bound, and the reason is the following. So before doing the quantum version of the problem, I will discuss the classical version. So a very typical problem, and like one of the most fundamental problem in quantum information theory, is that there are two parties, Alice and Bob. Alice wants to communicate some message to Bob over some noisy channel, and she does some encoding and Bob does some decoding. And the question which people ask is that what is the best rate of of communication, such that the decoding error goes to 0 as the number of channel used goes to infinity. And the answer to this question was given by Shannon in a very fundamental paper, where he showed the where he defined the channel capacity and things like that. But one of the key assumptions in solving such a problem is that we know the channel behavior. So like before this talk, Professor Hayashi was talking about channel estimation. So like typically what people do, like they try to estimate the channel and they believe that that they know the channel behavior as it is, and then they say that okay, the best rate of communication is that you maximize the mutual information between the channel input and channel output, and you maximize this over the input distribution. So the channel behavior is characterized in terms of this conditional distribution P of y given x. But because such a thing is not very practically feasible in general, so we try to relax this condition. So instead of saying that we know the channel behavior as it is, we sort of relax this condition a bit. And by a bit, I mean to say that we assume that this channel comes from a set of channels. So instead of being one channel, we say that okay, this conditional distribution of the channel will be one of these 10 guys. So let's say here this S is 10. So then and both Alice and Bob know that they don't know the channel behavior as it is, but they only know that one of the channel out of these 10 channels is acting. Then the question is that what is the best rate at which you can decode such that the decoding error is very small? And then it is quite intuitive, and I think many of you would expect is that you would try to maximize the mutual information between the channel input and the channel output over the worst case channel. So one can show that this is the channel capacity of a compound channel. So by a compound channel, I mean to say that a channel comes from a collection of channels. So we don't know exactly which of the channel is acting, but we know that one of these 10 channels, for example, is acting. So in this case, what we can do is that the best rate at which you can communicate is that you maximize the mutual information for the worst case channel. So likewise, we have a quantum version of the problem, where there are two parties, Alice and Bob. They're trying to communicate some. Alice is trying to communicate some message to Bob, and using quantum channels, and they also share some entanglement. And the goal is that they want to maximize R such that the decoding error is very small. But again, so this problem is very well studied in the quantum case. And again, people assume here is that they know the exact channel behavior, which is the super operator which maps the input A to B. But again, this thing is not very practically feasible. So like in the classical case, we sort of relax this condition. In the quantum case, we say that like one of these 100 channels, for example, is acting, but we don't know which one is it. So again, we ask the same question, like what is the best rate possible such that the decoding error is very small, and then we actually show that it's sort of very similar to what we see in the classical case, but here you see this very funny looking notation, which is IH epsilon. So it is some sort of mutual information, but it is actually called the hypothesis testing divergence. But I will not go into the detail about what is this hypothesis testing divergence, but I will tell you that like to solve this problem of finding the best rate when you don't know the channel, the whole problem boils down to the following: that given a collection of channels, and there is the psi a prime bs is like some state which has been induced at Bob's end, and Bob want to come up with a POVM such that POVM accepts this joint state with very large probability, and it accepts this tensor state with very small probability. And again, like to get this first thing, we actually use the first condition of our quantum hour bound, and to get this exponentially small thing, we use our this upper bound of pi star in terms of pi 1 and pi 2. So if we use this pi star, if we use our quantum hour bound, we can construct such a POVM, which is a lambda in our case, such that the joint state would be accepted with very large probability, and this tensor dot state, which is the marginal of the joint state, would be accepted with very small probability. Likewise, there is a more refined version of this problem. So in this case, people assume that that Alice knows what is the channel, like which channel is acting, but Bob has no idea. Then in this case, what happens is that we can again use this quantum or bond which we invent, and we can again show that so in the previous case, if you see, we were maximizing the worst case channel, but in this case, this worst case has come outside. So in this case, when the Alice knows, then the best rate is that you minimize the mutual information. So we maximize the, so it will be in this min max fashion. Like this answer would be in terms of this minimize over all the channel and then maximize the mutual information between channel input and the channel output. So another application of this quantum or bond is the following. So there is a very famous problem which is called the problem of composite quantum hypothesis testing. So what does it mean? It means that the aim here is to discriminate between different sets of states. So what do I mean by that? So suppose we have two sets, S1 and S2, and S1 consists of some quantum states, S2 consists of some quantum states, and then we define this convex hull of, for both S1 and S2, we define a convex hull of states which is rho tensor n, and where these rows belong to this SI, where SI means either it is S1 or S2. And the goal here is that we want to study this number over here, which is beta n epsilon. So I mean, this expression might look very long, but actually in English, what it means is that we want to come up with a POVM such that POVM succeeds on all the states in the set S1 with very large probability, but that POVM accepts all the states in this second set, which is S2n, with very small probability. That is, it should be as small as possible. So this problem was studied by Bhatta, Bernardo, and Hishe, where they studied this asymptotic behavior of this guy and like this 1 over n log of 1 over beta and epsilon, and it actually, in a typical information theorist language, this term is actually called the error exponent. And so actually they studied this problem when both S1 and S2 are not finite, like they can be an infinite set, but we actually studied this problem when this S2 is a finite set, and we actually recovered their result using our quantum Orban, and we show that actually this error exponent converges to this relative entropy of these two states. So you can see more about this talk, like whatever I have discussed, but you can read in more great detail in this following reference, which got accepted in 2019 in IEEE transaction. So yeah, I mean, that's the end of my talk. Thank you.
Thank you very much, Icqif. Are there questions or comments?
Hi, Icqif.
Yes.
You are referring to Jordan's theorem where two projective measurement can be block diagonalized with highest dimension 2 cross 2. So where did you exactly use this Jordan's lemma?
So once we have this pi, pi star which I'm showing here. So can you see the screen?
Yeah.
So this expression is true for for any pi 1 and pi 2, we can get this lower bound. But actually we use this when we study this problem. So actually what we want here is the following, that like we will get, depending upon S, we will get many states, but we want to accept all these states, psi a prime b s with large probability, and we want to reject these guys with with as high probability as possible. So actually, like to analyze these two conditions, we actually require that construction. it comes from the definition of. So there are many things here, but actually we require this 5-star to analyze these two conditions.
Okay. Okay, thank you. Yeah.
Could you show me the final slide? Final slide. No, next one. Yes. No, this one. No, this one.
Yeah,
There, this, I'm slightly confused. Their result is related to the, related to, what to say? Quantum Sanoff, no?
Yes, it is somewhat related to quantum Sanoff.
But quantum Sanoff is already shown by other authors.
Maybe, I don't know actually, I'm not but they have this paper in some convention in mathematical physics where they prove this. But they prove it for when they said S2 is not finite. So we only prove it when S2 is finite.
But that line is not so difficult, very easy. So rho is 1 and sigma, no, I'm sorry, confusing. So if sigma is 1 and rho is infinite, so that case is quantum Sanoff. But now sigma is plural.
Yes. So there are many states in
if sigma has so many, so that situation is more complicated.
Yes. That is the main contribution here. Yeah.
All right. Any further questions or comments? Does not seem to be the case. So thank you very much, Nakib, for a very interesting presentation. And I thank you on behalf of the organizers and thank all the speakers of the afternoon, Hayashi, Saikat, Ghosh, and Nakib for very interesting talks. Thank you all very much for attending and participating.
Thank you, Arul, for chairing the session.
Thank you very much.
So now we close this session and we will start at most possibly at 16:20 after the tea break. Okay, thank you. Thank all the participants. Devashi.
So this session will be chaired by Professor Shivashish Ghosh, and Shivashish Ghosh may have chaired some earlier session also, so he has already been introduced. He's from IMSC, Chennai. So Shivashish, take over.
Okay, thank you. Good afternoon, everybody. So this session will have 3 speakers. Professor Nilanjana Datta from Cambridge University, then Professor Manavendranath Bera from ISAR Mohali, and Professor Anil Saji from ISAR Trivandrum. So our first talk will be by Nilanjana Datta from University of Cambridge. So Nilanjana, she is a professor in quantum information theory at the Department of Applied Mathematics and Theoretical Physics at University of Cambridge, and also a fellow of Pembroke College. She obtained her PhD from ETH Zurich, working on quantum statistical mechanics and quantum Hall effect. So she, she has done pioneering works in these quantum channels, and in particular these one-shot capacities of quantum channels. So today she will be talking about determining whether a quantum channel has positive quantum capacity. Nilanjana.
Thank you very much, Shivashish, for the kind introduction. It's a real pity that I can't be there in person because Kolkata is where my home is. Anyway, this is work done with my PhD student, Satvik Singh. It's on the archive and it's has been accepted to the journal NPJQI. So I'll be talking about determining whether a quantum channel has positive quantum capacity. So as you know, quantum channels model the most general physical transformation that a quantum system can undergo. This includes time evolution of both open and closed quantum systems. And they serve as quantum analogs of classical communication channels. For example, Alice can use the quantum channel to send signals to Bob by suitable encoding and decoding. I'm just having a little problem here. Can't see the top of my slides. Give me one. I don't know what to do. Can you see my slides? But not full screen, I guess.
Yeah, we can see, but it's not full screen.
Yeah. I'm so sorry about this. It's just something strange with the sharing. Can you give me one second, please?
Sure, sure.
This is really awful. It's just that it's coming on the top and I cannot do it full screen. Anybody has any suggestions?
Yes, maybe push F5. F5.
F5. Is
Yes.
it Shift F5 or function? Yeah. No, it's just that you see what's coming. The bar is on the top, so I cannot.
Yeah.
I guess you need to share your entire screen instead of just PowerPoint.
Yeah, I'm sharing my entire screen. It's just that I can't go into the more. How can I move the top bar from the top? Any idea? This bar is preventing me to go to click on slideshow. You see this black bar on the top.
Yes, maybe escape or something.
On the bottom, you can click that. Right
Sorry?
in the bottom of it. Right at the bottom of your PPT, there's a tiny little thing on the right-hand corner. Yeah, right there. Just a little, move a little side. So that's
Perfect. Okay, good. Thank you for that. Okay, so But still I can't see the top of my slide. Is there any way to move this black thing from the top? You see the black bar?
You can try to drag it down.
Okay. Perfect. But you can't get rid of it, I guess. Okay.
For us, it is okay.
For viewers, it is okay. There is no problem. Nilanjana, for viewers, there is no problem. Okay.
Okay. So let's talk about capacities of a quantum channel. So capacities of a quantum channel quantify the optimal rates of reliable communication through it. So unlike a classical channel, a quantum channel has various different capacities, and that depends on different factors. For example, the nature of the information transmitted. You can use a quantum channel to send either classical or quantum information. It could depend on the presence or absence of auxiliary resources. For example, prior shared entanglement between sender and receiver. Also on the nature of inputs to successive uses of the channel. It could be product or entangled. Or the nature of measurement on outputs of multiple uses of the channel. You can do individual measurements or collective measurements. And also, it depends on whether the information is private or not. So, but in this talk, we will just be considering the situation where the information transmitted is quantum and where there is no extra auxiliary resources shared between the sender and the receiver. And in this case, the capacity of the channel is called the quantum capacity. So in other words, the quantum capacity is the maximum rate of noiseless quantum communication through the channel in the absence of any auxiliary resource. So the question we ask is, does a given quantum channel have positive quantum capacity? In other words, can the given quantum channel be used to transmit any quantum information reliably from a sender to a receiver in the absence of any auxiliary resource? However, answering this fundamental question has proved to be extremely difficult despite years of research. So let's see first why this is so. So a few definitions to start with. So let MD denote the set of D cross D complex matrices. And as you know, a linear map phi from MD to some MD out is a quantum channel if it is completely positive and trace preserving. So we need the concept of complementary channels. So if phi is a channel from MD to some MD out, and phi C goes from MD to MDenv, env for environment, then they are said to be complementary to each other if there exists an isometry from CD to CD out tensor CDenv, such that for any X input to the channel, when you partially trace out over the environment, you get the channel output phi X. And if you partially trace out over the output space, you get the complementary channel output phi C of X. So in other words, phi C models the leakage of information by phi to its environment. So the formula for the quantum capacity of a quantum channel is known. It was obtained with in different levels of rigor by Lloyd, Shore, and Devashi in different papers and is often called the LSD theorem. And this is the expression for the quantum capacity of quantum channel, for which I use the symbol Q of phi. So let me go through this expression. What is Q1 of phi? So that is called the coherent information of the channel phi. And it is the maximum over all possible rho input to the channel of a quantity which I denote as IC phi rho. So what is IC phi rho? It is called the coherent information of the channel phi when the input is rho. And it is just the difference of two von Neumann entropies. The von Neumann entropy of the output of the channel minus the von Neumann entropy of the output of the complementary channel. So here in the expression A, we have Q1 phi tensored n. So that is just the coherent information of n copies of the channel. Also, one thing we should note, we will use this later, that if you're interested in the coherent information of the complementary channel when the input is rho, then we just use the expression above with phi and phi c interchanged. And this, therefore, is just equal to the negative of the coherent information of the channel when the input is rho. Now, why is it so difficult to compute the quantum capacity of the channel, to determine the quantum capacity of the channel? Okay, that's because in the formula A, we have this regularization. It's a limiting formula, which makes the problem intractable. So what we need to do is to compute Q1 phi tensor n for an unbounded number n of copies of the channel. And this computation itself is a non-concave optimization problem. There are, however, certain facts that we know. Firstly, the coherent information of a channel is superadditive. So Q1 phi tensor n is greater than or equal to n times the coherent information of a single use of the channel. So if we plug this in to the formula A, we can therefore see that the quantum capacity of the channel is lower bounded by its coherent information. There are, however, channels for which the coherent information is strictly superadditive, which means Q1 phi tensor n is strictly greater than n Q1 phi, which if you plug into A would yield that the quantum capacity of the channel is strictly greater than its coherent information. And because of this, we see that the limiting regularization formula that we have there is indeed needed. And therefore the formula is untractable. So the question we ask, therefore, is a simpler question. We do not want to compute the capacity of the channel. We just want to determine the following. Is it possible to determine whether a given channel phi has positive quantum capacity? So you give me a channel phi, and I ask the question, is Q phi positive or is Q phi equal to 0? So before talking about the answer to this question, let's look at channels with 0 quantum capacity. So there are quantum channels phi for which Q phi is equal to 0. In fact, currently 2 such classes of channels are known. The first is the so-called anti-degradable channels, for which I use the acronym ADG. And phi is said to be an anti-degradable channel if there exists a CPTP map N, which, when acting on the output of the complementary channel, yields the output of the channel itself. Then, by a simple use of the no-cloning theorem, one can prove that the quantum capacity of such a channel is equal to 0. A second class of channels is the so-called family of PPT channels. So consider a bipartite state rho AB. Say the A part is sent through the channel and the B part is left untouched. So here IDB denotes the identity channel acting on B. So at the output end, you get this bipartite state, sigma AB, given in the following manner. So such a channel phi is said to be PPT if the partial transpose on B of the state sigma AB is positive semi-definite for any input rho AB. Now it is known that PPT states are undistillable, and using that fact, one can establish that such channels have 0 quantum capacity. So this is the picture. So here is the class of PPT channels and the anti-degradable channels, and at their intersection lies this well-known family of entanglement breaking channels. So these are channels for which the sigma AB state, which I showed in the last slide, is necessarily a separable state for every input state rho AB. However, the current understanding of the set of 0 capacity quantum channels is incomplete and poor. There could be possibly other quantum channels with 0 quantum capacity that we have not found yet. So let's go back to our question. Is it possible to determine whether a given quantum channel has positive quantum capacity? Now, there was no known systematic procedure to determine whether a given channel has positive quantum capacity until recently, where the first step was taken by Vikesh Sidhu, and he has a very nice paper in Nature Communications. So let me start with our contribution. What we do is we obtain a powerful sufficient condition which can be used to detect positive quantum capacities for a wide variety of quantum channels. And by exploiting this result, a number of important examples of quantum channels can be shown to have positive quantum capacities. So let's start with the key idea. We'll start with a simple lemma. So let phi and phi c be mutually complementary channels. Then one can easily show that the non-zero eigenvalues, multiplicity included, of phi acting on psi and phi c acting on psi are identical for any pure state psi. So this is easy to prove just using the Schmidt decomposition, but we will talk about its implication. It implies that the coherent information of the channel when the input is psi is necessarily equal to 0. That is easily seen by just inspecting the formula for this coherent information. So we know that it is just the difference of these two von Neumann entropies. And if phi psi and phi c psi have identical non-zero spectra, then their von Neumann entropies are identical, and hence the difference is 0. So what we ask is, what happens if we perturb this pure state psi with an arbitrary mixed state, sigma? So we consider the state rho epsilon, which is 1 minus epsilon psi plus epsilon sigma for any epsilon between 0 and 1. And obviously, when epsilon equal to 0, it reduces to the state psi. So consider the following input state, rho epsilon, that we just constructed to the channel and its complement. So this is the state. So by linearity, when phi acts on it, we get this state. And when the complementary channel acts on it, we get the other state. Now, at epsilon equal to 0, let us focus on the lambda equal to 0 eigenvalue of the outputs of phi and phi c. So these have the following multiplicity. So we are looking at the 0 eigenvalue of phi psi and phi c psi. So the multiplicities are obviously equal to kappa and kappa c, where kappa is equal to the dimension of the kernel of phi c, and kappa c is the dimension of the kernel of phi c acting on psi. So this is phi acting on psi and the kernel of phi c acting on psi. So the question we ask is, what happens when epsilon is positive? So we turn on the perturbation. So the key mathematical tool we use to answer this question is the famous theorem of Relish from the analytic, which deals with analytic perturbations of Hermitian matrices. So let us consider A epsilon, which is a perturbation of A0. So A0 and A1 are D cross D Hermitian matrices. For the time being, I consider any epsilon in the reals. So let lambda 0 be an eigenvalue of A0 with multiplicity M. And let P0 be the orthogonal projection onto the corresponding M-dimensional eigenspace. Then for sufficiently small values of mod epsilon, Relish's theorem says the following. It says that A epsilon has exactly M eigenvalues with convergent power series expansions in the neighborhood of epsilon equal to 0. So for all the eigenvalues lambda j epsilon from j equal to 1 to m, it looks like the following: lambda 0 plus lambda j1 epsilon, etc. Hence, as epsilon goes to 0, they all converge to lambda 0. And the important thing is that the first order correction term, lambda j1 not equal to 0, are the non-zero eigenvalues of A1 sandwiched between the orthogonal projections P0. So in other words, trace of P0 A1 is just equal to the sum of all the first order correction terms in that expansion. And we will use this fact in the next slide. So how do we apply Relish's theorem? So Relish's theorem deals with such an matrix A epsilon. So for example, let A epsilon be the output of the channel when the input is this perturbed state rho epsilon that we defined. So we can just shuffle things around a little bit and write it in the following way. So then this is A0 and this is A1. And let us focus on the eigenvalue lambda 0 equal to 0 of A0. So as we found in a previous slide, the multiplicity of that eigenvalue is just equal to the dimension of the kernel of phi psi. So what happens when epsilon is turned on? Epsilon is positive. Then by Relish's theorem, phi of rho epsilon and phi c of rho epsilon have exactly kappa and kappa c eigenvalues respectively. Let us denote it like that. And these converge to 0 as epsilon goes to 0. Why? Because we are focusing on lambda 0 equal to 0 eigenvalue of A0. So in the limit epsilon going to 0, they both go to 0. For all the j's from 1 to kappa, or respectively from 1 to kappa c. And they admit convergent power series expansions in the neighborhood of epsilon equal to 0, given by the following expressions. Now, how is this useful in determining whether the quantum capacity of the channel is positive or not? So remember that the quantum capacity involves an entropic quantity, which is the coherent information. So let us focus on the coherent information of phi when the input state is rho epsilon. So this is this quantity IC phi rho epsilon. And remember, when epsilon equal to 0, it reduces to IC phi psi, which is equal to 0 because psi is a pure state. So the question we ask is very simple. Is the derivative of this coherent information positive for epsilon sufficiently small? Why? Because we start at the value 0, and if the derivative is positive, then we can infer easily that the coherent information is strictly increasing in a range of values of epsilon, say epsilon between 0 and some delta. And this would then imply that the coherent information itself is positive in this range. And then we're done, because we know that the quantum capacity of the channel is lower bounded by the coherent information of the channel, whose definition is in terms of the supremum, and which is lower bounded by replacing the supremum by choosing a particular rho, which is this rho epsilon, which is therefore positive. So if the derivative is positive, then we can infer that the quantum capacity of the channel is positive. So all we need to do is to inspect the derivative. And conversely, if the derivative is negative, then the coherent information of the channel is negative. But this would imply that the coherent information of the complementary channel is positive, because we saw that the coherent information of the complementary channel is the negative of that of the channel itself for any input state. So let's think about computing the derivative. So this was the expression for the coherent information of the channel when the input is rho epsilon. So all we do is to put in the formulas for the von Neumann entropies, because lambda j epsilon and lambda j c epsilon were the sets of eigenvalues of phi when the input state is, and phi c when the input state is rho epsilon. And these were the convergent power series expansions that we get from Relish's theorem. So if we just do the computation, you can find that the derivative can be, the leading order term of the derivative only involves the first order correction terms. And we have the remainder, which I denote by m epsilon, which is bounded in epsilon. So if we denote by k psi and k psi c, the orthogonal projections onto the kernel of phi c and the kernel of phi c psi, then from this Relish's theorem, we know that these sums are just given by the traces of the projections times the output, just by this expression. So we get a very nice expression for the derivative of the coherent information. And this puts us in a very convenient position. I've just highlighted what I had in the last slide, and therefore we immediately see that if the trace of k psi phi sigma is greater than k psi c phi sigma, that means the quantity in parentheses is positive, then the derivative is positive, hence the coherent information corresponding to the input rho epsilon is positive, and hence the quantum capacity of the channel is positive. And conversely, if that parenthesis is negative, which would happen if the opposite trace inequality is satisfied, then we find that due to the following chain of inequalities, the quantum capacity of the complementary channel is positive. So this leads to our main theorem, which I call the star theorem, which states that if phi and phi c are complementary channels, and for a pure input state, psi, let k psi and k psi c denote orthogonal projections onto the kernel of phi psi and the kernel of phi c psi, then the quantum capacity of the channel would be positive if there exists states, a pure state psi, and in general a mixed state sigma, such that this trace inequality holds. And on the contrary, the quantum capacity of the complementary channel would be positive if the opposite trace inequality holds. Now, it might seem that it's not maybe non-trivial to check these trace inequalities for any arbitrary channel. But thankfully, we also have a very useful corollary, which has a much simpler condition for checking whether a quantum channel or its complement have positive capacity or not. So I call it a useful corollary, but before stating it and seeing how it follows simply from this main theorem, let me introduce a few necessary definitions. So first is the definition of a minimal output and environment dimensions. So let phi be a channel, quantum channel as we've been considering so far. Then one can denote something called the minimal environment dimensions. That means you consider the minimum dimension dn such that there exists a complementary channel going from MD to MDN. So the channel phi c has to be complementary to phi. And in using the same formula, if you compute the minimal environment dimension for the complementary channel, you get the minimum output dimension of the channel. Now, this might look complicated, but the necessity for this is very simple. Suppose you have this generalized depolarizing channel. For any input rho, all that the channel does is maps it to some state sigma. So even though the channel might be defined from MD to some MD out, the minimal output dimension is just the support sigma. So the channel does not explore the entire output space. So that's why it is meaningful to talk about minimal output and environment dimensions. There is also a very simple lemma which gives you a way to compute these dimensions. What can prove that this minimal environment dimension is just the rank of the complementary channel acting on the identity matrix, D cross D identity matrix, and this is equal to the rank of the Choi matrix, which I denote by J phi. And similarly, the minimum output dimension is the rank of the Choi matrix of the complementary channel. So what I'm saying is these dimensions can be easily computed. However, for capacity calculations, we can assume without loss of generality that the channel we are considering are minimally defined. That is, we just consider D out, the minimal D out, to be equal to its minimal output dimension, D out star, and similarly Dn, the environment dimension, to be the minimally defined one. So you might ask, why is this so? That's because, let's start with phi and assume it to be minimally defined. Then let W be an isometry which goes from D out to some other output space, D out prime. So one can always define a new channel in this manner. And then this channel phi tilde would go from MD to MD out prime. But one can easily check that a channel phi C, which was complementary to the original channel, is also complementary to phi tilde. And for any input state rho, the von Neumann entropy of the output of the original channel, is identical to the von Neumann entropy to the output of this new channel with a different output space that we have constructed, phi tilde. So the von Neumann entropy is all that comes in in the definition of the quantum capacity. And so we can infer that the quantum capacities of the channel with the minimal dimension and that with the out prime dimension are the same. So every channel is related to such a minimally defined one in the following manner. And therefore, we can assume to start with that the channels we are working with are minimally defined. So now I am in a position to state the simple corollary. So the corollary is that if phi is a channel from MD to MD out, such that the following condition holds, that there exists a pure input state such that the rank of the output of the channel is the minimum of the two dimensions that I just introduced, and let phi c be a channel complementary to phi. Then the quantum capacity of the channel is positive if the output dimension is greater than the environment dimension, and the quantum capacity of the complementary channel is positive if the reverse inequality holds. So this is definitely much simpler than the star theorem. But let's inspect. This result was also obtained by Shidua, but let us inspect this assumption. So this is what we assume. Now what one can prove, and one can easily verify in fact, that for any channel and any arbitrary pure state, the rank of phi psi is less than equal to the minimum of these two dimensions. And this just follows from the fact that for any input state rho, the support of phi rho is contained in the support of phi acting on ID. And that the rank of phi psi is equal to the rank of phi c psi, which just follows from the fact that our original lemma, which was that the phi psi and phi c psi have identical non-zero spectra. And the following relations, which we had stated in a lemma before. So the fact that the rank is less than equal to the minimum of these dimensions is easy to verify, but the assumption that in the corollary is stronger. It requires that this upper bound is saturated. So this is the same corollary. I'll show it quite a few times, so don't worry about reading the whole thing. So what it states is that if the two dimensions, the output dimensions and the environment dimensions, are unequal, and if there exists a state for which phi psi or phi c psi is full rank, then q phi or q of phi c is strictly positive. So let me say, pick just the second statement and see how it follows immediately from the star theorem that we encountered before. So this corresponds to the situation when the output dimension is less than the environment dimension. So therefore, we assume that the output dimension is less than the environment dimension and the channel are minimally defined. And we also need to assume that there exists a pure state such that the rank of phi psi satisfies the desired condition. And in this case, the minimum dimension is that of the output because of this condition. So phi psi is full rank. So remember we had defined k psi to be the orthogonal projection onto the kernel of phi psi. So if phi psi is full rank, k psi is 0, but k psi c is not equal to 0. So the star theorem told us that the quantum capacity of a complement of a channel would be positive if there exists a pure state psi and a mixed state sigma, such that the following trace inequality holds. So if we use the star theorem and choose sigma to be the completely mixed state, then we will see, because k psi is 0, the trace on the left-hand side of this inequality is equal to 0, whereas the right-hand side is not equal to 0. So the star theorem holds, and therefore the quantum capacity of the complementary channel becomes positive, which was the statement, second statement of the corollary. Okay, so once again, I'm flashing the same corollary. So in order to use it, you have to, step one is to check if the output and environment dimensions are different. It's only in that case that it applies. And we can do this easily because we have these simple ways to compute these output and environment dimensions, the minimal ones. And secondly, we have to check that there exists a pure state such that this rank condition is also satisfied. But this step is in general hard, unless certain inequalities hold. And these inequalities are called, we call them star inequalities. So I'm just going to flash them. So there are two families of these inequalities. They are just inequalities between the minimal output dimension, the minimal environment dimension, and D, which is the input dimension. So if this set of inequalities hold, then the quantum capacity of the channel is positive, or the quantum capacity of the complement is positive. And also if this set of inequalities hold, then we have similar inferences. So you see, these are very powerful inequalities, because irrespective of the form of the channels, we only need to check these inequalities between the input, output, and environment dimensions. So we have the star theorem, the star corollary, and these star inequalities. But I would like to stress that the star theorem has a much wider applicability. It is even applicable to channels for which the environment and output dimensions are equal, and even if there does not exist a psi for which phi and phi c are full rank. And we will see that we need to use this theorem, for example, to infer the positivity of the quantum capacity of the complement of the, for example, the Werner oligo channel to be positive for certain dimensions. I'll come to it in a while. So let's look at some applications. So let's start with the well-known depolarizing channel and also their sister channels called transpose depolarizing channel. So a depolarizing channel of parameter P from output input space of dimension D to output space of dimension D out, and dQt, let us denote by dQt transpose depolarizing channels of parameter Q. So for any X input to the channel, the depolarizing channel, as you all know, acts in the following way. With probability 1 minus P, it keeps the input unchanged. And with probability P, it replaces it by the completely X state. I have this trace of X here because in my definition, I'm allowing any possible D cross D matrix, not necessarily a trace one. So this is a CPTP map for all P's in that range. And similarly, the transpose depolarizing channel, the difference is instead of outputting X with probability 1 minus Q, it outputs X transpose with probability 1 minus Q. And it is also a CPTP map for this range of values of Q. And for D equal to 2, it was proved by Debbie Loying and John Watrous that the quantum capacity of the complement of the depolarizing channel for a Q bit is positive for any P positive. So what we do is we extend their result for all Q dits and also have a corresponding set of results for transpose depolarizing channel. So this is our theorem. For any finite D, the quantum capacity of any quantum channel which is complementary to a Q dit depolarizing channel is positive for any P positive. So this is really a direct extension of Loying-Watrous result. And for a Q dit transpose depolarizing channel, for Q between D over D plus 1 and the open interval going up to D over D minus 1, the complementary channel also has positive quantum capacity. And both these set of results are proved simply using the star inequalities, which, as you saw, all only involved comparing dimensions. But what happens at the endpoint, D over D minus 1, this extreme case? So this extreme case of the depolarizing channel, transpose depolarizing channel, is the very well-known Werner oligo channel. So what happens here? So if you compute the minimal environment dimension using the Choi matrix, as I said, you'll find that it is equal to D times D minus 1 over 2. If you compute the minimal output dimension, it's D. So we see that whenever D is greater than or equal to 4, you do have this inequality satisfied. So you would think, okay, so perhaps we can apply the corollary. But you remember that the corollary has two assumptions. One is that the dimensions have to be unequal, and the secondly, that there should be an input state for which a certain rank condition, so either phi psi or phi c psi, has to be full rank for any pure input state. But for the Werner-Holliver channel, the output for any input state does not satisfy this condition. It is rank deficient. However, this is where our star theorem comes to our rescue. And using it, we can prove the following. We can prove that any complementary channel to the Werner-Holliver channel has positive quantum capacity whenever D is greater than or equal to 4. Just before ending, let me give you one last example. These are the so-called Hadamard or generalized dephasing channels. They're known by different names, or the Schur multiplier channels. So they are parametrized by a matrix B. B is a positive semi-definite matrix, and its diagonal elements are all equal to 1. Input dimension D, and so you go from MD to MD out. So how does it act? This is the Hadamard or entry-wise matrix product. So if you inspect the ijth element of phi bx, which is the output of the channel when the input is x, that is just given by bij times xij. So the effect of the channel is to diminish the magnitude of the off-diagonal entries, hence the word dephasing. Now, it is known that the complementary channel of a Hadamard channel is entanglement breaking. So phi CB, which is a complementary channel, is entanglement breaking. And we know that entanglement breaking channels are also anti-degradable. And anti-degradable channels, we know, have zero quantum capacity. So we know that the quantum capacities of Hadamard channel, of complements of Hadamard channels, have zero quantum capacities. But if a complementary channel is anti-degradable, then the channel itself is what's called degradable. Well, I haven't introduced the definition of degradability, but just to, note the fact that if a channel is degradable, then its quantum capacity is just given by its coherent information. So a valid question to ask is, when is the quantum capacity of phi b equal to 0? Okay, this is the theorem that we prove. If phi b is a Hadamard channel, then its quantum capacity, which we know is equal to its coherent information, is equal to 0 if and only if phi b is entanglement breaking, which happens if and only if B is the D cross D identity matrix. So this equivalence A was known previously. It is also known that if phi b is entanglement breaking, then the quantum capacity is equal to 0. So we know this direction, one direction, the reverse direction. So it suffices to prove that phi b is not entanglement breaking, implies quantum capacity of the channel being strictly positive. And this we do prove using the corollary if rank of B is less than D, and using the theorem, star theorem, if rank B is equal to D. So in summary, using elementary techniques from analytic perturbation theory of Hermitian matrices, we devise a simple strategy to detect positive quantum capacities of quantum channels and their complements. And what we get is a sufficient condition. And we can use these results that we get, the theorem, the corollary, and the inequalities, to determine the positivity of the quantum capacities of certain channels or their complements, and which can be applied to a host of familiar channels. So maybe a minute for an open problem. So star theorem said this, right? That the quantum capacity is positive if there exists a pure state psi and say some mixed state sigma, such that the following trace inequality holds. Yeah, k psi and k psi. C were the orthogonal projections onto the kernel of phi psi and phi c psi. But it is interesting to ask, could there be a channel phi for which the coherent information of n users of the channel is 0 for all n less than equal to m for some fixed integer m, but it is positive for all n greater than m? This would be really interesting, because this could potentially shed new light on the superadditivity of coherent information. Thank you for your attention, and many thanks to my students.
Thank you, Nilanjana, for very nice talk. So questions?
Shivashida, can I ask a question to Professor Datta?
Sure.
This is Indranil. Thank you, Professor Datta, for such a nice talk. I have one question. In your earlier slides where you are defining the coherent information, so we can always express this coherent information as a negative of quantum conditional entropy, right?
Sure.
So, and hello, am I audible?
Yes, I can hear you. Mm-hmm.
So negative of quantum conditional entropy. So if the output, so whenever we are writing down this coherent information, say for as a negative of conditional entropy, then it will be useful to look out for the output states which is having negative conditional entropies, right? So if some way we can able to detect the states which are having negative conditional entropies in the output, then we can say that we can have a positive coherent information, if I am correct.
Yeah, but yes, you're looking at, I'm writing them as the coherent information as a difference of the output of the channel and its complement, because I want to use properties of the channel and its complement. Yeah. And you want to write it as the negative of the coherent information. Two ways of looking at the same
negative
thing.
of conditional.
Of the conditional.
Yeah. So there is one comment over here. So at least we can create witness to detect negative conditional entropy states. So and for that reason, I think if we can create witness to detect negative conditional entropy states, then we can, in the similar spirit, we can detect those channels which are having a positive coherent information. Do you think that is possible, or is there is some other nuances to it?
Yes, but the question is how would you detect it? Yeah. So the way we are doing it, we are giving a prescription for detecting positive coherent information and detecting negative conditional entropy. Yeah, they are equivalent questions, because you're writing the same formula in two different forms. Yeah?
Right.
And but the way we deal with it allows us to use this very powerful yet simple analytic perturbation theory. So I have not thought about witnesses to determine negative conditional entropy.
So one of the application that we have shown, maybe I can communicate with you offline, in our paper in Physical Review in 2021, detecting the negative conditional entropy states with the help of witness operators. And that also having an application where we had mentioned that it can detect those channels which is having a positive coherent information.
I'd be very interested in, sorry, Indranil. Yeah, I would be very interested in seeing that, and maybe that can lead to another application of what we have done. Yes. So I'm very happy to chat offline. If you could send me an email with the reference, I'd really appreciate it.
Sure. Thanks.
Thank you.
There is a question in the chat box. It says that it's from Ananda. Does the framework that is getting positive derivative of coherent information also work for channels other than only those of mutually complementary channels in order to decide whether a channel has positive quantum capacity?
Yeah, but we are the point is we are interested in a channel, right? And we only want to, if the derivative of the coherent information of the channel itself, yeah, for this input rho epsilon is positive, then we can immediately infer that the channel would have positive capacity. Yeah. So for that positivity of that quantum capacity, we need not look at the complementary channel. So yes, the answer to your question is yes. All we need to see is that is the derivative positive or not. But very often what we prove, so they are like dual to each other, right? The channel and its complementary channel. And very often what we are proving is that the positivity of not the quantum capacity of the channel, but of its complement, because of this dual nature. With certain inequalities being satisfied, we get positivity of the quantum channel, and for certain cases, we have positivity of the complementary channel. But indeed, the positivity of the derivative of the coherent information of the channel when the input is that perturbed state rho epsilon is sufficient to determine the positivity of the channel itself, nothing to do with its complement.
Okay. Any other question?
I see a hand by Bihalan Bhattacharjee.
Okay. Yeah, Bihalan.
Hello. Thank you very much, Professor Dotto, for this nice talk. I'd like to ask that we discussed one class of channel, that is PPT channel, which does not have any quantum capacity, and it also includes the entanglement breaking channel as well. So there is a notion of eventually entanglement breaking channel, that there might be channels which is not. Hello.
Yes, I'm very aware of that definition. Yes.
So my question is, can we comment something about the quantum capacity of such eventually entanglement breaking channels?
Very interesting question. I would not like to say with. So that means, I don't know the answer to the question straight away, but it's a very interesting question to ask because, as you know very well, eventually entanglement breaking means we are considering not tensor products of channel, but rather successive applications.
Composition of the channel, and it's a special case of the squared conjecture. Actually,
okay, drop me a line, Bihalan. Let's talk offline, because I don't know the answer.
Thank you very much. Thank you very much. Thank you very much.
Okay. So I have, a side question. What about, going to infinite dimension?
Would be wonderful, right? That's on our cards.
Yes,
but you see, it has to be a completely, it's got to be a different sort of treatment. Because as you must have seen through this whole talk, all I was talking about was comparing dimensions, etc. Yeah. So this is on our to-do list, and if we make any progress at all, I'm sure I'll get that with you.
Okay.
But it's a challenging problem. Maybe if I have one more minute, I can say something. Remember, we have this corollary, and the corollary had this important point that you need there to exist a pure state which is such that the output of the channel or of its complement is full rank. Yeah? And this checking that this state really exists is not trivial, is a hard problem. But what we have done in a following work is to prove that if you sample channels randomly in a very sensible way, then almost surely such a pure state does exist. So I did not talk about that work in this talk, but if you're interested, you can just, we are the same set of authors, Satvik, the first author of the paper as well. And so this shows that it is not, almost surely for almost all random channels, you would find that obstacle can be jumped over because almost surely such a state exists. Thank you very much. I'm very sorry about the initial disruption. Hope it wasn't too awful or distracting.
Thank you. Okay, so let's thank the speaker again. So let us have our next speaker. So our next speaker is Manavendranath Bera. He is from ISER Mohali. So Manavendra is He's a faculty member in the physics department of Isar Mohali. So Madhavendra did his PhD from the University of Paris Sud in France. He's an assistant professor in the School of Physics at Isar Mohali. His areas of expertise is quantum information computation, quantum thermodynamics, foundations of quantum mechanics, and so on and so forth. So today he is going to talk about bounding quantum advantages in post-selected metrology. Manavendra.
Thank you, Shivasishda, for your nice introduction. And I also would like to thank the organizer. First, I would like to congratulate for organizing such a wonderful conference in this trying time. And also thank you for giving me the opportunity to present some of our recent work. It's a little cute work. And that is bounding quantum advantages in post-selected metrology. So here I start, just give me a moment. Yeah. So here is the outline. So the outline essentially has, first part is related to quasi-probability distribution. In particular, I will emphasize on a probability distribution called Kirkwood-Dirac distribution and indicate the notion of non-classicality one may find there. Then I shall be talking about quantum metrology. And then I go towards post-selected quantum metrology and talking about its quantum advantages and how to bound these advantages. And finally, sort out what is the source of such quantum advantages. And then I will conclude. So here goes the quantum quasi-probabilities. So obviously we know there are two kinds of quasi-probabilities we are very much familiar with, and they're coming from phase space. So the first one is the Wigner quasi-probability distribution, and it is introduced in 1932 somewhere around. And later on in 1960s, while working in quantum optical systems, Glover and Sudarshan came up with a quasi-probability distribution. So here, these alphas are essentially coherent states, and this is also known as this Glover-Sudarshan P function, and so on and so forth. So apart from that, almost during that time, I would say rather around 1933, Kirkwood also came up with another description of quasi-probabilities that kind of can take this phase space notion. That means you deal with two observables, they may not commute, but using these two observables, whether you can express a physical system or not. And later on, that has again further be contributed by, got contributed by Dirac during 1945. So for the people who would like to know more about these quasi-probabilities, I would request them to go through these two articles. So here it is. So what does it mean by, or what do we mean by this Kirkwood-Dirac distribution? And in this setting, I shall be considering mostly discrete variable situation. And let us say there is a state that is rho here, and I consider two non-commuting observable A and B. These are the projectors essentially for the time being. And I also at the same time assume that these observables, not only they are mutually non-commuting, but also their individual projectors also non-commuting. And then any arbitrary state can be expressed in this form. So that means, as you see, it looks like in literature, it is known to be conditional state when you consider successive measurements and so. But what I want to highlight here is that this rho can be expressed in this form, where this P in the parenthesis AMBN can be is essentially the trace of rho AM and BN. And the important fact here is that this is a complex number. And this particular probability distribution is known as Kirkwood-Dirac distribution. And the most important thing is that this probability distribution is informationally complete. That means if I fix any two observables having this particular condition satisfied, then all the information that I would like to know from this state is essentially can be extracted from this probability distribution. And what further is that this kind of like a joint probability distribution, obviously in this case it is complex, and in particular they also follow the Bayes rule and all these things. At the same time, you can always get back to the reduced probability distribution just for summing over one of these observable. Okay, the outcome of one of these observable essentially. Well, now if I want to say that obviously this is complex, and many of the cases whenever we find that there is a probability distribution which is not positive semi-definite, it possibly have some kind of non-classicality. So now if I ask, how do I understand whether this Dirac-Kirkwood distribution essentially encode this non-classical feature in terms of probably this negative or some complex feature it may have. So here actually it goes like this, that excuse me, that this probability distribution, obviously, since I said it's a complex, it's often you have to trick in order to get access to this probability distribution. And there are one very interesting paper actually came during 2007. It says that this probability distribution can be simulated with the help of successive projective measurements. So essentially what you could do is that this probability distribution can be expressed in this form where you have your rho, the first term. You see, I have two terms, three terms here. This is the first term, which essentially also called the Wigner probability. It means that you take your rho, you measure in AM, and then again you measure the resultant state with Bn, and this is the corresponding probability. And then there are two other terms. Essentially, if you look at the second term, is essentially like you have your rho, I measure in AM, and after I measure, and also the complement of this AM, whatever you get, this is your rho prime. And this is kind of like the modification you have done to your state after you measure this AM. And then you take a difference between these two and measure this Bn. And this particular quantity can be positive, negative. It essentially tells you the probability difference between the undisturbed state and the disturbed state. And also there can be some imaginary part where again you are doing you are looking at the probability difference between rho and rho prime, where the rho prime is this, but with a Bn pi by 2 that is essentially rotating this Bn with pi by 2, this particular operator, what I wanted to say. So what I wanted to say in this is that this joint complex Kirkwood-Dirac quasi-probability distribution you can simulate in terms of successive projective measurements. And what I want to highlight here is that this probability distribution, if you look at little closely, you see it kind of having some term here. I hope you can see my cursor. This looks like a weak value where the observable, where you kind of pre-select your state in AM and post-select it in Bn, and essentially this is kind of a weak value. And obviously we know that the weak values can be complex. And now the question came later on that, well, I have this probability distribution indeed, but how can I, in general, find out whether it is classical or non-classical? Well, so far there have been quite a few studies, and most of the cases it has been shown that if you look at this probability distribution in particular, and if I find that the real part of this is negative, then only we say it has some non-classical feature. Okay, but what we found that I'm going to also justify at the later part of my talk is that if this quasi-probability distribution is not equal to this first term that I mentioned to be the Wigner formula, then I say that this is actually non-classical. So that means I give you, even for a discrete variable situation or discrete level system, that I can have a joint probability distribution, and that can be complex or negative and so on and so forth. And whenever I find this particular condition satisfied, I say it does have some non-classical feature. Okay, so with this, I shall now go towards the next part of my talk, and that is the quantum metrology. And I think many of you in the audience probably are familiar with this, so I'm not going going to get into details. So essentially the metrology, when we say, it deals with the theory of measurement. So that means, let's say I want to measure some particular parameter, which is a priori unknown, and how do I really determine such a parameter? So what we in general do is that we take a system rho and let it go through this particular region. It can so happen that, for example, let's say I would like to measure the magnetic field in particular region. So what I will do, I in general can send a system in a state having some spin and let this spin to interact with this magnetic field, and because of that the state evolves to some other state, and obviously this other state encodes the strength of the magnetic field, not only that, even the direction of the magnetic field and so on and so forth. So that is how essentially we do. If obviously in classical case, you consider like this is a probability distribution of some initial ensemble of state, and then you let it interact with your environment or the region where you are interested in, and then you get your modified state, and then you do a measurement. And obviously there are many possibilities of choosing the measurement, but whatever it may be, you get certain probability distribution. And from this probability distribution, essentially, you try to get or try to infer about this particular parameter, let's say in this case, theta. Okay, and what we know from classical Cramer-Rao bound is that if I look at this probability distribution, then the precision with which I can measure the value theta is inversely, it's lower bounded by the inverse of classical Fisher information, where the classical Fisher information is given here. Excuse me. Well, the same thing also one could extend to quantum domain. So in that case, the states should be states that you will be considering, the system you will be considering are quantum, and then again you send it to some place of your interest or system of, I would say, the region of your interest, and that will evolve the state, let's say, to rho theta, and again you do the measurement. And in that case, whatever the probability distribution you will get, if you look at the variance, that means the uncertainties or the standard deviation that you get while you are measuring this theta is essentially lower bounded by the inverse of quantum Fisher information, where the quantum Fisher information is essentially maximized over all possible choice of your measurement. That means when you analyze the overall final state after it got evolved. And what we know that if I consider my initial state to be a pure state, let's say, and you let the interaction to be unitary for this case, for example, let's say you want to measure the value of this theta, and obviously you evolve it with some generator, then in that case, this Fisher information is nothing but 4 times the variance of this generator. And actually, you can have you can also scan over all this initial state, and what you find that is the maximum possible Fisher information that you may have is essentially the square of the spectral distance. That means the difference between maximum and minimum eigenvalues of this generator. Okay, and then people have used this particular quantum metrology to get some quantum advantages. For example, that instead of sending one system one after another, rather they took initially entangled quantum system, and what they found later on is that you can actually increase the precision in the sense that you can go from standard quantum limit to Heisenberg limit, where your Fisher information essentially scale with n instead of square root of n. Okay, so this is what I have about quantum metrology. And now I shall go towards the post-selected quantum metrology. So obviously, the moment I say post-selected, that means in this regular framework, somewhere I will actually introduce a post-selection, and the selected states after the evolutions will essentially would be analyzed through some final measurements. So here is the scenario, and throughout this talk I shall be considering actually the pure states as my initial state and the unitary evolution as the way I have displayed here. So here I have this preparation, then I let this state to evolve through some unitary evolution here that encodes this parameter theta, and overall the state becomes psi theta. And then I shall select essentially a part of it using some, for example, in this way, I select it through some projector. And in this case, it can be rank 1, rank 2, rank 3, depends on the dimension or whatever the interest you have. But for this case, let's say it's more than rank 1 projector. And obviously, after you project it, you have some kind of the post-selected state, as you can see it from here, and with the probability with which this selection may occur is essentially given by this. Now, obviously, as you can understand what Fisher information does, Fisher information essentially it actually quantifies the information that got encoded in this psi theta. But obviously, if you only look at a part of it, obviously you can think of that you may get a less amount of information that is being that had been or that got encoded through this unitary evolution. And actually, one could define this corresponding Fisher information that I call to be the post-selected Fisher information. That means that is actually appearing from this ensemble after you post-select is given by essentially almost the similar formula that you have, but with a term on the here is like 1 by the post-selected probability, and on the second term it is 1 by post-selected probability square. And what one can show that this particular quantity is always positive. That means this first term is always greater than the other one, the second one. And when we talk about quantum advantage, what it exactly means is that you can have this Fisher information, that is this post-selected Fisher information, much more than the one that is possible when you don't execute it or when you don't have this post-selection essentially. So it is again, it looks like in a similar language, if I say it's like the weak value like situation. So that means in weak value, if I have this pre-selection and post-selection, I can come up with a value, the weak value, which goes far more beyond than the observable that allows in general. So here also, in turn, that when I have this post-selection, my Fisher information can be increased arbitrarily. And essentially that is termed to be the quantum advantage. That the meaning of why I say quantum advantage will be clear later on. Okay, and this particular work has been actually done last to last year in Nature Communication, got published there. Now the point here immediately comes is that from here, that obviously this Fisher information, they can take arbitrarily high value indeed, but with a cost where the post-selection probability goes to 0. So that means there is a kind of a trade-off I have. So I can obviously say my Fisher information got increased. That means my precision may increase substantially, but such a situation will appear with a very low probability. So if I now want to really understand this quantum advantage, one needs to take into account the probability along with this conditional, this post-selected Fisher information. And that is what we are going to essentially do in the next, where I introduce something called the metrological efficiency. As I said, you may have a gain to have high Fisher information, but the cost is that it appears with low probability. So here we define the metrological efficiency, that is nothing but the probability times this conditional Fisher post-selected Fisher information. And if you express it a little bit further, what it appears is that this particular term here now becomes combination of two terms, where the first term is expressed in this way, which is nothing but the probability of post-selection times the square, mod square of the weak value, and another term that involves essentially the Kirkwood-Dirac distribution, here as you can see, which is expressed in this form. So this is also an interesting point to mention, is that although we are not in the paradigm of like weak measurement kind of scenario, but the weak value naturally appears here because of this pre-selection and post-selection. Okay. So now if I want to say, let's say, what is the quantum advantage or essentially how do I see it essentially in this case? So if I once again display this metrological efficiency, I'm just repeating it, this expression again and again, because this looks a little complicated, so that you don't have to remember all this thing. So once again, this is the function of the weak value, and this is essentially the second term is the function of this Kirkwood distribution. And now, if I look at this Dirac-Kirkwood distribution, again, I can express them in two terms. One is essentially the Wigner term that I have mentioned here, and another term essentially that is coming up because of like mutual non-compatibility of this of these operators, this Fk or the projector of the generator, essentially Am, and so on and so forth. And what I want to say from here is that for pure state, the metrological efficiency is 0 when this particular distribution gets equal to this Wigner formula. That means this quantity here becomes exactly equal to this Q rho. So that kind of tells you that, well, in which situation this particular quantity becomes exactly equal to this particular quantity. This is only in the case where you have some kind of mutual commutation between Am or Fk, or it may so happen that your rho is commuting with Am or your rho is commuting with Fk. So in either of these cases, it kind of tells you that obviously you won't see any feature that is appearing from this non-commutativity. And in that case, your Q, that means this Dirac-Kirkwood distribution, becomes exactly equal to the Wigner formula. And in that case, you won't have metrological efficiency. So that means if I want to have metrological efficiency that is non-zero, then you need to have this relation to be violated, and that immediately indicates that means your quasi-probability distribution must have some additional term apart from this Wigner formula that is essentially coming from this non-commutating part. Okay. Well, and then after understanding this quantum advantage, essentially what we went on to show essentially that how this quantity may be bounded, because previously I have seen that the Fisher information can increase at the cost of decrease in post-selection probability. But if I combine them together, what we can show here is that this efficiency is essentially bounded by this quantity where A is your generator with which you evolve the system through unitary evolution. And now the question may come, that means that although you may have arbitrary increase in your Fisher information, but the probability cannot be increased in an unbounded way. So they must be having some kind of a trade-off relation, and this is essentially giving this, and this right-hand side is the upper bound. And you can understand how this can be proven. It's that, see, we have two different terms here, and all of them, this is also a positive quantity, this is also a positive quantity. If we can make this particular quantity to be 0, and at the same time, this particular quantity to be maximum, then obviously this particular relation would be satisfied. And it is already known from this reference is that whenever I have a state, I have the relations that are satisfied in this way, this particular, that means the first term actually saturates this value here, and obviously, and as we have shown also in the paper, that in that case this particular term also becomes also becomes 0, and that is how you actually reach this upper bound. Okay, so with that, now essentially we will go towards an example with which we get this bound saturated. Okay, so once again, I start with my Shah I, the initial state, and then this unitary encoding, and then the final state. Do I have time? Oh, I'm sorry. So essentially
5 minutes.
I'm sorry. Okay, so essentially, again, I have this post-selection and the post-selected state and probabilities, and then I essentially go towards a generator that is of this form. So I have to flash it very quickly, and the post-selection I have chosen in a little bit smarter way, in this way, like F1, F2, and then this is my initial state, this is the final state, and then what I would like to estimate essentially this theta 0. And what we find that this post-selected quantum feature information is this, the post-selection probability is this, and essentially it satisfies this optimality condition. Okay, so this is essentially, we come up with an example and we show that indeed you can saturate this bound. Now, if I look at the Dirac-Karpuk distribution for which we claim that we are getting this quantum advantage, then if I just look at the Dirac-Karpuk distribution corresponding to the aforementioned system, state, evolution, and post-selection, I see all these are actually positive, essentially. And on the other side, if you look that this Wigner formula, that means this particular quantity here, well, they obviously would be positive because these are classical quantities, but obviously this Q is not equal to this Wigner. That means the Dirac-Karpuk distribution is not equal to your Wigner formula. So and even in this case, we get this quantum advantage. Not only that, we saturate the bound. That means we maximize the efficiency. So this kind of tells you that positivity of Dirac-Karpuk distribution not necessarily imply classicality. Rather, what we find is that whenever this Dirac-Karpuk distribution become equal to the Wigner distribution, only in that case we can say that this is essentially classical. So with this, I shall go towards the conclusion. So we talked about Dirac-Karpuk quasi-probability distribution and how it can be understood as like joint probability, complex joint probability. And then we introduce metrological efficiency, derive a bound of on the quantum advantages, and we identified the source of such quantum advantages and also justify that non-classical signature of Karpuk-Dirac distribution is not necessarily the negativity or something. It is rather has to be equal to the Wigner formula. So with this, I would like to acknowledge that Saurav and Dr. Subrajit Modak essentially has collaborated in this work. So I'm very happy that we have something to present here, and also we have, let me also acknowledge the fund that we have received from this ACRB DST. And with that, I thank you. Thank you for your attention.
Thank you, Manav, for this nice talk. And now the session for question.
Yes.
Let me see whether in chat box there is any question.
Hi, thank you so much for the presentation. It was very clear presentation with many nice results. I would like to understand two things better. So your lambda square in your example, or generically the upper bound, which is the norm square, operator norm of the A square. So how does this relate to the delta A square that you mentioned? So can I use the efficiency and
so this
efficiency that is higher than the delta A square?
Can you so which delta? Okay.
You see, because I think that in the papers by Nature communication that you mentioned, for instance, I had the impression that although you had a post-selected advantage, you needed to be clever to choose a correct type of post-selection operators in order to obtain an efficiency that gets towards the delta A square. Now I would like to understand if you and your collaborators improve this to getting even higher than the delta A square.
See, so for example, look at this particular quantity. This is probability multiplied with the post-selected feature information, no? So whenever you have probability multiplied by this post-selected feature information, it is bounded again by the one what we have found for non-selected case, essentially. But you see, I have multiplied here with the probability. If you look at, let me go back. The efficiency is this, no? You got the point?
Yes.
So obviously, if you ignore this probability here and only look at this post-selected Fisher information, obviously it blows up, no, as the probability goes to 0. So that is what they indicated in this Nature Communication paper, as if like you really can get precision with arbitrary precision, obviously, and which, although it occurs very rarely, that means the probability of happening such a precision is very low, but still this Fisher information goes much beyond this delta S square, no? If you just look at
even in that place, sometimes the efficiency would go up to the square, delta A square over 2, for instance, right?
See,
in the paper, not in your results.
Yes. So what we have shown is that this is whatever they had is based on some example only. It's not a general result, but this is like the general one. Yeah.
This is great. Just a quick other. In your Wigner equality,
yes,
is this Wigner term necessarily positive? So are you relating some sort of non-classicality, or actually classicality in terms of, well, whenever the KD is related to the Wigner and the Wigner is positive, so this Wigner term, then you get positivity of the KD?
No. See, this particular term is always positive. Okay.
Yes.
And there may be some situation where the KD distribution is also positive, but that does not mean it is classical.
Perfect. No, I see. No, this is great. So whenever it's equal to the Wigner formula, not necessarily positive, then you have a necessary condition, right?
Yes.
This is great. Thank you so much.
Thank you so much.
Great work. Congratulations.
Thank you.
Okay. Any other question? Let me see the chat box. Oh, I don't see here. Okay, so Manav, so
there
your
is one
example
question.
shows. Can I ask some question?
Yes, please go ahead.
Okay, so if so, your example that you have considered, so it basically tells you that using this this distribution, Kirkwood-Dirac distribution, the way you define its non-classicality. Actually, in this particular example, that non-classicality doesn't help in achieving the maximum value, right?
Can you repeat? Actually,
so the example that you have considered,
correct,
right? So there, the I mean, the distribution in the table that you have shown,
yes,
there is nothing negative or complex, right?
Correct.
So therefore, it is so this. If you say that this is basically classical according to the definition, and same is the case with Wigner, right?
Correct. So that is what we wanted to say, that when you have positive Dirac-Kirkwood distribution, it does not mean it is classical.
Right.
So that is why we came up with this, let's say, definition here at the end.
Yeah, that is true. So, this is true even also for the Wigner distribution. These.
Correct. Actually, they have some connection.
Have Gaussian Wigner distribution, which are non-classical, right?
Correct.
Okay.
Correct. They are actually interrelated in some way or the other.
Okay. So that is fine. Now, my question is that rather than going through this way of connecting non-classicality and the metrological efficiency, what about going through, let's say, some kind of coherence, so that you have some coherence in the state, because that is also, some kind of non-classical feature, right?
It's a very good question. It's a very good question, and actually we are working on it. And what I can say is that obviously, these probability distributions are defined in a very particular way. So many cases, whenever you try to come up with how it may represent the presence of coherence somewhere, It not necessarily comes in a straightforward way. Okay, so there it becomes a function of these probabilities and so on and so forth. So it is not obvious how we can use here in the context of Fisher information. That is not yet clear. I think one has to work on it, and we have some work going on in this direction. Yeah.
Okay.
Yeah.
Okay, good. So if there is no more question, so let us thank Manav once again for a nice talk. So you can unshare your.
Thank you so much.
Okay. So our next speaker is Professor Anil Shaji from ISA Trivandrum. So Anil is has been there in this field for a long time. So I think he may not be the last student of Professor ECG Sudarshan, but maybe somewhat almost last. So anyway, so Anil has been in the field for a long time. Everybody knows him. I don't have to introduce him much, but anyway, so Anil did his PhD, as I said, from University of Texas, Austin, on open quantum system and quantum information. And thereafter, he was a postdoc in the group of Professor Carlton Caves in University of New Mexico. So he joined this physics department of ISA Trivandrum right from the beginning. So today he is going to talk about can a mixed quantum state computer, mixed state quantum computer, use computational resources of its environment also. Here is Anil.
Thank you, Shivashish. I hope you can hear me and see the screen. Let me thank the organizers also for inviting me to give a talk in this wonderful conference. And also special thanks to them for accommodating my last minute request to shift the schedule a little bit so that swap my talk with Manav's one because I got called up for something I couldn't avoid. Thank you for that also. So I've given a bit of a provocative title to my talk, which says that can a mixed state quantum computer use the computational resources of its environment also. So you'll see why I have given this title as we go along. I hope I'll try to keep it quite simple and try to communicate the main idea without going into too much detail. So a lot of what I'm going to talk about depends on or is about this notion of delocalized information in quantum information theory. So I'd rather so it's not probably standard terminology, but so I would like to make clear first what I mean by that. That's just a simple idea that when you bring in this Landau's idea that information is physical or information requires physical entities for it to exist or to be represented on. Quantum information is different from classical information in the sense that we all know that it can lie across multiple physical systems rather than on one of them. If you have a scenario in which you have multiple physical systems that you're using to manipulate and store and do other things with information in a sense. So we all know this. If you go to physical systems, to qubits specifically, we can have entangled states of them, in particular maximally entangled states, in which case the reduced density matrices of each subsystem is maximally mixed. And you would say that by looking at the subsystems themselves, you are not able to, your ignorance about the overall system remains just as before. It is not reduced. You are completely ignorant about the overall, the nature and state of the overall system if you look at any of the two subsystems or even both of them independently. But on the other hand, if you're allowed to look at both of them together, you can have perfect knowledge of the system. Your entropy about the system can go to zero because you recognize it's in a pure entangled state. Right. So that's just for making sure that we're on the same page when I talk about use the phrase delocalized information, nothing more than that. I'm sure you all are quite familiar with this. So now let us let me set the stage for the ensuing discussion and talk about a model of a rather old now, almost 2 decades or more before. Neil and Laflamme came up with this interesting model for discussing mixed state quantum computation, which is called the DQC1 model of quantum computation. Right. What it does is that it does a task which is to essentially compute the normalized trace of this unitary shown here in this box by essentially doing measurement on a single qubit which has any measurable purity, while the unitary itself acts on a state that is completely mixed. Right. So this is a state really that contains no information, or your ignorance about it is complete because it's a completely mixed state. Its entropy is maximal, and since it's a fully mixed state, it's proportional to the identity. The action of the unitary matrix on this is really trivial. Right? It doesn't do anything to it because it's a fully mixed state. But still, this little connection between this single qubit here, which is pure, which is shown by this line on top, and this conditional nature of this unitary being done, it turns out that you can find something about this unitary by doing measurements on the single pure qubit. And specifically, you can find these two quantities, the real and imaginary parts of the trace of this unitary, by doing sigma x and sigma y measurements on this top qubit. The point is that the evaluation of sigma x and sigma y, the accuracy with which you get this result, is really independent of the number of qubits or the size of U of n. So remember that U of n is a unitary that is of size 2 to the power n by 2 to the power n. Therefore, if you were to evaluate its trace by simply counting and looking at simply adding up its diagonal elements, which is how you would normally do the trace, it is a job that requires an exponential resources when you count the total number of qubits that are involved in the circuit. So it goes as exponential in n because U of n is of the soft size 2 to the n. But in this case, with the help of one pure qubit, Neil and Laflamme showed that you can estimate the trace to any accuracy you want. And as long as that accuracy is fixed, the number of trials you have to do in order to estimate sigma x and sigma y is fixed by that and not by the size n of the unitary. Till date, there is no efficient algorithm for doing classical algorithm for doing this particular job. So then the question comes, you got this overwhelmingly mixed state, which doesn't seem to have much quantum features going for it. And you got this one little tiny qubit, which is, of course, has some purity, some coherence, if you will, that is there. And you're still able to do a task exponentially faster than any known classical algorithm. So where does this particular device or this setup derive its computational power from? That's a question that automatically pops up, right? So of course, quantum computation, we know that quantum computers can do certain problems exponentially faster than any known classical algorithms. And what makes investigation of quantum computers interesting, other than the fact that they can do many problems exponentially faster, is the tracing down the resources that enable this exponential speed up. And if you really think about it, what is really known about the resources can be hasn't moved much further than the 2003 result by Josiah and Linton, which showed that for a quantum computer or an algorithm operating on pure states, multipartite entanglement that spreads unboundedly with the size, input size, or multipartite entanglement in our case across all the n qubits in our quantum computer is necessary if the algorithm is to offer exponential speed up. And that proof was done constructively by showing that if entanglement did not spread, you can find an efficient classical simulation of the quantum computer. So your quantum computer is no better than a classical computer. And in that paper, they also very clearly state that these results do not apply to quantum algorithm operating on mixed states. And it really, there is not no clear answer as to what makes a DQC1 kind of circuit. There are not many of them known. There are a few. where mixed states are sufficient, what makes it work, right? So why is it? So they say here that mixed state quantum computers can perform exponentially faster, even in the absence of entanglement. Right? So so in the DQC1 circuit, definitely you cannot find much entanglement, and more importantly, the natural division of the circuit into two halves, the little qubit that finally gives you the trace that you're looking for, and the remaining qubits, which doesn't seem to have much role except just stand around here. In this division, if you compute before or after the conditional unitary, you'll find that there is no entanglement. You can write down as a separable form for the state, separable between the top qubit and the rest. So by definition, there is no entanglement. Now, you can find some entanglement if you divide the circuit into two like this. You can find some bipartite entanglement in this scenario. But then again, you can actually kill that off also by essentially saying that the top qubit is not fully pure, but it is mostly mixed. And you'll find that when you make it sufficiently mixed, even across these divisions, there is no detectable bipartite entanglement, although the associated questions about how do you measure entanglement for n qubits, what is how do you compute it for mixed states, all these questions come into play, but that's a different story which I'm not going into. But let's just take it on faith that even if it's there, it's kind of tiny and very hard to find. Okay. But then in the DQC1 model, there is one other place where you can think maybe obviously there has to be some kind of entanglement. And that's the following argument. The argument is that you are inputting into this n qubit register a fully mixed quantum state of n qubits. And if you're considering a single trial of the DQC1 circuit, there is only a single fully mixed state that is going in, which also means that there is no way that you can actually imagine that the mixed state is really the state of an ensemble of inputs into the bottom register in the DQC1, because there is actually only one trial you're considering. There's only one mixed state going in. So in that sense, you've got a fully mixed state of n qubits. So what does that mean? Where did it come from? Of course, this idea that we talked about before of delocalized information and partial traces of fully entangled states becoming fully mixed, that tells you one possibility, which is to say that really the n qubits that you are sending in is really a part of a larger system that has, say, n more qubits in it. And these these blue dots represent those n more qubits. And this little red lines tells you that there has been some unitaries that has been done between these red dots and blue dots and between each other and so on, which somehow has created some gigantic entangled state of these blue and red black qubits together, such that the subsystem consisting of only the black qubits is in a fully mixed state. Of course, this is something that's quite familiar to everybody. This is what is often referred to as going to the church of the larger Hilbert space, nothing new there. Let's actually create that entangled state, the fully mixed state of the n qubits in the bottom register in this manner. Let's consider eigenstates of the unitary that is acting on the fully mixed state of n qubits. Let those eigenstates be labeled by uj. So the unitary u acting on uj will give you some phase e raised by theta j times uj. Since the completely mixed state, I should probably normalize it, identity divided by 2 to the power n, but all the same, since the state is completely sort of isotropic, you can write multiple alternate forms for it. And since uj form a possible basis for your Hilbert space of n qubits, you can write it as a equal mixture of all the uj's so they provide a resolution of the identity. Now you can expand into the blue qubit space by considering uj to be uj. And then you can take the trace with respect to the extended system, which I call E, and you'll get back your fully mixed state. Okay. And so in specifically, psi of RE is this. And you can say that as a result of the conditional unitary, the overall transformation happening to this new system, this expanded system, can be written in this way, wherein the conditional unitary in the end ends up entangling your top qubit with not only the bottom n qubits, but also with the remaining n, which is for which it is a part of. Okay. Indeed, by tracing out the extended system starting from this state, we will get back a state like this, in which we are now associating this theta j by the usual process of phase kickback with the top qubit. Okay, so instead of attaching it to the uj part, I'm just attaching it to the one which I'm allowed to do. If you remember, this was one of the discussions that was there in earlier talks by, say, Professor Vedral and others, which talked about the locality of the phase being picked up and how you can move it around to the other system, but still, even though the phase pickup is happening in the n qubits in the bottom register, you can move it around that way effectively. And there were quite a few interesting talks in that line earlier. But whatever, once you do that, and when you trace out that extra qubits that you added, you get a state like this, which by construction is separable. Therefore, it has no entanglement between this division of the top qubit and the remaining ones. And the point is that these theta j's, which are now the states associated with various uj's of the bottom half, are given by these guys. So what you get are essentially non-orthogonal states of the top qubit gets correlated in some fashion with orthogonal states of the bottom register. Okay, so this is a standard, straightforward thing. And I just, as an aside, as I had mentioned before, you don't require a fully pure qubit state for the top qubit. You can actually make it also mixed with a little bit of purity. So unless alpha goes to 0, there is a little bit of purity. And you can show that you can still do this, except that your computational overhead will grow as 1 over alpha square. But alpha square, since it doesn't decrease or increase with n, it has no independence. It's just another constant overhead. So there is no scaling issue in terms of the efficiency. And again, the top qubit always remains separable from the bottom one, as we have seen before. Okay, so this is this prompted some of us long time back. This idea that non-orthogonal states of the top qubits are associated with orthogonal states of the bottom one, it led us to the idea that we should be probably looking at something other than entanglement as a resource in a possible resource in these kind of computational scenarios. And it came from the realization, as pointed out by Oliver and Zurek and Ednison and Vedral and others, that quantum states can be correlated in ways that equivalent classical systems cannot be. For example, I have 4 non-orthogonal states of the first qubit correlated with 4 non-orthogonal states of a second qubit in this 2-qubit state, which is by construction separable, right? And these kind of correlations, and these people suggested one measure for measuring these kind of correlation. It's quite well known now, quantum discord and its various families of derivative of allied measures for measuring non-classical correlations other than discord. So, but as an accident back in the day, almost a decade and a half back now, I, along with Dr. Animesh Datta and Carl Caves and others, we just computed the discord across the top and bottom, top qubit and the rest in the DQC1 model, and we found that that seems to characterize the effectiveness of the DQC1 quantum computer, the mixed state quantum computer, much more better than going after entanglement. So the discord as a function of alpha, which is that little bit of purity that we put in the top qubit, behaves something like this. Okay, so this we were able to compute, and we could compare it with what happens to, for example, detectable entanglement in terms of some kind of partial transpose type criteria, which abruptly vanishes when the purity of the top qubit goes below a certain level. So I guess the argument there was that even if the purity of the top qubit does go below, in this case, say 0.5, you know that with a constant overhead, you can still make the circuit work exponentially faster than any classical algorithm. Therefore, trying to explain the effectiveness of the circuit in terms of this entanglement may not be the right thing to do. And something like the non-classical correlations could be the proper resource to consider for explaining it. But there was still no real clinching proof or argument that tells you that Discord or any of its cousins would quantify the effectiveness of the circuit. It's just a suggestion that it could be. And this had snowballed into a lot of discussion in the literature. This is the old story, nothing new here. And there were some interesting results that came slowly but trickling down. Things like that says that, okay, suppose you have a quantum computation in which at every stage of the computer, after every gate, all the qubits in the circuit are in what is called a concordant state, in the sense that there is no quantum discord across any division of the n qubits. Then Easton and Cable and others showed that they can be simulated efficiently. So that's again circumstantial evidence that tells you that, okay, suppose it is not concordant, maybe it cannot be simulated efficiently on classical computers. Therefore, this not concordant scenario may be or this presence of quantum discord may be suggestive of as a resource for quantum computing. And there were counter questions also. So about what if the unitary in the bottom does not produce a quantum discord? Can it be simulated classically? And there is quite a general answer to that is not yet available. So this prompted, after thinking about it a little bit, and also with the picture in mind that yes, this mixed state is actually part of a larger quantum pure state, can we think of it slightly differently, sort of discuss the problem in a reverse direction to say that maybe discord is not, or non-classical correlations are not really the resource per se, but they are indicative or signaling or symptomatic of a larger resource, which is a more conventional one, which is the entanglement in the larger quantum state of which your mixed state is part of. Is it indicative of presence of entanglement in that larger system of a type that is useful for doing certain kinds of computation? And is that the real resource behind mixed state quantum computation? Can we actually address this question or even formulate this question in some manner? Because right now it's quite nebulous. What do you mean by using the entanglement of the rest of the universe, which is actually connected to your mixed state, which you are using in your single copy of the mixed state that you are using in your quantum computer, mixed state quantum computer. So I guess so we watered down that question to the question: is there a connection between global entanglement and discord of subsystems? So let's just ask that question first, rather than thinking about this much more involved question about how it plays into computation and so on, and specifically in explaining the effectiveness of mixed state quantum computation in certain scenarios. But this investigation led us to some very interesting directions and suggestions, which I wanted to talk to you about. So in a sense, what we are trying to ask is the discord in a multipartite mixed state a reflection of the entanglement that the mixer subsystem has with the rest of the universe, right? So as I said, rather than being a resource, does it just signal the ability of the mixed state to utilize the global entanglement under the correct scenarios when you do the correct set of gates and algorithms and steps to utilize or sort of pull in the computational power, so to say, of this larger pure state into something that gives you a advantage over classical algorithms, because classical information cannot be delocalized in this manner. Therefore, you cannot expect a classical computer to do something analogous in that scenario. So what we did as a very simple thing to start off with was to consider several multi-qubit systems in which truly global multipartite entanglement is present. And we computed sort of the average or maximal discord in some 2-qubit or 3-qubit subsystem among them. Okay, so so we started off quite naively and simple-mindedly. But before we could do that, we needed to have a measure of the global multipartite entanglement. So notice that we are really concerning ourselves right now only with genuine multipartite entanglement. So if you have got a so we divide our, or we to fix the terminology, when we say that we have, when I say global state, I'm saying that there is some purification of some mixed state that I'm interested in. So this entire set of all the this entire purification, that is the global state. And again, I am considering only states of qubits, so I'm not allowing the global states to be made of higher dimensional quantum systems, but I'm always restricting myself to collection of qubits. So there's a collection of n qubits which I call the global state, and out of that there are 1 or 2 qubits which I am interested in, which I call the subsystem state, which hypothetically or you can imagine are the qubits that actually take part in a mixed state quantum computation. But that's right now secondary. Let's not worry about all that. Let's just ask a question about larger. So global system is n qubits and subsystems maybe 1 or 2 qubit subsystems. So the first problem was to identify a measure of truly multipartite entanglement, not bipartite, not tripartite, but all n entanglement. And there are reasons why we are interested only in that, which I'm not going into, but we can discuss that later, or it's there in the reference I'll give in the end of this work, which I did with 3 very bright students here. Right. So to quantify the multi-qubit genuine multipartite entanglement, we use the generalized geometric measure. Remember that our global state is always pure because you are essentially doing a purification. So by definition, it's always pure. This measure was talked about by Aditi and Ujjwal and others in this reference given at the bottom. The main point is that, well, while it's hard to compute, it gives us a fighting chance of computing it. And it turns out this for pure states, even though the formal definition involves a sort of an overlap with all possible n-party pure states that are not truly n-party entangled and all that, operationally it can be computed in terms of Schmidt coefficients of subsystem states. So even there, you have to find Schmidt coefficients are essentially eigenvalues of subsystem density matrices. But the point is that you have to essentially find all possible subsystems of all possible subsystem dimensions and look at all their density matrices and pick out the largest eigenvalue among all of them. So computationally, again, that looks very complicated because you have to consider all possible sizes of subsystem, all possible combinations of qubits that make up your subsystem, and then maximize, find the largest eigenvalue of the reduced density matrix out of them, and so on. For example, the intuition is that, for example, if n of them is not genuinely multi-party entanglement, but one qubit, for example, is not entangled with the rest of it. Since the overall state is pure, that one qubit also state is pure. So its eigenvalue, eigenvalues are 1 and 0. So the maximum eigenvalue is 1, and therefore this measure will go to 0. So if 1 out of all n qubits stand aside, automatically this will go to 0. Right? So you can see that. But it turns out as we go along that for the cases we are considering, we find that we can end up getting away by computing the reduced density matrix of very small subsystems, because those typically end up having the largest eigenvalues. So this search over all possible subsystems gets considerably reduced. So that's why we kind of use this measure of entanglement. So in simple-minded manner, what we did was that we generated, say, a random pure 5 or 10 qubit states. This I think is for 5 qubit states, and computed and just put a scatter plot of, say, the generalized geometric measure, which is on the x-axis, versus, say, discord D on the y-axis, and we got this blue cloud of dots. Now, for reference, this yellow cloud of dots is the concurrence corresponding to those subsystems. So what we did was we had computed the generalized geometric measure for n qubit state, and then we took 2 qubit subsystems all possible 2-qubit subsystems of the n-qubit states and found the discord in them and took the maximum discord, whichever subsystem had the maximum one, and plotted it here. And that is this blue cloud of dots. For reference, we also plotted the concurrence, the maximum concurrence out of all the possible 2-qubit subsystems. The reason is that discord or animation of non-classical correlations also includes within it the bipartite correlation. But due to monogamy of entanglement, when you're talking about large values of truly multipartite entanglement, you expect that bipartite entanglement to be small. And we wanted to make sure that, however small, what we get as non-classical correlations is not just the entanglement, but something more than that also. And that we can get here. But the disappointing fact here is that there is no pattern, right? There is no real connection between global entanglement and either discord or concurrence. They seem to be just kind of being independent of each other, and you get this blob of states. Instead of finding the maximum out of all possible 2-qubit subsystems of a given n-qubit state and repeating it for a lot of n-qubit states, we also computed the average discord of over all possible 2-qubit subsystems of an n-qubit state, and it also behaved something like this. Nothing. We also, given this data, you can also compare the discord versus concurrence, and it does expected lines because discord subsumes concurrence. So as concurrence goes up, discord has to go up. So there is a pattern there which is to be expected. Right. So looking at random states did not do us much good. But then we remember that there is this paper, very ingenious one by Vaibhav Madhok and Shohini Ghosh and others, which considered the quantum discord in a 2-qubit subsystem of a n-qubit quantum system, which is evolving under the quantum kick-top Hamiltonian. Now, the point there was that what they showed is that the 2-qubit discord goes up whenever the parameter k or kappa here goes above a threshold above which the classical version of the kick-top is chaotic. So this is like a two-step argument. The argument here is that there is no direct measurement of multi-party entanglement here, but it is known that when the classical system is chaotic, then the corresponding quantum state, that the chaos in the classical system is reflected in the corresponding quantum state being highly entangled in a multipartite manner. Therefore, the parameter going above the threshold of chaos is indicative or is symptomatic, or rather, it's indicative of multipartite entanglement, of possibility of multipartite entanglement. And whenever there is chaotic behavior, the quantum discord of 2-qubit subsystems seems to show this jump as given in this paper, in this plot of k, and the chaos sets in somewhere around 3.5 or 4. I think I remember kappa is to be 4 for the system to be completely chaotic. And you see that around that point, the average discord between 2-qubit subsystems goes up significantly. So what we did as preliminary thing is that we looked at, instead of deducing multipartite entanglement out of the value of the chaoticity parameter, we armed with our idea of generalized geometric measure, we computed the generalized geometric measure as a function of number of kicks in the kicked oscillator model and for different values of the chaoticity parameter, okay, and different initial states. And we find that whenever the system is chaotic, the GGM jumps up as shown by this violet curve abruptly and kind of stays there for all kicks. While for whenever it is not chaotic but in some regular regime, the global entanglement goes up and down. So now we looked at, on the right hand side, the average discord in 2-qubit subsystems for the same scenario, and we find that the two kind of follow each other very closely. Whenever GGM is high, Discord is high. Whenever it's low, irrespective of whether you are in the chaotic regime or in the regular non-chaotic regime. And we also compared it with concurrence, which kind of behave opposite. So that 2-qubit concurrence. So bipartite entanglement goes to 0, while multipartite entanglement goes up. That's again expected. But the thing is that the non-classical correlation, in fact, does not follow the concurrence, but follows the global entanglement. So what that suggested to us, at least, is that maybe when you have more structure to your global state, there may be a connection, a much more noticeable connection between the global entanglement and the subsystem discord. So therefore, we went ahead and considered a set of states, a bunch of states, wherein there is an imposed structure. Okay, it is not randomly generated states, but we consider states defined on graphs, which also we know are quite important in the context of, for example, measurement-based quantum computation. They provide the resource for measurement-based quantum computation. So when we started doing that, there is a lot of a little bit of technicality of how to talk about graph states, but there is a very neat thing called projected entangled pair state construction, which you can follow. But the take-home message is that using this for a graph state, you can obtain expressions for the reduced density matrices of 2-qubit and 1-qubit subsystems and so on, which is what we want, because given a global graph state, we want to compute its subsystem states and find its discord, and GGM, it turns out, is typically the eigenvalue, largest eigenvalue of the 1-qubit subsystem. So if we can compute the subsystem the density matrices, reduced density matrices, which was given to us by this PEPS construction, the reference is given there, then you can actually compute what we are trying to do. So we consider, for example, a square lattice. I guess I should mention here the take-home message is that in order to find the reduced density matrix of these 3 red qubits, it turns out we only need to consider those qubits which are connected to it by links of the graph. The other things go away from the picture. So that simplifies our problem. So the red ones are the ones for which you want to find a density matrix. And this is the expression for the elements of the density matrix modulo the unitary links between them, which we have to add later to this. But yeah, so that's just technicality that I don't want to go into. So we consider square lattice and we considered computed the GGM of the lattice, which is given by this dashed line, and it behaves like this. And we are computing it as a function of theta, which is the angle that defines the unitary link between each of the nodes of the graph. So every line here is represented by this unitary u theta, which is parameterized by a single angle theta. As a function of theta, we find that the GGM behaves like this. So for most values of theta, the global entanglement is high in this graph state. Now for these various cases in which the 2 qubits that we are interested in are connected directly or indirectly through 2 links or indirectly through a single link, cases A, B, and C, we computed the quantum discord, and that's given by these 3 solid lines. And we see that they are also non-zero, except that around theta equal to pi, they go to 0, which is significant. We also computed the concurrence, for example, which is this dotted line. We see that much before the discord goes to 0, whenever GGM rises to a certain level, global entanglement rises to a certain level, the concurrence, the entanglement, bipartite entanglement between these 2 red qubits, whichever those 2 are, they go to 0. So really, the only correlation between the red qubits are non-classical in nature, and they are not entanglement. It is not entanglement. We did the same thing for other kind of lattices which are known to be resource states for measurement-based quantum computation. And we always find the same result, that the discord is actually finite over the entire range except around theta equal to pi. You can zoom in on this area and you'll find that this curve doesn't touch 0 except at theta equal to pi. This got us thinking what is important about pi. And we considered these more complicated clusters in which or graphs in which all qubits are connected to each other. And we consider 5, 10, 20, etc. And the discord started behaving like this, in which it is maximum for all values. And it's easy to show that for these kind of clusters, the GGM is always maximal, except at theta equal to 0 and 2 pi, sorry. But discord is also maximal for large clusters, except at theta equal to pi. Okay. Which was quite surprising, because what happens at theta equal to pi is that this entire graph becomes a stabilized state, because the u theta we used essentially becomes a Clifford operation. So all operations, the initial operation is just the Hadamard gate on all the qubits, followed by this u, which is also Clifford. So at theta equal to pi, the state is a stabilizer state, which actually has a efficient classical description. And precisely at that point, the discord of the subsystems also vanishes to 0. So it's not just, but on the other hand, the overall state is highly entangled, because it's a stabilizer state and it's highly entangled. Its GGM is big. But the instant it allows a classical description, you find that the subsystem discord just vanishes. It just goes away. It's as if it's not sufficient that the global state that we considered has high entanglement for your subsystem discord to be 0. It seems to be as if it's saying that the global state you are considering should be have entanglement that is computationally useful or computationally non-trivial in order for the subsystem to have discord that is non-zero. Right. So we consider fully connected but randomly weighted graphs, so in which the theta is not held constant. Again, we considered a randomly generated such fully connected graph. And now, compared to the first picture that I showed for randomly generated states, when we have the structure of graph states, we find that there is a pattern between GGM and discord. As GGM increases, discord also increases. And there is a imaginary line here beyond with, so for a particular value of global entanglement, the discord doesn't go up too much. And there are some additional structures here which we are not sure. Okay, Shivaji, so I'll wind up in a minute or so, not much, almost done. Now, right, so there are additional structures here which we are not sure of what it is, but this is the behavior here. So what could we conclude? Well, there seems to be a clear connection between non-classical correlations of 2-qubit subsystem of n-qubit pure states when there is additional structure for the global states. And when the global states are graph states, we also see that the subsystem discord is high only when the overall state is not a stabilizer state. So details of this is in this archive paper, which is work done with 3 of my students here, Chandan and Vijay, PhD students. Ardra did her master's here is an earlier, a year back or so, more than a year back, and she's now in Australia. Right. So just to wrap up, I'll just leave you with this picture of a hypothetical mixed state quantum computer. So you got this ring of red states, red qubits, which are connected to all kinds of other qubits in this by these random links. And these links I have colored, given different colors to say that some of them may be stabilizer kind of links, some may be non-stabilizer, and so on. And this is kind of suggestive of the DQC1 model in the sense that you got this ring of qubits whose reduced state is likely mixed because it's entangled with all these other guys. And there's one that's staying apart. So this is sort of your initial state of the quantum computer. Now, as the computation proceeds, you necessarily have to connect these qubits together through 1 and 2 qubit gates and so on. And you get this structure here. Now, the question is, does this, when you have this entire structure and you're only looking at this subsystem, are you in a position to use the computational resources of these remaining qubits in a productive manner, such that even if this subsystem state is completely mixed, you do get computational advantage related to classical state, to classical computation. So with that, thank you for your attention, and I will be happy to address questions if any.
Thank you, Anil, for such a nice talk. So questions now?
I think I see a hand raised by Edwin.
Yes. So I have a basic question with the first circuit that you showed, the DC QI.
DQC1 circuit.
Yes. Can you please go back to that slide?
Okay, let me see. Let me share once more. Right. Yeah.
Okay, so here, so naively, what I think is the entanglement that you should be looking at shouldn't it be like after the conditional tree has been applied and before the measurement, like between the
that's exactly the state. So what I'm saying is that the state after the conditional unitary is actually across this top qubit and the rest. It is, you can actually write down the separable form of that state. So it's not before. It's after the.
Oh, is it? Okay, okay. So it is it is not entangled even after the unitary.
Yeah, even after. And even if you divide it, sorry, I wasn't clear on that. It's all these entanglement measurements are after the conditional unitary. So
okay, okay, yes.
Between the top and bottom, there is no entanglement because you can explicitly write down the separable form. While for other divisions, you can detect in some scenarios, but the instant you start making this top qubit mixed and mixed, you start, it becomes really difficult to find any entanglement in it.
Okay, okay, yeah, thanks.
Okay, any other question?
Yeah, is there any other question?
Anil, can I just ask a small question? This is Shrikant here.
Yeah, sure.
Yeah, the following question. So I can manifestly construct, this in by 2 power n, right? You have the state, right?
Yeah.
So each of these wires, okay, I can entangle each of these wires with just one other qubit.
Yeah,
okay,
sure.
So,
you can do it that way.
So I produce a maximally mixed state, but which is manifestly lacking global entanglement. And clearly, it shouldn't affect the performance of this quantum computer, this one qubit DC qubit. So would that not imply that? Yeah, that was my question. So clearly, it seems like global entanglement. Would that be right? So that is the thought that comes to me, because I can manifestly construct one which lacks global.
Again, Srikant, that is again the initial state. But notice that this UN is going to entangle all of them, right? Okay. Because if UN is actually divided into blocks, of course, you're not going to get anything interesting, right? Okay. That is there. You're saying is that okay, for each input qubit, I have got one other guy, but then all the input qubit you are going to act on with this gigantic unitary, which will couple all of them. Generally. So then again, you're after the conditional unitary, you're again kind of back to where we started.
Oh, okay. Yeah. Thank you.
Okay. Any other question?
Can I ask a short question, please?
Yeah, sure.
I had a question. If we're using the environment as a resource, will there be any entropic like consequences? Can you are they calculatable in terms of we get information, we use an environment in information processing, so there should be maybe some entropy changes and entropy
that is a very good
stuff
question.
with entropy.
Yes, that's a very good question, and I would guess that it should be detectable, because this kind of structure again shows up in a different format. For example, in condensed matter physics, when you talk about area law of entropy and all that, right? Because there also you are kind of counting the links between your subsystem and the one remaining, right? So there must be an entropic consequence. I don't know whether that's what you're implying. That could be
yes.
Sort of deduced, right? Which it's a good question, but that's not something that we have looked at so far.
Thank you very much.
Okay. So if there is no more question, let us thank the speaker once again for the wonderful talk. And so let me thank all the 3 speakers for this session. And we'll end this session now, and our next session will start at 7 p.m. IST. Thank you.
Thank you, Professor Ghosh. We have a small tea break and we'll meet again 7 p.m. Okay, thank you.
Yeah, Professor Spakens.
Yes, hello.
I'm Guru Prasad. I will be chairing this session.
Nice to meet you. I'm going to try to share my screen to see if it works properly. Let's see. Can you see this?
So we are going to start our late evening session and the last session also. So in this session, there are two speakers. First one is Professor Robert Spakens, and second speaker is Mark Wilde. Professor Spakens has been a faculty member at the Perimeter Institute, Canada since November 2008. His research is focused upon identifying the conceptual innovations that distinguish quantum theories from classical theories and investigating their significance for various axiomatization, interpretation, and the implementation of various information theoretic tasks. And in particular, he has been very well known in the community due to his work in extending the ideas of contextuality to preparation procedure and transformation in quantum mechanics. And he has another famous work related to epistemic view of quantum states. These two papers are very key, offers very key concepts, and that's why in the community, these two papers are considered great papers. So with this, I invite Professor Spakens to start his talk.
Okay, well, thanks very much for the introduction. And thanks to our friends in Calcutta and especially the organizers for putting this together. It's I'm sure it's a lot of work, and it's a really great opportunity for people who work at the interface of quantum foundations and quantum information to hear a lot of different talks, even if it's to watch the pre-recorded ones in the daytime. And also thanks for allowing people like me to participate virtually so I can reduce my carbon footprint. So I'm going to talk today not about contextuality, but about causal inference. And so basically this is going to be an introduction or a kind of invitation to this field of research. And I'm not going to go into too many of the technical details. And I'm happy to take questions during the talk. And let me just verify, you can see my slides, yes? Okay, I'm going to assume.
Yes, we can see.
Okay, thanks very much. Okay, so the talk is about the interplay between work in quantum foundations and a field called causal inference. So causal inference is a branch of machine learning. It's interested in the problem of inferring from statistical data what caused what. So, what are the causal relations among a set of variables about which you have a joint probability distribution or a finite sample of that. So this has been studied by people in computer science, statistics, and other fields that are interested in these sorts of problems like epidemiology, economics, things like that. So it's very interdisciplinary. And it turns out it's closely connected to problems in the foundations of quantum mechanics. So in this talk, I'm going to talk a little bit about how the conceptual framework of causal inference has changed, my views of quantum theory and has suggested a number of interesting problems to work on, but also kind of the opposite direction, what people in the field of quantum foundations have done to develop state-of-the-art techniques in causal inference. So I'm going to begin by just giving you a flavor of what causal inference problems look like. So here's a really simple example. Imagine you're interested in determining how effective, devoting certain resources in firefighting to reducing property damage might be. So you collect a bunch of statistical data about different fires, and then you see the surprising pattern wherein the amount of damage done by the fire is positively correlated to the number of fighters that show up on the scene. And so if you naively thought, okay, well, there's going to be a causal influence from the number of firefighters who show up to the amount of damage that's done, you would expect the opposite correlation. And you'd be unwise to imagine that, the lesson of this data is that you should just send fewer firefighters and you'll, reduce property damage. What you should do, of course, is go looking for other explanations of the positive correlation, like a common cause. And so there's an obvious one in this case, which is the size of the fire. So the size of the fire influences both, the amount of damage that's done, but it also determines how many firefighters the dispatcher sends to fight the fire. So it can account for the positive correlation. So the thing that one ought to do in this circumstance, given that this is your hypothesis about what's going on causally, is to stratify the data by fire size. So here I've kind of suggested, that if these would be sets of data corresponding to different sizes of fire, with the smallest fire down here and the largest fire up here. And then you see that as you increase fire size, both the amount of damage done increases and the number of firefighters showing up increases with some variation in each category. And if I look at a particular value of fire size like this one here, then I see a kind of the remaining causal effect of number of firefighters on the amount of damage done. And here it's a negative correlation. So this sort of accords with your intuition that if you send more firefighters, you'll tend to reduce the amount of damage done. So the idea is that ultimately the positive correlation is really just about inference. It's about saying that if I learn how many firefighters show up on the scene, I can infer how much damage was done by virtue of the fact that learning how many firefighters show up teaches me something about the size of the fire, and knowing the size of the fire, I can infer how much damage was likely to have been done. So correlation is really about inference. It's a symmetric relation. It's not inherently a causal relation. So one needs to unscramble those two concepts to solve the problem of inferring cause-effect relations from statistical data. Here's a second example, which will get us a bit closer to the connection to quantum theory. This is an example from economics. So the idea is that one wants to know whether getting a degree from some educational institution is useful for increasing future wages in your career. And so suppose maybe you just care about some threshold wage, and you find that in a certain population, those who got the degree were 79% likely to be above that threshold, whereas those who didn't were only 43% likely to be above that threshold. So then you might say, aha, that looks like, if I assume that the skills you acquired or the certification from the degree is what influences your wages, it looks like that particular educational institution increases your likelihood of these sorts of future wages. But again, you have to ask yourself, you shouldn't jump to that conclusion. You have to ask, are there other ways that these things could become correlated? Could there be a common cause explanation? And sure enough, there can be, such as here, aptitude. So your aptitude might determine whether you got admitted into this institution and whether you completed. And it might also determine, what your future wages were ultimately, because it determines how successful you were in your career. Now, the difference here relative to the example of the firefighters, I'm going to imagine that you have no data on this factor here, the aptitude factor, so it's hidden. So in that circumstance, all you can measure are these two things. You can't stratify by this variable, so you can't determine the actual causal influence in that way. So you have to look for other schemes for assessing that causal influence. And there's a good trick that's used in the causal inference community, which is to go looking for what's called an instrumental variable. So an instrumental variable is going to be something that just influences this. So actually, I jumped the gun a bit. Let me mention just one scheme prior to the instrumental scheme that could always solve these sorts of problems, which is the randomized controlled trial. So there you basically suspend the causal influence that would normally determine this variable you're interested in, and you replace it with something that you're confident is uncorrelated with any factors that might influence this effect you're interested in. So, the standard thing would be a coin flip. So that works in some circumstances like drug trials, where you can give a drug or a placebo depending on the outcome of a coin flip. But it's very rare that you can do that. It sort of compromises on the best outcomes, in the sense that if you have a promising treatment, you would want to give it to everyone. But in most cases, you just can't do it. So here you certainly wouldn't want to determine whether somebody can be admitted to a school or not based on a coin flip. So for this reason, this randomized control trial really has limited effectiveness. And what we would much prefer is a scheme that allows us to make inferences about this causal effect just in the natural experiment that was done, just using observational data where we don't have to intervene. And so that's where the instrumental technique comes in. And the idea is to go looking for something that influences this variable you're interested in addition to whatever hidden factors might influence it. And importantly, which is not itself influenced by those factors. So in this example, you can find such a thing. Perhaps this particular school has admission factors that are not related to aptitude. So if your parents perhaps made a large donation, then that might be sufficient to get admission into that institution. And so now if you see a correlation between admission by those sorts of means and maximum future wages, there's no possibility of explaining it by this common cause because this common cause doesn't influence the admission factor. So it must be in that circumstances that variability in the admission factors here implied variability in whether you got this degree or not, which is what accounted for the variability in whether your maximum wages were above some threshold or not. So you can basically infer that there must be some causal influence here, and you can sort of back out from the degree of correlation that you observe something about the strength of that causal influence. So that's called the instrumental variable scheme. And now I want to go one step further, and I've chosen this example such that there's another possibility for explaining that positive correlation, which is maybe there's a direct effect of this admission factor on maximum wages. So perhaps if your parents are sufficiently wealthy to make a large donation, maybe you were likely to have higher than average wages in your future career, regardless of whether you got that degree. And now if it's a direct influence, you know, that means that perhaps there isn't an influence here. And this is what you're really interested in, how the schooling affects your wages. So in this case, you can make progress by recognizing that this original causal structure we had implies some constraints on the joint distribution over these three observed variables. And those constraints come in the form of inequalities. So inequalities that the joint distribution has to satisfy if it's to be consistent with this hypothesis. Those are called instrumental inequalities. And so if you see a violation of those inequalities, so if you measure this joint distribution and it violates those inequalities, then you can conclude it definitely wasn't this causal structure. And so it must have been something else, for example, the case where I have this arrow. And something about the strength of those inequality violations can teach you something about the strength of this causal relation. And again, you could back out what you're really interested in, which is some estimate of the strength of this causal relation. Okay, so let me give it just a bit of formalism here. So I'm going to abstract things by drawing the causal structure now just as a directed acyclic graph. So there's no cycles. The nodes just going to label by some classical random variables. And the hidden variables, the hidden nodes, are going to be given by Greek letters. And so this is called a causal model. In addition to the causal structure, I need to specify some parameters that determine the dependence of every variable on its parents in the DAG. So y depends on x and lambda, those are its parents. So I need to stipulate the conditional probability distribution of y given lambda and x. X depends on z and lambda, so I specify this conditional. And lambda and z have no parents, so I just can specify distributions for them. So given all this, I can compute the joint distribution over x, y, z for these traces of parameters. And because lambda is not observed, I marginalize over lambda. And that gives me, you know, for every choice of these conditionals, that gives me some joint distribution over x, y, z. And the set of distributions that are compatible with this causal structure are just the set of distributions I get by varying over all possibilities for these conditionals and these distributions here. And in this example, as I vary over all those possibilities, I don't get to the set of all joint distributions on this triple of variables. I only get a subset. So if you're in that subset, yeah, we say that the distribution is compatible with this causal structure. Otherwise, it's not compatible. And you know, an example of a constraint that describes the subset is this inequality here, which was derived by Judea-Pearl in 1993. And this is what I meant by the instrumental inequality. So if you have a joint distribution over X, Y, Z, and you take the conditional on Z and you compute this sum, and you find is greater than 1, you know that this causal structure could not have generated your data. Good. So let's move to the next slide. So here's the overall pattern, that you have some evidence, some input into your algorithm, which could be, in this case, a joint distribution over X, Y, and Z. You have different possible causal hypotheses for what might explain that distribution. And then you note that some of them imply constraints on the distribution, like instrumental inequality. And so if the distribution you've observed violates it, well, then you know it definitely wasn't this causal structure here. It must have been the other hypothesis on your slate of candidates. And so then you can start analyzing what the strength of the causal effect is using the hypothesis and the data. Okay, so the field of causal inference has, well, this is just a set of textbooks from different fields that use it. And recently there's been more and more work in this field. And so it's really becoming something that's used broadly to analyze statistical data. If you're interested in kind of knowing how it all got started and maybe a bit more, I recommend this popular science book here. So it's written by Judea-Pearl, who's one of the founders of the field, and is very accessible. So now let me move on to what the connection with quantum theory is. So the connection is going to be through Bell's theorem, and I'll just remind you briefly the setup. So you've got this pair of particles. You measure it on the left and the right wing. You have some setting variable in both places and outcome variables. Here I'm depicting them as binary outcomes. And if the settings are also binary, then you can imagine, for each pair of setting values, you can just compute in the experiment the relative frequencies of the 4 possible outcomes for the pair of measurements. And quantum theory predicts that you can see this sort of pattern here, where for 0, 0, 0, 1, and 1, 0 settings, you mostly get correlated outcomes. And for the 1 and 1 setting, you mostly get anti-correlated outcomes. And so the question, if you look at Bell's theorem from a causal inference perspective, the question is, what sort of causal structure is consistent with this statistical data? What sort of causal structure can explain it? And so this is the causal structure that Bell considered in his paper, which is that you just have random variables associated to the settings and the outcomes, and some random variable which is common cause of the 2 outcomes. So an outcome on one wing depends on that common cause and depends on its local setting. And that is a very natural assumption, because if I look at the structure of the experiment, it looks very much like this is what's going on. But it turns out that this sort of causal structure has inequality constraints on the joint distributions over the settings and the outcomes, which we call Bell inequalities. And the data I showed you here, which is consistent with quantum theory, violates those Bell inequalities. So you conclude that these are incompatible, and therefore it's definitely not this causal structure that explains this data. So that's just the standard Bell story, but with in a way presented in a way that draws the parallel to what I was saying about the instrumental inequality earlier, which is something studied entirely in a classical context in the field of causal inference. So again, just some of the details. This is the abstract causal structure that Bell is interested in. We specify conditional probability distributions for every variable given its parents. And we compute the joint distribution over the observed variables, these ones in black, by marginalizing over the hidden variable on the product of these guys. Now, typically in quantum physics, we look at the conditional of the outcomes given the settings. So if I just conditionalize on the settings, I don't need to stipulate how they're distributed, and I can just look at this standard form for the conditional. Okay, and then if you ask, well, what are all the constraints that this conditional satisfies if it is to be compatible with this causal structure? Well, first of all, there's what we call the no signaling constraints. So X is independent, statistically independent of T, and it's statistically independent even if I condition on S, and Y is independent of S even if I already know the value of T. So those are here. And there are famously Bell inequalities. So this is the Clauser-Horn-Schmony-Holt inequality, which holds with, these are all binary variables. And I like to write it in this form where it's about the probability of getting correlation for the settings 0, 0, 0, 1, and 1, 0, and anti-correlation for the setting 1, 1. And yeah, the probability of winning this sort of CHSH game is 3/4. So that's the analog of the instrumental inequality. So that's what this data here violates, and that's why we can conclude that this causal structure is not possible. So what the causal inference perspective suggests is that one should go looking for other possible causal explanations. So one that does work is that if you imagine that there's extra influences, for example, from the setting on the left to the outcome on the right, that can explain the correlations you see here. So this data is in fact compatible with distribution, but there are some uncomfortable features of this sort of explanation. So first of all, here's what the model looks like. I've sort of highlighted in blue how it's changed relative to Bell's model. So now the outcome on the right, y, can depend on the setting on the left. So this is what the conditional looks like. I can plug that in. Again, I can ask what are all the constraints on the joint distribution over the outcomes given the settings that follow. And now you only have this one constraint, which is that x should be independent of t, and it should be independent even if I know the value of s. And I've lost the constraint of no signaling in the other direction. And I've also lost the Bell inequalities that in this sort of structure, you can violate the Bell inequalities up to their logical maximum. So you can do justice to the data that was seen, but it's uncomfortable because the data you collect also satisfies this no signaling condition in the Alice to Bob direction. So this identity here, even though that's not implied by the causal structure. And so what that means is that if I vary over these parameters in the causal model, let them take arbitrary values, generally I'll violate this condition. And so to ensure that the data satisfies this condition, I have to choose these parameters very carefully. So there's only a set of measure 0 of all choices of the parameters that ensure this equality. And so in the causal inference community, assuming that your explanation works not just in a set of measure 0 is called the assumption of faithfulness. And it's typically made when people go looking for good causal explanations. From a physicist perspective, it makes sense to call this principle no fine-tuning, that if you have to choose these parameters from a set of measure 0, your explanation seems fine-tuned. So that's one uncomfortable feature of this sort of explanation, is that it requires this sort of fine-tuning. So you can take a look at this paper of mine for that argument. The common reason people reject this causal explanation is more basic, which is that we can do the Bell experiment in a way that the two wings are space-like separated, or more precisely, the outcome, the registration of the outcome on one wing is space-like separated from the process that determines the setting on the other wing. And therefore, if there is a causal influence that establishes, that goes across the labs, like this one here, then it has to propagate faster than the speed of light. So it has to be a superluminal influence. And so it doesn't necessarily have to lead to superluminal signaling. It can, again, if I choose these parameters carefully, I can sort of wash out this influence so that it doesn't allow for signals to be sent. The distribution of y could still be independent of the setting S. And so there's possibility for saying, well, it's not in tension with relativity, if you think relativity is only about signals. But many people think that relativity prohibits not only superluminal signaling, but superluminal causal influences. And if you think that, then there's a real tension between quantum theory and relativity for this sort of causal explanation. So for both those reasons and others, this seems to be a pretty implausible causal explanation of the statistical data we see. And so you can go looking for others. And there are other causal structures that allow you to explain this data. So I won't go into the details, but there's something called superdeterminism, where you imagine that there might be a common cause of the setting value and the hidden variables. People have studied retrocausation, where there's causal influence from the outcomes back to the hidden variables. But it turns out that for all those explanations, you can show that they have the same fine-tuning problem I mentioned, that they all, if you allowed them to have generic parameters, would allow for signaling in one or both directions in the causal, would allow for violations of no signaling in the causal structure. And therefore, to make sure that you don't see in the experiment those violations, you have to fine tune the parameters of those models. Okay, so here's where the sort of new idea comes in, which is inspired by this field of causal inference, that maybe what we really need to do here is just break free of the framework of classical causal models. That maybe all we need is an intrinsically quantum notion of a causal model. So the idea, and I'm not going to go into too many details, but the idea is that rather than having a latent variable, just a random variable that acts as the common cause of the outcomes, you have something more exotic, which I'll call a quantum common cause here. And you know, this is the kind of thing that we're going to imagine, that the causal structure now is very conservative. It's just the thing that Bell thought was going on, the thing that the structure of the experiment suggests. But the way I model causal dependencies and what I can infer about one variable given other variables, that's no longer given by formalism classical probability theory. That gets innovated. And so it uses the formalism of Hilbert spaces. And one way to write it down to make it look a lot like the formalism of classical probability theory is using what we call conditional density operators. So here, instead of a probability distribution over a latent variable, you have a density operator on a pair of systems A and B. And here I have a conditional density operator X given A and S. And that's basically just playing the role of the positive operator valued measure that would determine the outcomes of a measurement on A. Or equivalently, the completely positive map that takes S and A to X. It's just essentially isomorphic to that object. But if I write it as this conditional density operator, then I can write the formula for the conditional probability of X and Y given S and T in this form that's reminiscent of the classical one, where instead of marginalizing over lambda, I'm tracing over A and B. And I'm just, again, taking the product of these conditional density operators. So I'm not going to say too much about this formalism and what it means to update classical probability theory into these sorts of conditional density operators. You can read more about it in this paper. But the idea is that this is, you know, one way of thinking about how a causal model can go intrinsically quantum. And it's been devised in such a way that for this experiment, at least, it just reproduces what operational quantum theory would tell you is going on. And so in particular, because of the causal structure, you still have these no signaling conditions in both directions holding. And furthermore, you can saturate what's called, you know, the Tserosen bound, which is this 85% roughly value. You know, the left-hand side here is just the left-hand side of the CHSH inequality, but I can go beyond 3/4 all the way up to 85%. So this causal model can do justice to the quantum violations of the Bell inequality. So it's compatible with what we see. I argue that it's the right causal explanation, or something like it is the right way of explaining the statistical data that we see. Now, I want to just mention that this is not, I'm not saying that this is a finished story, that we fully understand what quantum generalization of causal models are. If you're interested, there's been a lot of recent work on, you know, exactly how do you take any given concept in classical causal modeling and make it quantum. There's some disagreements about certain things. But in some recent work I've done with David Schmidt and John Selby, we realized that there's still a lot more work to be done, that even this sort of framework I've just told you about fails to unscramble this omelet of causal notions and inferential notions completely. So there's sort of some more unscrambling that needs to be done. And so we need a better framework if we really want to be clear about, you know, what are causal relations and what are just statistical correlations. So the bottom line for this Bell type experiment is, you know, here I've just drawn the Bell structure, and now I haven't labeled the nodes because I want you to imagine that these might not be settings and outcomes of a Bell experiment. They could be variables in economics or medicine. And, you know, this could be some causal hypothesis you have about what's going on in that system where there's some hidden common cause. And so we know that whatever those variables are, you know, this causal structure implies constraints on the joint distribution over the 4 observed variables. And if you violate those constraints, so the constraints of the Bell inequalities, if you violate those constraints, you know that it definitely wasn't this causal structure with its classical common cause. And now the point is that these two communities, the classical causal inference community and the quantum foundations community, use this one and the same tool for two different purposes. So in the quantum community, you say, well, if I trust that the causal structure I drew here is correct, it does describe my experiment. For example, if I did it at space-like separation, then the violation of Bell inequalities can witness quantumness. It can tell me that the common cause, must be described quantumly. It must have some entanglement, for example. It can't just be modeled. What we normally say is it can't just be modeled by a locally causal hidden variable model, or in other words, one of these classical causal models. But somebody in the causal inference community who's confident that there's absolutely nothing quantum in their experiment going on, because these are just variables having to do with economics or something, has a different conclusion. They say, oh, well, this causal structure I drew was just a hypothesis about what's going on. And the fact that I violated the Bell inequalities tells me that that hypothesis was wrong and it must be something else, like this causal structure here with the arrow going across. So it's the same set of inequalities can be used by both communities, but with different conclusions. And in one, you're witnessing quantumness for that causal structure, and the other, you're witnessing that your hypothesis was wrong. And so if I go back to the instrumental structure that I mentioned at the beginning of the talk, it's the same pattern that, if you violate the instrumental inequalities, it wasn't this. Classically, you can infer that there must be a causal influence from this variable to that variable. But if you're a quantum physicist and you devise an experiment and you're confident that it does have this causal structure, then you draw a different conclusion. You say, I've witnessed that the common cause has gone quantum. And indeed, there are correlations between these three observed variables that you can get when the common cause here is quantum that you cannot get in this case. So it's been confirmed that there are some inequalities for this instrumental structure that can be violated quantumly. So that was shown in these two papers. And so in particular, that means you can do an experiment to try to violate those inequalities. It has a different structure from the Bell experiment. So you can read about this in this night's Nature of Physics paper, where the theoretical lead was Rafael Chavez, and it was done in the lab of Fabio Schirino in Rome. And now let me mention a third, another causal structure that hasn't showed up in the talk so far, but this is one that's been studied a lot. It's called the triangle causal structure. So it has a classical common cause between every pair of the observed variables, but no three-way common cause. So again, there you can find some constraints on the joint distributions of the three variables, and if you violate those, then it's not this one. But you can conclude from that either that one or more of the nodes has gone quantum. So there's certain inequalities that only guarantee quantumness of one of the nodes. So if you violate those, you'll infer that some node is quantum, or you might just infer that the causal structure that you thought held is wrong, and there's some extra error. So this causal structure is already kind of general enough to give you any distribution over these three variables here. So again, same tool, witnessing two things, and so in this case, the proof that there are quantum correlations, in this kind of causal structure here, which can't be explained in the classical causal structure of the same form, was given by Tobias Fritz in 2012, and recently we've sort of taken the idea behind Fritz's proof, and his proof is really just a sort of idealized set of correlations that involve some sort of perfect correlation between certain variables. That does exist in quantum theory, can't be explained here. Ideally, you want to turn that into inequality constraints so that you can move away from those perfect correlations, add some noise, and still have a proof of quantumness. So some such inequalities are derived in this paper, a large collaboration of which I was a part. But there's more to be done in this sphere of figuring out exactly how to get the most noise robust inequalities so that you can experimentally witness quantumness in this sort of causal structure. Another interesting development recently is that it's been shown in this nice paper that there are certain correlations in quantum theory that demonstrate that you need all three of these common causes to go quantum in order to explain them. But unfortunately, we haven't, or it hasn't been determined yet how to make that sort of proof noise robust, how to find inequalities that if you violate them can witness the quantumness of all the latent nodes here. So it turns out that, we've been talking about this instrumental scenario, bell, triangle, but there's lots and lots of other causal structures that are potentially interesting. And in fact, just last week, I was working on the question of, which causal structures do admit of quantum classical gaps. And so all of these ones I've drawn on the slide and many others, we now know have quantum classical gaps. So if I take these latent nodes and I make one or more of them quantum, I can get correlations that I couldn't get if those nodes were classical. And it's starting to look like perhaps in the space of all kind of equivalence classes of DAGs, ones that generate the same set of a class gives a certain set of compatible distributions with it. So there's a number of different classes. It's looking like perhaps the existence of these quantum classical gaps is generic. It's not rare, but it's actually the norm. But that's still unclear at this stage. So what you really want is a general purpose technique, not just so that, when you have an arbitrary DAG, you find ways of deriving inequalities for it that are inequalities that are satisfied if you have the classical latent variables, but that can be violated if you have quantum latent variables. And so a few years ago, Ellie Wolf, Tobias Fritz, and I devised what we call the inflation technique for causal inference, which is an algorithm for computing these inequality constraints on DAGs with latent variables that you can then apply it to any causal structure you like and get some noise robust inequalities out of it. So in the example of the triangle causal structure where the observed variables are A, B, and C, this is the standard story about what the parameters are and what the joint distribution that comes out of those parameters are. And an example of a sort of inequality that we can derive from the inflation technique is this one here. It's clearly a polynomial inequality in certain marginals of the joint distribution. And I won't go into great detail about the inflation technique, but the basic idea is that you can find causal structures that are different from the one you're interested in, that are kind of bigger, inflated. They have multiple copies of one or more of the variables that appear in the original structure. But the ancestry of a given variable is kind of reproduced in the inflated DAG. And therefore, certain marginals of the observed variables are the same in the original DAG and the inflated DAG. The inflated DAG is assumed to have the same parameters. It determines how a variable depends on its parents in exactly the same way as the original causal structure. And so there's the marginals in these two DAGs are the same. And it turns out that the bigger inflated DAGs tend to have more opportunities for deriving inequality constraints on them. And then you can just pull those constraints back to the original DAG. So that's the idea. You can read about it in the paper on inflation. And then some follow-up work by Ellie Wolf and Miguel Vasquez showed that actually you can use this technique to define a convergent hierarchy of tests and basically determine whether a given distribution is compatible with a DAG or not. So it may not be feasible to do that computationally, but at least it's an algorithm that in principle can solve the problem of compatibility for any given DAG. Some more recent developments are just like for the CHSH, we have the Tsearelson bound, which tells us how much can I violate this inequality if I allow the latent variable to go quantum. I can't violate it up to its logical maximum. There's also a question for these inequalities that we're talking about. For these novel causal structures, can we also figure out the inequalities that bound what can be achieved in quantum theory? And so there's a quantum inflation technique by Ellie Wolf and these people, which gives you a means for doing that, for driving those inequalities. And then very recently, it was proven that you also have a convergent hierarchy of tests using this quantum inflation technique. So what are the applications of this sort of stuff to quantum information? Well, if we have a quantum network, we're doing quantum communication, quantum cryptography, then a particular setup wherein certain nodes share arbitrary amounts of entanglement and there's classical channels among them can correspond to a particularly directed acyclic graph. So if you have ways of determining whether the resources of shared correlations in a given graph are sufficient to violate some inequality that's defined by those sources being classical, then you can witness quantum. So you can use these sorts of techniques to sort of understand what quantum resources you have in a given network structure, and possibly to sort of build information processing protocols for particular network structures. But also in quantum computing, you can think of a circuit as stipulating a particular causal connection among systems. It's sort of like a multiple time steps sort of causal connection, but ultimately it's just a causal structure. And so again, if you want to know, for example, whether a particular quantum computing architecture is doing something genuinely quantum, you can try to look at the causal structure of the circuit, find constraints that follow from assuming that everything is classical, and then if you violate those constraints, you'll have witnessed quantumness in that structure. Okay, so I've mostly been talking about how tools and concepts from the field of causal inference can impact problems in the field of quantum foundations. And now I want to say a little bit about sort of the other direction. So what can quantum foundations do for the field of causal inference? And here the key is that it might not have come out in my introduction, but most of the work in the field of causal inference does not involve hidden variables. Most of it concerns directed acyclic graphs where all the variables are observed. And the instrumental inequality is kind of an exception in that sense, that it's sort of one case where there's some strong results concerning hidden variables. But generically, this is not a well-studied problem in the causal inference community. But in the quantum foundations community, we've been thinking for 60 years about Bell's theorem. And so our comparative advantage in causal inference is these invariable problems. And there's so many different ideas about Bell's theorem that it's very easy to take those ideas and sort of port them to these new causal structures and ask, what can I say about, deriving Bell type inequalities in these new types of causal structures. And so, for example, the inflation technique that I told you about earlier was, really came out of thinking about Hardy paradox type approaches to non-locality and generalizing those sorts of ideas to arbitrary causal structures. Furthermore, if you look at sort of the literature on causal inference in DAGs with hidden variables, there's a lot of nice stuff coming out of groups that are basically quantum physicists. So there's this is just a very partial list of some nice results on classical, that are, in my opinion, best understood as results about classical causal inference. So anytime you derive Bell type inequalities, you're just really contributing to the field of causal inference. And many of these are being published in Journal of Causal Inference and other journals that the causal inference community publishes in. So ultimately, quantum physicists, I would say, are now contributing to state-of-the-art techniques in these sorts of causal inference problems. Okay, so I think I have just a few minutes left, and I was going to end with just a description of an experiment that we did in Waterloo recently. So this is a collaboration with it's done in the quantum optics lab of Kevin Resch at the University of Waterloo, and Patrick Daly was the student who did the experiment. And the idea is to try to experimentally decide or adjudicate between different accounts, causal explanations of Bell inequality violations. So you'll remember earlier in the talk, I mentioned that this sort of causal structure here with the classical latent node and the cause-effect influence across is compatible with this data. It's a possible causal explanation. And I tried to argue that it was implausible because of fine-tuning and its tension with relativity. But I want you to imagine that maybe you don't buy that story. So maybe you say, well, I'm not convinced that this is the right causal explanation, and maybe this one is actually the correct one, because perhaps there's a story that could say that fine-tuning is not such a big problem, or that relativity is really about signaling and not about influences. So what I want to consider is, can we try to decide between these two causal explanations, not based on theoretical principles, but rather just based on how well they can account for actual experimental data. So what is their predictive power? Can we just use standard model selection tools for making a decision between these two types of causal structures? And so let me emphasize that the difference between them is really that, over here on the left, we're imagining a radical causal structure in the sense that it's not what you would expect for the structure of the experiment. On the right, the causal structure is conservative. It's exactly what you would expect. But where the right model, the quantum causal model, goes radical is in this choice of parameters. So we're on the left, we're very conservative in terms of how we describe causal influences and the inferences we can make about them. It's all just classical probability theory. Whereas over here on the right, we have to use this exotic alternative to classical probability theory in terms of these conditional density operators. So the question is really, can we try to get some insight as to sort of where the model goes radical? Like both of these can ultimately do justice to Bell, the statistical data that violates Bell inequalities. And the question is, is one of them better? So the idea is going to be that we're going to look for overfitting. They both can fit the data, but we're going to ask whether one of them overfits the data relative to the other. So let me just remind you of how that works. So there's some basic model selection technique where you train and test. So suppose I just have two variables that obey some linear relationship, and this is the ground truth. So ideally, if I took infinite statistics, I might find points on this line. But in the training data set, I have finite statistics, and I have statistical fluctuations away from that. So the blue points represent what I've actually measured for the values of these two variables. And so then I do the standard thing, which is if I have a linear model of the data, I find the best fit model. And the training error is just the chi-squared. So the sums of the squares of the differences between my data and the best fit linear model to that data. That's the training error. And now if I go to a different kind of model, not a linear model, but a higher order polynomial model, I can get a much better fit to the training data. I can reduce the deviation. And that means that the training error will be less. I'll have a smaller chi-squared. But now what I do in this model selection technique is I have some other data, which is called the test data, which I have not used to find the best fit, my best fit model. I've only used the training data for the best fit model. But now I go to the test data. So again, it exhibits some statistical fluctuations away from the ideal. And now I compute the test error, which is the chi-squared between this new test data and the best fit linear model I got for my training data. So now if I look at how the linear and the polynomial models compare, this higher order polynomial, did a good job of hitting the training data points, but it actually deviates further from the test data points. Ultimately, this polynomial kind of took these statistical fluctuations to be real features. So, it matched it quite nicely, but that it gets penalized for that when you present it with some data that has different statistical fluctuations. So generically, a model like this polynomial model is identified as overfitting the data if it tests worse than the other model. So like the linear model tests better than the polynomial model on the test data that it hasn't seen in making its fit. The polynomial model trains better, so it has a lower training error than the linear model, but it has a worse test error. So that's the technique we're going to use here. And so we just do a basic Bell experiment. It's done in quantum optics, so you can read the paper for the details of the experiment. Let me just show you the results. So here in blue, I'm plotting the training error and the test error for this model that involves a classical model with cause-effect influence. This is the quantum causal model. And so the quantum causal model has the lower test error, so it tests better and it trains worse. So, or to put it another way, this cause-effect model trains better but tests worse than the quantum causal model, and therefore it seems to overfit the data. And the idea is basically, that we think the reason it overfits the data is that for finite statistics, you always see a little bit of violation of the no signaling condition, right? You see, for example, the distribution over y might not be exactly the same for every value of s. This model has no way of thinking that those statistical fluctuations are real, whereas this model can. It can say, I will interpret those fluctuations as a real feature, a real dependence of y on s. And so it comes up with a best fit model that allows for that dependence. And then when it gets presented with the test data, which has different fluctuations, it does a worse job at predicting them. So anyways, even experimentally, that sort of explanation is disfavored. I want to end just by saying that I think getting to the bottom of what's the right causal explanation of quantum correlations is important, because if you look at general relativity, causal structure is very fundamental to general relativity. There's dynamical causal structure. So if you don't understand the right causal explanation of correlations in quantum theory, I think it's sort of unlikely that you'll be able to unify it with relativity theory. Okay, so with that, thanks for your attention, and I'll just leave some references that I talked about during the talk.
Thank Professor Spekens for your beautiful talk. Now it is open for question and comment. Anyone who would like to put any question, because you speak just.
Hello, Professor Spekens. Thanks for the talk. So my question is very naive question kind of thing. So whenever we say causation, so it seems, okay, some event, they are a cause-effect related something. But whenever we say inference, someone is coming in picture who is going to infer regarding that. Well, some agent is required. But in causation, it is not at all. Means how we think in causation, no presence of agent is that seems doesn't require. But inference, some agent present is required. Is there any fundamental difference? Or I'm thinking wrongly.
Did I hear you correctly? Did you say that in inference, I need there to be some agent?
Agent is somebody is someone is inference regarding this data.
Right, right. Yeah. So no, that's correct. That I would say that the main difference between a theory of causation and a theory of inference is a theory of inference is a theory that somebody uses to contend with the fact that they don't have perfect information. And so, in a theory of inference, you'll have things like Bayes' theorem about, how to make inferences about A given B. Whereas a theory of causal structure is not like that at all. Now, it's, to my mind, like in quantum theory, I've done a lot of work on, why it seems likely, to me at least, that quantum states are best understood as describing knowledge about some deeper reality, so that they belong on the kind of inferential side of things. But there's a problem with kind of disentangling in the quantum formalism what is about causation and what is about inference. And the field of causal inference has that same problem, even though there's no quantum mechanics, that even classically it's hard to disentangle those two notions. So things like Simpson's paradox and Bergson's paradox are all these statistical paradoxes are basically about confusing inference with causation. And there's like even my first example in the talk was about positive correlation that just allows you to make inferences and doesn't support causal effects. But yeah, so yeah, I think if I understood your question correctly, yeah, there's a big difference between those two types of theories, and only one of them is about an agent's incomplete information. And so that's why we need to disentangle.
If I just continue in this direction, let's say this, as you said, this quantum state is this means epistemic kind of things, means means inferential something. So in quantum gravity theory, we don't know the full theory also. In that case, then the space-time structure also will become agent dependent something. Its description will.
No, so if space-time structure is all about causal structure, then it's going to be in the causal theory half of things, which has nothing to do with agents. And so, in particular, if superposition is a concept that applies to states of knowledge, then the notion that different space-times go into superposition is incorrect. That space-times are just not the kinds of things that can go into superposition. They're not the, quantum state does not describe the physical state of space-time. So the, I would say it's, if one is worried about things like space-time being agent-dependent, the answer is just, oh no, space-time, that ought to be part of the causal theory, which is independent of all agents. And it's only our knowledge of those degrees of freedom, which that's going to be the subject of the theory of inference.
Okay. Thank you for your answer. Yeah.
Professor Spekens,
yes.
I have a question to ask. So some of the causal inequality that you showed, and violation of which imply either there is a quantum cause or there would be combination of direct cause and common cause. Now, if you assume that direct cause happens with finite velocity, then at least in some cases, there is a proof by Professor Gissin and his group that direct cause with finite velocity can be rejected by violation of some inequality. So I am thinking between these two alternatives, quantum cause and combination of direct cause and common cause, whether they can be differentiated by developing some more complex inequalities, violation of which will tell that quantum cause is the only possibility. Is there of course, there is an assumption that common cause, direct cause happens with finite velocity.
So there's been no assumption about the velocity of this causal
No, I am
influence.
thinking whether this can be thought that if we further assume that direct cause happens with finite velocity, then the other picture can be rejected.
I see what you mean. That certainly, like when I gave the list of reasons you might be unhappy with this causal explanation, something I could have added to that list is just that, not only does any such causal influence have to be superluminal, but because of this work by Gissin and his collaborators, it has to propagate at infinite velocity. So if you thought that, if you think that infinite velocity makes it even more implausible than merely superluminal, then you say, well, that's yet another reason to reject this. Yeah, and that's a reason on the theoretical side, I would say. But yeah, what's one of the nice things about this causal framework is that it doesn't stipulate, where these variables live in space-time. And to some extent, if you have the perspective that causal structure is more fundamental than spatiotemporal structure, so that this is really the primitive description, and maybe spatiotemporal descriptions emerge from descriptions of the causal relations. So what's nice about this sort of analysis is it really doesn't care about the nature, the spatiotemporal locations of these variables. So it just says whatever this causal relation is, whether it be superluminal, infinite velocity, or action at a distance, for example, with nothing mediating between it. It doesn't matter what any of that is. It still has the problem that it's fine-tuned, for example.
Yeah. Okay. Thank you. Thank you, Professor Robert Spekens, once again. So we move to our next talk by Professor Mark Wilde. Hello, Professor Wilde.
Sir, this is Tilman here.
Hello.
Do you hear me?
Yes.
Yeah. Now our speaker is Professor Mark Wilde. Mark Wilde is an associate professor at the Department of Physics and Astronomy and the Center for Computation and Technology at Louisiana State University. He is a recipient of the Career Development Award from the U.S. National Science Foundation, and he is associate editor for quantum information theory at IEEE Transactions on Information Theory and New Journal of Physics. His current research interests are in quantum Shannon theory, quantum optical communication, quantum computational complexity theory, and quantum error correction. So over to Professor Wilde.
All right, thanks a lot for the introduction. Thanks for having me for this conference. So I wanted to begin my talk by telling a bit of the story behind it. This is a new book that Sumit Khatri and I are working on. It's still in progress. It's a very long book. You see it's 970 pages. So we posted it to the archive in November of 2020, and we've still been working on it. Anyway, I actually want to share the link with you in the chat, and then here's a later version, the latest version. So while working on this book, one of the chapters is entanglement theory, entanglement measures. And while working on it, I realized there was a question that was still open regarding an important entanglement measure called the Raines relative entropy. This was invented by Eric Raines in, I would say, the late 90s, early 2000s. Okay, and so I realized there was still an open question to prove that it satisfies a fundamental property called entanglement monotonicity. Sometimes it's called selective entanglement monotonicity. So I thought about it for a while, and I couldn't figure it out. Maybe I should have thought about it longer. But I then went to Twitter. And I posted the question, has anyone proved that the Raines relative entropy is a selective LOCC monotone? And I pointed to the book. And this was in September. So then the same day, Jens Eisert replied to me, yes, sure. This is the proof. I was like, oh, okay. And then he wrote, he wasn't totally sure, is this right? And so anyway, we started conversing, and some point he said, yes, okay, I think it still works. I'll try to present a write-up. And then I bugged him about 2 weeks later. This was all, Twitter's in the public domain. And then he sent me an email. Anyway, so that was how this work came about. It was the first time that something came about scientific from Twitter. You see that there's a lot of junk on Twitter on the right. Anyway, so that's what I'm going to tell you about today. So let me share this. All right, everyone can see my screen, right?
Yes.
Great. Okay, so we've now posted this work to the archive as this paper. We submitted it to the International Symposium on Information Theory, and we're waiting feedback. This will be one of the first in-person conferences I'll get to attend if the paper is accepted. And indeed, it was a great pleasure to work with Jens Eisert. He's a famous person in quantum information theory who developed a lot of early results on entanglement theory. And so for him, it was also nice to return to this kind of fundamental question in entanglement theory. Okay, so I'm going to tell you about this result. Really, you should feel free to interrupt me at any point. The number of slides that I have, I don't know if I'll fill in the full 50 minutes. So really feel free to interrupt at any point, and this can be more of a discussion if you have questions. Okay, so we're going to talk about how the Raines relative entropy, this quantity that's been known for a while, is actually an entanglement monotone. And what's nice about it is that it's the smallest known one. And so why are we interested in entanglement measures? Well, we want to quantify entanglement in sort of a fundamental way, but we're also interested in operational tasks, in ways that you can use entanglement. And there's a famous problem known as entanglement distillation. And these entanglement monotones can serve as upper bounds on the distillable entanglement of a quantum state. And so I'll motivate everything by this problem of entanglement distillation. Okay, that's how we'll kind of start out. So let's start with some basic introductory remarks. Entanglement, it's really a key feature that distinguishes quantum theory from classical theory. There's remarkable things that you can do with it. It kind of comes to the forefront when you start studying quantum information and quantum computing. But I'd say it's sort of, it's very fundamental to quantum communication theory. So major insights were made a long time ago that entanglement can be understood as a resource for tasks like teleportation superdense coding and quantum key distribution. Without entanglement, teleportation and dense coding are not possible to simulate using classical resources alone. And then there's variants of quantum key distribution called device-independent quantum key distribution or entanglement-based QKD that rely on entanglement to work. Okay, so from this perspective, it's important to quantify and understand entanglement. Like, there's a basic question, you know, to do teleportation, you need perfect entangled states. To do dense coding, you need perfect entangled states. What if you have imperfect entangled states? Well, how many teleportations can you do using it? How many teleportations can you do approximately? And that's where this notion of distillable entanglement plays a key role. Okay, so it's common to consider two approaches that are actually intertwined with each other. I would say the operational approach kind of motivates the axiomatic approach. In the axiomatic approach, you list several properties that are desirable for a function to satisfy, to be an entanglement measure. And then you try to prove that a given quantity satisfies those properties. And those properties are motivated by the operational approach. And we'll see that in a few slides, how there'll be a task, I'm going to call it probabilistic approximate distillable entanglement. And there are several properties that we need to establish a given function as an upper bound on that, on the objective function of that task. Okay, so we're going to consider both of these approaches in this talk. And the main technical result is that this quantity called Rain's relative entropy that's existed for over 20 years will prove that it's a selective entanglement monotone. And I'll describe what this means in what follows. Okay, so we believe that our work elevates the Rain's relative entropy to a new status. Okay. All right, so let's recall the basic paradigm of entanglement theory. In this operational approach, so entanglement theory was one of the first resource theories that came into being in quantum information, possibly the first. And since then, there's been a lot of work on resource theories that have been inspired by the framework that Bennett, DiVincenzo, Smolin, and Wouters established. So we allow operations called local operations in classical communication for free. And I have this picture for you to indicate what an LOCC protocol looks like. It's a bit, I think it's sensible physically, but mathematically to describe it, it's a bit complex. So we just imagine an LOCC protocol. The two parties start with some state, rho AB. It's an arbitrary state. It could be entangled or unentangled. And then doesn't really matter who goes first. Alice can go first. She does a quantum channel that has as output a quantum system and a classical system. She sends the classical system to Bob. She could keep a copy. We can copy classical information, but it suffices for our purposes that she just fully transmits it to Bob. And then based on the value in this classical system, Bob performs a quantum channel. You can also think of this as a quantum channel that accepts a classical input, a quantum system, and outputs a classical system and a quantum system. This goes on, and then we allow them a finite yet arbitrarily large number of rounds of this back and forth. And at the end, they produce some states, okay? And so you might think that your objective is to convert an initial state to a target state. And then there's various ways to think about this task, you might demand that this happen exactly, right? And if you do that, I'd question whether that's really physical, because it's going to be hard in any experiment. I think impossible to convert rho AB to a target state exactly. So we'll introduce various notions of approximation in what's coming. If the target state sigma is the maximally entangled state, then this is what we call entanglement distillation. I was mentioning that just a minute ago. That's where you're trying to obtain from this rho AB a pure form of entanglement that can be used for teleportation or dense coding. It's also interesting in physics to think about reverse processes and efficiency. So, we can think that the source state is a maximally entangled state, and then the target state is some sigma. And if you're doing that, the task is called entanglement dilution. And there's questions about reversibility, like, is the rate of distillation the same as dilution? That's known to be true for pure states. You need to go to an asymptotic regime for that statement to be true. But then when you go to mixed states, it becomes irreversible. Okay, so I mentioned that if we demand an exact transformation, that's somehow unphysical. And we can make it physical if we allow for various kinds of errors. And there's at least two ways that you can do that. And we're going to, people have often thought about these separately. More recently, we're seeing people think about the two kinds of errors together and trying to quantify rates with both the probabilistic and approximate sense. So one way of allowing for error is that the target state is produced exactly, but only with some probability. And this is meant to mimic kind of what happens in experiments, like with a photodetector, maybe, conditioned on the photodetector clicking in the other arms of an interferometer, you generate a state. And so the state is heralded on a success signal in a classical flag register. So that we call probabilistic transformation. And then we can also have a notion of approximation. So not only could it be generated probabilistically, but also approximately. So the state in this register would be close to rho AB in some well-defined sense. Here we're going to use the fidelity measure. Okay. So if we allow for these two kinds of errors, we'll get a notion that we call probabilistic approximate distillable entanglement. Okay, and then that makes this acronym PAID. So you'll see that throughout. Okay, so what is the formal definition of probabilistic approximate distillable entanglement? This is a way that we defined it. This is how we defined it in our paper, and this is what we apply the Rain's relative entropy to. So this quantity is a function of a input state. You should think of it as the input state to this protocol. And we're trying to use LOCC to get as much maximally entangled state as possible. So we want the dimension of the maximally entangled state to be as large as possible. And we're going to allow for these kinds of errors. So the quantity will be a function of the state and an error epsilon. This will be the approximation error. And we're going to instead optimize over the probability of generating that state. Okay. So the objective function is the expected number of approximate E-bits. Okay. So, log D will be the number of approximate E-bits, but that number of E-bits will be generated only with probability P. And so this is the expected number of E-bits. Okay. D is the Schmidt rank of the maximally entangled state defined here. Okay, this is the density operator for the maximally entangled state. So we're going to optimize over P. We're going to optimize over all LOCC protocols. So here you see we discussed an LLCC protocol, so we're going to optimize over all of them. So you can see that this is going to be a difficult quantity to compute. It's very hard to optimize over all LLCC. So we're going to need some way to address that problem when trying to establish a bound on this quantity. Okay, so the LLCC, it's going to act on row AB. As input, it accepts systems A and B, and sorry for the bad handwriting. It outputs a classical register X, that's this X here, and two quantum systems A hat, B hat. These are the target systems up here, okay? So in this diagram, I did not depict the register X, but you can think of it as maybe you're allowing to just, since classical data can be copied, Alice and Bob just keep a copy of all the classical data at the end, and that could be the register X, or it could be some part of that classical data. And in fact, it will be just a part of the classical data, because in this model, I want X to be just a binary flag register indicating success. So in the case of success with probability P, you're generating the maximally entangled state approximately. And in case of failure, you generate some other state, and it doesn't matter what it is. This is just some density operator. Sorry, I forgot to close the parentheses. So it's some density operator sigma. So that's the problem. And then, this is the mathematical expression, which, and just in sort of English terms, it's the largest expected number of EBITs, expected number of epsilon approximate EBITs that we can generate from row AB by LOCC. So are there any questions about the task before we go on? All right. Not, let's continue. So a basic question is, if we could, we'd like to calculate this exactly, but I said that's going to be hard in general. So what we do instead is try to bound it from above. You could try to bound it from below, you could try to bound it from above. Here we're going to be interested in bounding it from above, and we're going to use the Rain's relative entropy to do that. And we're going to see how in this task, this property of selective entanglement monotonicity is critical. So why do we want to bound it from above? Well, we want to understand the fundamental limitations of entanglement processing, just like as we are in thermodynamics or in information theory. Okay, so in order to get this upper bound, we're gonna want a function that has some properties. So let's identify some key properties that this function should have. These are all basic properties that are considered in entanglement theory. And the most fundamental one, they're all important. The most fundamental one will be property 3. And so this is what we're going to establish for the Rain's relative entropy. So let's talk about them one by one. First is normalization. If we evaluate the function on an exact maximally entangled state, then it should be equal to log base 2 of the Schmidt rank. So if you have a Bell state, if you have a qubit Bell state, this would be binary log of 2, which is 1. And then it's consistent with the notion that it's 1 Bell state, 1 EBIT. If you have 2 Bell states, D will be 4. And this log base 2 will evaluate to 2. And it's like, okay, well, yeah, you have 2 Bell states. And so then more generally, we allow D to be, it doesn't have to be a power of 2. And then, that's this normalization property. Another property that's natural physically is a kind of continuity property. I didn't write details of it. But we want that if 2 states are close, then the function doesn't change very much. And then this kind of property mathematically is called continuity. What's often demanded for applications is to have like a precise form of this continuity. And then that has this historical name, asymptotic continuity. Okay. Then this is a key property. So if you have an LOCC protocol that transforms a source state to an ensemble of target states. So this is the kind of situation we're looking at here, right? There's the source state, and either we successfully generate an approximate maximally entangled state or some other state. So in general, we could talk about this kind of thing. You know, there's a classical flag register that indicates which state has been generated with probability P of X. Okay. And so this selective entanglement monotone, if you look in papers of Martin Planio and others, they just call this entanglement monotonicity. It's that under this free operation, the entanglement should not increase on average. So that's what this is saying. Okay. And so this kind of property is known for many entanglement measures. There's famous entanglement measures like entanglement of formation, relative entropy of entanglement. Squashed entanglement is a very nice one. And this property is known for them, but what remained open was to show this property for the range relative entropy. Another kind of property we need is that the entanglement, this function, is non-negative for all states. Okay, so let's now, so given these, suppose we have a function that has these properties. Let's show how these properties can be used to establish an upper bound on the probabilistic approximate distillable entanglement. Okay. So let's consider an arbitrary protocol of the form discussed in arbitrary LCC protocol. So it takes rho AB, the source state, to this classical quantum state. Okay. So let's suppose that the quantity possesses those four properties we discussed. So we can put these together to get an upper bound. That it's a very simple argument. So from the selective monotonicity, we'll start by evaluating the function on the state rho AB. We'll use the selective entanglement monotonicity, and the entanglement does not increase on average under this operation. So we get the average of the entanglement on the approximate target state and the entanglement of the other state, which we don't care about. So I forgot to mention another property. It should be zero on separable states, on an unentangled state. And so in this kind of protocol, if you're trying to get as much maximally entangled state out as possible, then it's probably best to just have this be a separable state, because then it's like, this is the useless part that you're not going to make any use of. So if indeed it's a separable state, then this function will evaluate to zero. But in general, it could be some other state, in which case we just drop this term and we get an inequality, right? So here we used selective monotonicity for the first inequality, non-negativity to drop this term here. So we end up with this term. We use the continuity and the assumption that the protocol is such that this fidelity constraint is holding. And then we can invoke, so then, we know that phi and phi tilde are close. And so then we can invoke the continuity to say, well, the entanglements of those states are close. Then we use the normalization. And then we precisely end up with the objective function. And then this upper bound holds for all possible protocols. There was nothing special about this protocol that we considered other than these, that it satisfies this constraint such that the phi tilde is close to the ideal maximally entangled state. So using that, we can then infer that this entanglement function is an upper bound on the probabilistic approximate distillable entanglement. I put the kind of approximate symbol here because we didn't keep track of the precise correction term that would be a function of epsilon. That was You know, so that kind of thing will appear when you go to an analysis. All right. So what you see here is that we have an operational task here. So this is like the operational approach to entanglement theory. And we wanted to say something meaningful about this quantity. And then that motivated the axiomatic approach. Like we seek out functions that satisfy these properties. Okay. And so that gives when you try to give these upper bounds on operational quantities, you're kind of naturally led to these properties. Okay. So now what we're going to do is try to find the smallest possible upper bounds on this probabilistic approximate distillable entanglement. I should probably say smallest known. You know, it could be that tomorrow someone has a clever idea and figures out something better. But given the history of entanglement theory, that's probably unlikely because people have been thinking about this stuff for a while. Okay, so I want to find the smallest upper bounds. So for this, we can turn to what's known about distillable entanglement. Let me say that the usual notion of one-shot distillable entanglement, I think this one-shot distillable entanglement was first studied by Francesco Buscemi and Nilanjana Datta, who was a speaker earlier today. If instead of optimizing over P, you simply set it equal to 1, then you get the usual notion of one-shot distillable entanglement. Okay, so for that problem, the best known upper bound is the Rain's relative entropy. Okay, so as I said earlier, the main thing that was not known about it is that it's a selective entanglement monotone, and this is one of the main results in the paper I have with Jens Zeiser. Okay, so let's focus on this now. Let's focus on what is Rain's relative entropy. So the idea of Rain's, if you're familiar with entanglement theory, you've probably encountered relative entropy of entanglement and logarithmic negativity. And so his idea was to combine those two notions into a single function and do an optimization. So, and to optimize overall density operators. So one thing that you see is that if you simply set sigma to be equal to rho, this is the relative entropy of two states. If you set sigma equal to rho, then the relative entropy will be equal to 0, and you'll end up with the logarithmic negativity of rho. But by doing this optimization, you can end up with something smaller, potentially. There are classes of states for which the Rain's relative entropy is no different from the log negativity, but in general, it can be smaller. Okay, and just to remind you, this T is a positive map called the transpose map, and this is how you can write it as a linear map. But you know, it corresponds to the usual matrix transposition from linear algebra. Okay, it's just transposition, not taking complex conjugate. Okay, good. That's the Rain's relative entropy. As an aside, I realized while preparing this talk that we actually don't need this to prove the main result. In the paper, we make it seem as if you do need it, so we might revise the paper a little bit. But it's possible to show that the Rain's relative entropy can be rewritten as an optimization in terms of a single relative entropy where you optimize, rather than over the set of bipartite density operators, a set of positive semi-definite operators that we'll call PPT prime for positive partial transpose. But it's not quite positive partial transpose. What we do is we make this norm constraint. And that's related to this partial transpose norm that's appearing here. You can work with this definition and the scaling property of relative entropy to show this equality. So that was proved by Konrad Oudenaardt et al. quite some time ago. And you can show this equivalence. And so this is a more compact form that can be useful to deal with at times. Okay, let's now prove the main result that the range relative entropy is a selective entanglement monotone. And what we'll see is that we only need two properties. When I was preparing the talk, I thought we needed the scaling property, but then we'll see in the proof that we don't. So what are the two properties that we need? One is a basic property of any distinguishability measure, including relative entropy. It's this data processing inequality. So if omega is a state, tau is a positive semi-definite operator. If you act on these states with the same quantum channel, n, a completely positive trace preserving map, then the distinguishability measure does not increase. So this is a basic property, and it gets used all throughout quantum information theory and quantum resource theories and quantum channel capacity theory, etc. The other property of relative entropy that we need is what I'll call a classical quantum decomposition. So if you evaluate the relative entropy for operators having this classical quantum form, so there's a classical system and a quantum system. Omega is a state. Tau, more generally, we allow it to be a positive semi-definite operator. So this right here will be a probability distribution, and this will just be a non-negative function. This will be a state, and this will be a positive semi-definite operator. So the relative entropy of a for classical quantum operators decomposes into a classical part and a quantum part. This is the classical relative entropy, also called Kullback-Leibler divergence, measuring the distinguishability of W and T. Okay, and then this is an average of the quantum relative entropies. Okay, so we only need these two properties. So it's nice that the proof is simple and you can actually show it in a talk. We're also going to introduce a notion. We're going to use a notion that Raines introduced. It's been used a lot to understand entanglement theory and other tasks. It's this notion of a completely positive partial transpose preserving channel. So we say that a bipartite channel, so a bipartite channel has an input for Alice and an output for Alice, and an input for Bob and an output for Bob. We say that it's completely positive partial transpose preserving if this map is completely positive. What is this map? You act first with the transpose map on the system B, and then you act again with the transpose map on the system B prime at the output. Okay. What you can show, and what I won't show, is that LOCC channels. So this whole, early on, we had this diagram. In some sense, anything is a quantum channel. Everything and anything is a quantum channel. And so this process, realized by the back and forth, realizes a quantum channel from rho AB to, from systems AB to systems A hat and B hat. Okay. So it's been known for a while that an LOCC channel, because there's no quantum communication that crosses the boundary connecting Alice's lab and Bob's lab, it's possible to show that an LOCC channel is a C-PPT-P channel. Okay. And it's related to the fact that a separable state is a positive partial transpose state. You can think of what we're talking about as the dynamical generalization of that well-known fact. Okay, so let's go back to where we were. We're trying to prove that the Raines relative entropy is a selective monotone, selective entanglement monotone. And we're going to do it by using this fact that LOCC is contained in this larger set of operations. We can then define a selective PPT operation to be, it's very much related to this notion we just defined. So it's a collection of bipartite maps such that each map is completely positive, and this transpose version of the map is also completely positive. That's sort of in line with this condition. And then the sum map is trace preserving. So if you had just these two conditions, this is often called a quantum instrument. But then if we add this, we could say that it's a PPT quantum instrument. So if I, selective PPT operation, PPT quantum instrument, those are names that you can use for the same thing. So let's then prove that this property holds. All right, so that the range relative entropy is a selective entanglement monotone. So P of X rho X will be the ensemble that results from a selective PPT operation. And then we want to show that the range relative entropy does not increase on average. How we're going to do it? We're going to use just those two properties of relative entropy. One is that data processing, the other is the classical quantum decomposition. So the proof will be very basic, and then there will be some algebraic manipulations involved. Okay, so we're going to take the selective PPT operation, we're going to place each map here, and we're going to have this classical register which will be where we place the outcome of this PPT measurement. And if we do this makes a quantum channel. It makes a trace preserving completely positive map. How do you see it's trace preserving? Well, if you take the trace, you'll trace out this, and then you get the sum of the PXs, which we said by definition is trace preserving. Okay, so in the definition of the range relative entropy, at least the first one I presented, you optimize over all states. So let's consider sigma to be an arbitrary state, and we'll define this to be the probability distribution that results from doing the instrument, acting with the instrument on sigma, and this will be the post-measurement state. Okay, so first step, let's start with the relative entropy between the state of interest and this sort of test state, sigma, okay? Because remember, that's involved in the range relative entropy. We use data processing to say that under this quantum channel, the measure does not increase. Let's write out the channel acting on rho AB and sigma AB. So we get this step here. So we get this classical quantum form. Let's use the definitions of rho X, PX, QX, and sigma X, right? So this is just applying definitions. PX was defined like this, rho X like this, QX and sigma X. Let's use the classical quantum decomposition to write this relative entropy as a sum of a classical part and a quantum part. We're going to invoke a known fact from the PhD thesis of Jens Eisert and a paper published in PRL of Martin Planio that so if I take away the logs, this partial transpose norm is called, it's related to something called negativity. So that does not increase on average under a PPT instrument. So that explicit statement is shown in Planio's PRL paper. And then log is a monotone function. Okay, so we'll use that also. So remember this, the range relative entropy is the sum of this term and this term. Okay, so what we're going to do is we're going to add those. Then this is like the objective function of the range relative entropy. We will apply this inequality we just established. All right, so this is greater than this term, the quantum term and the classical term. We're going to use the result from Eisert and Planio's thesis to get to this is larger than that. Then I guess this is a part I'll skip. Indeed, we're getting close to the end of the talk. I guess I did not have as much time as I thought. So you can do some algebra with this term and this term and use the concavity of logarithm to get that this term plus this term is larger than this, right? So then now we're basically there. We can take out the sum, and then we see that here is a state, sigma x, that could be like a test state for rho x, and then the range relative entropy involves an infimum over all such states. So if we do that, the quantity is lower. And then that's basically the end of the proof. Sigma is an arbitrary state, so we're allowed to take the infimum over all states and we get the desired inequality. That's the end of the proof. That's really the end of the talk. In the paper, we show how this proof generalizes the quantum Renyi relative entropies. So it goes, well, actually the proof we did in the paper, we did it in a very general way. We said, let D be a function that satisfies data processing, and rather than this equality, we made it an inequality, because you see that suffices for the proof. And then everything just goes through also for Renyi relative entropies, and then you can get refined bounds on the page. So with the previous proof that I showed you, what did we need? We needed selective entanglement monotonicity, we needed non-negativity, we needed continuity, and we needed normalization. So you can show that the Renyi relative entropy, the range quantity based on Renyi relative entropy satisfies those properties. And then this will be the correction term related to continuity. Okay, so that's really the end of the talk. Main results, we have this fundamental property for range relative entropy, and then this application in bounding the probabilistic approximate distillable entanglement. With that, I'll stop. Thank you.
Thank Professor Wildred for his beautiful talk on such complex subjects. So now it's open for question or remarks. Yeah.
I think there's a question from Bihalan.
Bihalan Bhattaji. Yeah, you speak.
Hello. First of all, I'd like to thank for this nice talk. But I don't know whether my question will be relevant in this context, but I'd like to make a comment that recently it has been shown that entanglement manipulation is irreversible even if it is asymptotic regime under general non-entanglement operation. So here you are also considering the range relative entropy is a monotone under beyond LOCC. So is there any connection between these two things?
That's a great question. Thank you for that. I think you're talking about the paper of Ludovico Lamy and Bartosz Regular. Is that right?
Yes.
Yeah, that's a very nice paper. And you know, what did we use here? What did we use in this proof? So that's a good question. Let's examine the proof. What did we use? We used data processing, but then this part, we used that we have a selective PPT operation. And so to generalize it to a non-entanglement operation, you would need a different measure, right? So it's a very good question. Maybe there's a way, you know, if we go back to the range relative entropy, you see it's the sum of the relative entropy and some other entanglement measure with log, right? So if there's some other entanglement measure that we can place here, perhaps the one they used in their paper, I think they called it, what do they call it? Tempered negativity. Yeah, you could possibly put that here and revisit this proof and see whether it would hold more generally. And so you see the manipulations that are done here are pretty simple, right? So maybe that would lead to something interesting. But as it stands, this proof is limited by this step, and this step relies on having a selective PPT operation.
Okay.
Good.
Thank you very much. Thank you very much.
Yeah.
Any more question or comment?
It's like from
Rito Broto, yeah. You speak, yeah.
Hi, Mark.
Hello.
Thanks for a very nice talk. Just two quick questions. I mean, one is standard for me, actually. I mean, I just want to know whether, is there a kind of Gaussian kind of version or infinite dimension version in this relative?
That's a very interesting question. That's actually something we're working on.
Okay.
Okay. So there's a I've hired a postdoc. His name's Hemant Mishra, coming from Indian Statistical Institute in New Delhi.
Yeah, I know him. I know him.
Yeah. And we've been working on this question, and so
excellent.
You know, it's we could discuss it further if you like. But yeah, sorry, I'm kind of scrolling around randomly. I was meaning to hum in on this. So you could ask the question, when rho AB is a Gaussian state, what can you say? And you know, it could be a bosonic Gaussian state or a fermionic Gaussian state. And there's a formula that's known for the relative entropy of Gaussian states and the negativity as well. And you could try to solve this. You know, what you could do is restrict the optimization to Gaussian states and then try to solve this. And that's the problem we're working on. And it's sort of just underway. Yeah. The hope would be the hope would be that you could find like a maybe exact expression. I will say that there's a paper of someone named Xiao Yu Chen. Let me write his name in the chat. Xiao Yu Chen, Gaussian relative entropy of entanglement. This is from, I think, 2005. And then in that paper, he also derived the formula for the relative entropy of bosonic Gaussian states.
Okay. Yeah.
Any more questions?
Yeah, I think I have noticed. Oh, I have one more question actually. Mark, if it's not too late. Okay. So I think I missed at some point because of a network issue. Was it someplace you were talking about a completely positive map from A to AB to A dash B dash, such that you take transposition, compose that map, compose with the other transposition in this way, right? Yes. Yeah. So will it be slightly different from the completely positive, or it will be a subclass of completely positive? I mean, like if you have a complete co-positive thing also is there, right?
Okay.
Or is it just a completely co-positive?
Right. So this is a good question. If you do a full transpose, so remember this is a bipartite channel, right?
Right.
So if at first you do a full transpose,
oh yeah, right. It's a bipartite channel. Right.
Yeah. So if you do a full transpose, then the channel, then a full transpose, that's no different from completely positive. But if you do partial transposes,
right,
then you get something that's not all. Like for example, if you take the channel to be a swap channel, that will not. When you do this composition, you will not get a complete positive map. You can think of this as being equivalent to you look at the Choi operator of this bipartite channel, which will involve 4 systems, and then you take the partial transpose of the Bob systems, and the Choi is PPT if and only if the map is C PPT P.
CPT.
Yeah, it's kind of a lot of You could just call it a PPT channel, but like there are technical reasons why Gilad Gore and others prefer to call this completely PPT preserving.
Okay. Thanks. Thanks a lot.
Sure.
Any more question from anyone or comments? Yeah, if not, then let us thank once more Professor Mark Wilde for his beautiful talk on such complex things. Okay, thank you.
Thanks
Thanks
for having
to
me.
all the speakers in this session, as well as all the participants. So we are closing this session. We're closing this session for today, and tomorrow is our last day of the conference, and it will start at 11 a.m. Okay, thank you.